everybody. Thank you so much for enrolling in the Aerospace Cybersecurity Satellite Hacking course. This course teaches you the foundations of satellite cybersecurity by guiding you through the four main phases of attacking satellites. It goes through reconnaissance, where we'll be employing methods to scan for information about satellites. We'll go over communication dissection in Module 2, where we will be analyzing the communication protocols and encryption methods behind satellites. Then we'll move on to decoding satellite communication. And then finally, we'll do a vulnerability analysis module of satellite systems. All of this will be interactive. We'll have quizzes at the end of each lesson within the module, alongside activities that you'll be pursuing after I show you how to do them within the lessons. So all this is meant to develop your skill set and not just your knowledge base within satellite systems and also aerospace cybersecurity. You'll learn a lot about the underlying concepts of what makes satellites work and function, so you understand both from a red team and a blue team perspective about the satellite network infrastructure and how it functions and core vulnerabilities within it. You'll also be able to apply your knowledge to conduct digital forensic scenarios on real-life satellites in orbit. A little bit about me. I first began off as a software developer alongside doing mechatronics work. I started doing software development about 10 years ago, and I got contracted to start doing cybersecurity focused work about a few years ago after I was given my first job there. I've also done research for NASA, where I conducted scientific research on meteorites alongside space systems. And over the years, I noticed a really unique intersection between cybersecurity, software, and space systems, which brought me to harness a really valuable knowledge base, not only within satellite systems, but also piqued my interest to look into core vulnerabilities within satellite network infrastructure. So on the side, I build a lot of aerospace cybersecurity programs alongside multidisciplinary engineering projects in order to spearhead more democratization endeavors within aerospace cybersecurity. You can learn more about me on my website, angelinaspoy.com, or my cybersecurity-focused research website, g4lxy.space. All right, so who is this course meant for? I really made sure the course was very beginner-friendly. So if you're a beginner who's really interested in learning more about the field, such as aerospace cybersecurity, and just develop your overall pen testing skills, I would recommend you take modules up 1 to 3. We'll be diving more into more advanced attacks and techniques in module 4, but overall, this course is very beginner friendly. I will also recommend this course for any cybersecurity enthusiasts. So if you're already experienced in cybersecurity and want to learn and translate your skill set to the satellite or aerospace infrastructure, this course would be great for you. And finally, I really wanted to cater this course to all beginners along the spectrum. So if you're a beginner in cybersecurity but have a profound knowledge in aerospace, and also but want to learn more about cybersecurity tools and programs, this course will be tailored towards you as well. So why should we take a satellite infrastructure and a satellite hacking course style? Well, over the years, there's been a rising democratization of space systems and a demand within the industry. However, this demand within the industry has also been met in tandem with bad actors who are trying to exploit this newfound technology to conduct malicious intents. So in order to conduct this growing threat, we need to think from a defensive perspective and be forthright about employing our knowledge to secure these systems. So this course instructs you on the foundations of satellite security and detection methods for very common satellite cyber attacks, such as jamming, spoofing. We'll be diving more into that later on in this course. So why satellite security? Why is it important? Well, I would say aerospace security is a huge growing field. It's very interconnected. There's lots of playing parts within it. And it's vital not only for the future of technological programs as more aerospace infrastructure is developed, but also for minimizing risk within the sector. As more cyber systems are deployed within a space-based environment, we need to increase the amount of resilience we have within these digital systems, especially for aircraft controls, communication networks, satellite operations, in order to mitigate the vulnerabilities and risks that are inherent within this infrastructure. Lastly, I would say aerospace cybersecurity is a great modality for developing your cybersecurity skills. Learning just generally about aerospace cybersecurity equips you with the proper expertise and skill set to safeguard critical systems and infrastructure, which you can apply to any field of cybersecurity you decide to pursue in the future. All right, so we don't have a lot of prerequisites for this course. It's very beginner focused, like I mentioned before. The first two modules will be heavily focusing on learning the conceptual part of satellite infrastructure, but the last two modules a little bit more hands-on and technical. I would recommend you have some basic familiarity with the Python programming languages, because we're going to be writing some simple scripts with Python and also utilizing a lot of open source Python programs that are out there to conduct digital forensics and open source intelligence on satellites. So make sure your computer, laptop, machine has Python 3 and pip installed. If for some reason you don't have Python installed, go to python.org/downloads and just follow through the download instructions on that site. All right. So here's a general course overview. The course is split into 4 modules. The first module will be focusing heavily on satellite reconnaissance. So this entails what information we can extract from satellites. The second module will be looking for ways of eavesdropping satellites and performing communication analysis. So we're going to be focusing on what security researchers call the link segment. Module 3 is reverse engineering and decoding communication. A lot of threat vectors and vulnerabilities exist within the communication link of satellites. So I'll be teaching you a couple of techniques that red teamers use in order to reverse engineer communication. And lastly, we'll be going over very common vulnerabilities and attack surfaces inherent to most satellite systems and how a red teamer or a blue teamer would approach the situation. So holistically, the class scope consists of the following topics. We'll touch upon orbital mechanics, satellite reconnaissance, decoding satellite communication, satellite onboard systems, listening to satellites by inspecting radio frequencies. We'll be conducting vulnerability analysis on multiple satellite systems. We'll be looking through different examples. We'll also be looking at common attacks employed against satellite systems and understanding detection of satellite attacks and how we can approach them from a defensive standpoint. So the fundamental skills you'll be developing throughout this course is garnering a deep understanding of satellite communication systems. We'll also be developing your space-based open source intelligence skills. So you'll learn more about investigation and how you can learn more about the components and subsystems located within satellites. You'll also be working on your Python and scripting skills to receive satellite telemetry and valuable information. We'll also be doing a little bit of digital forensics and employing techniques to conduct investigations on satellite attacks. We'll also be decoding and identifying satellite communication protocols. And finally, just doing incident analysis and detection of common attacks run on satellites. I also wanted to give a very warm thank you to Pentest Magazine for giving me the opportunity to host this course. Not a lot of cybersecurity companies have courses or are open to having courses as unique as this one. So please, if you have the time, make sure to check out Pentest Magazine. They have a wide range of courses, not just satellite hacking, but I noticed they had an automotive one recently. They've had malware courses in the past. It's a very great company. And they also run I think monthly or weekly IT security magazine, and they host a wide range of courses as well. So you can check them out at pentestmag.com. There's also the Aerospace Cybersecurity course description on their site as well, if you're interested in looking through the entire syllabus of this course. With that being said, I hope you guys enjoy the rest of Module 1, and thank you so much again for your interest in this course. Hello, everybody. Welcome to Lesson 1 of Module 1 of the Aerospace Cybersecurity Satellite Hacking course. In the first module, we'll be talking about satellite reconnaissance and reconnaissance techniques. So for the first lesson, we'll be covering over a very basic conceptual knowledge of satellites and ground stations and how they function and operate. So firstly, what is a satellite? There's not a lot of specifications you need in order to qualify to be a satellite. All you need to do in order to qualify to be a satellite is be an object in space that orbits or circles around a bigger object. So this could include many things, but they're generally split into two broad categories: natural satellites and artificial satellites. Natural satellites, as you might have guessed by the name, are naturally occurring. So these include moons, comets, asteroids, etc. As long as it's a naturally occurring object that orbits around an object that has bigger mass, it can qualify to be a natural satellite. A more modern version of a satellite is an artificial satellite. Artificial satellites haven't been around for that long. The first artificial satellite was introduced by the Soviets in about 1957 when the Sputnik 1 was launched, and since then we've been developing more artificial satellites that have been deployed into orbit. Some examples include a Hubble Space Telescope, the International Space Station, and the GPS satellite constellation. Satellites have their roots back in the 1957. As I mentioned before, the Sputnik was the first artificial satellite that was launched into orbit, which was developed back during the Cold War by the Soviets. Since then, a year later, the United States deployed the first artificial satellite into orbit called the Explorer 1, as shown in the bottom left-hand picture. In 1971, a low Earth orbit satellite was created by the Soviets for scientific research and military purposes called the Salyut 1. A year later, the first land reconnaissance and remote sensing satellite was created by NASA, which was the Landsat. And then in the same year, in 1972, Navstar 1 was also deployed into orbit, which was the first GPS satellite, which allowed for pinpointing of locations on Earth. And then in 1998 was the deployment of the famous International Space Station. And then now a more modern example of satellites that are being deployed into orbit are the Starlink constellations. The first Starlink batches that were sent out into orbit have their roots back in 2018, and now they deliver broadband internet around the world. So what are satellites used for? And the general answer to that question would be a lot of things, but usually we can break it down into 4 broad categories because satellites have a wide range of applications, especially for scientific and technical purposes. but they usually boil down to communication, remote sensing, navigation, and astronomical research. So communication satellites, they're usually often deployed for long-range communication. The reason being is that short-term communication on the ground, it gets pretty problematic when you're trying to transmit information and signal over long distances. For ground-based communication, we technically use a lot of transmitters and antennas, but the problem is there's a lot of interference when you're trying to communicate through on the ground over long distances. So things such as buildings, mountains, and other naturally occurring objects can interfere with those signals on the ground. So in order to work ourselves around that problem, we've deployed satellite communication methods for communicating, which is a lot more seamless and involves way less interference, because now you can avoid interference on the ground by sending up a signal straight up into space, so there's minimal interference by the atmosphere, and then have a satellite in space relay that information back down to another location on Earth, making long-range communication a lot more pertinent and applicable. Satellites for communication purposes often include a transponder, which receives and sends communication signals from Earth, which allow for long-range communication. And these types of communication satellites are often used for media transmissions, such as radio, TV signals, internet, phone services, and much more. The second type of satellites are for remote sensing. Remote sensing deals with monitoring and obtaining information and research, most likely for meteorological research or scientific research about the Earth. So these kinds of satellites are often deployed by scientific-based institutions, NASA being one of the main contributors, and they perform a wide range of functions, such as tracking for environmental patterns, what's going on with climate change, so forth, forecasting for weather observations, conducting geographical and topological mapping of things such as like mountains and high altitude natural landscapes, and much more. The third broad category of satellites is for navigation. This includes the sending of telemetry data, such as timing and location, within a space-time environment. This is often used for geolocation purposes. So whenever you're on a mobile application, such as Google Maps or Uber, or anything that requires pinpointing your location at a specific point, it often relies on a huge constellation of navigation satellites within space called the Global Navigation Satellite System. We'll be talking more in depth about it later on in this course, but in general, it's a huge constellation of satellites that handle navigation telemetry data. Lastly, in my opinion, this is like one of the coolest applications of satellites, is for conducting astronomical research. So these are just like huge, giant telescope satellites that are sent up into orbit, and they use a wide range of electromagnetic-based techniques, one of the most common being infrared imaging, to investigate and look for and analyze different types of celestial bodies to conduct astronomical research. So these can include like telescope photography, or analyzing the infrared imaging of various celestial objects within space. James Webb Telescope is one that comes to mind, but any telescope that's been sent out into orbit has been conducting astronomical investigations. So the space industry, as I mentioned in the first video, has been growing significantly annually. If you look to the image to the right, I put a chart displaying the global space economy, and you can see it's risen significantly over the years, and the market value has increased drastically. This is mostly due to the reduced financial barrier to entry of deploying spacecraft into orbit. In the past, it was extremely expensive to send anything to orbit because of the lack of technology and scientific research that was going on. But now, with the growing accessibility of space-related technology, it has become way more accessible for companies to get involved and contribute. However, like I mentioned before, this growth is unfortunately also met in tandem with bad actors who are trying to exploit this valuable technology to compromise space systems, such as satellites and a wide variety of other spacecraft as well. This is extremely concerning because hacking satellites could result in a wide range of cascading repercussions, mostly involving infrastructure damage, because if you are able to hack into one satellite, that could lead to collisions with multiple other satellites, especially with the amount of traffic that's going on within low Earth orbit satellites. If one satellite is compromised, that could cascade into a wide range of collisions. And I'll be mentioning an example in the future where a satellite that was exploited in the past came crashing back down into Earth, because you have nothing like, if you compromise a satellite, you also compromise its subsystems, and that could cause a wide range of failures. It can also cause disruption of services, so things such as like the global navigation system, constellation, or internet services. All kinds of functionalities can be rendered useless by hacking into satellites, which could cause a huge disruption. The third repercussion are huge financial losses. Satellites, as you probably might know, are extremely expensive. Putting anything into orbit currently is very expensive. Although much more accessible, it's still very expensive. And things are sent up into space depending on their weight. Satellites are not too light, so putting a satellite into orbit is extremely expensive. So, like I mentioned before, wide collisions and disruption of services that could result from compromising a satellite can result in wide range financial losses. Lastly, hacking a satellite can lead to collisions with other satellites and debris that comes crashing back down into Earth, damaging not only just personnel, but also infrastructure. A case study of a satellite attack that happened, this was back in 2000, is for the ROSAT X-ray satellite. So this was a joint collaboration between the US and Germany, where the organizations collaborate together in order to make this astronomical research satellite that used X-ray to conduct astronomical research. And a team of hackers were able to hack into the computer systems running the satellite in the Goddard Space Flight Center. And they were able to hack into the solar panel array subsystem, or subsystem that controls that, and rotate the satellite panels to aim towards the sun. Within space, there's no atmosphere, so it's a very harsh environment where the sun, any rotation or adjustment of solar panels could lead to frying of batteries because of the harsh environment. This team rotated panels to aim towards the sun, which fried the satellite's batteries and caused it to crash back into Earth in 2011. A more modern case study of satellite attacks involve the Starlink involvement in the Russian-Ukraine conflict. During the conflict, Starlink satellites that were orbiting around Russia were infested with a wide range of hacking attempts on the communication link, such as jamming and spoofing, which resulted in a lot of conflict between SpaceX and Russia. So in order to combat these wide range of threats I mentioned in the previous slides, there have been some efforts presented to modernize spacecraft cyber systems, especially within satellites. And there has been some rising initiative for ensuring the cybersecurity and integrity of protocols and systems in place. One main example includes the CSFC requirements, which is required for all military-grade satellites, and this was a set of requirements that was established by the NSA for ensuring the security of satellite communication transmissions. And although there has been multiple other attempts and requirements, such as this one, by other organizations, there still is a lack of globalized standards, which is really concerning as more companies, especially smaller companies, deploy satellites into space. Many startups perceive cybersecurity as being too costly, especially within such a rapidly changing environment, especially within the space industry, where you always have to act quick in order to evade bankruptcy and other financial repercussions. A lot of companies really deem satellite cybersecurity, unfortunately, as too costly and too niche to really hone in and make sure they have a system in place in order to secure their systems. So currently there's no global requirements that need to be adhered to in order to maintain the integrity of systems running on satellites, making them really vulnerable. So with the current cybersecurity guidelines I mentioned, there is one main one called the Space Policy Directive 5, which is a document that establishes the key cybersecurity standards for America's growing space cybersecurity infrastructure. And it notes the following security measures for protecting space systems. Firstly, it notes communication protections. So this includes protecting against very common attacks such as jamming and spoofing from ground-based sources. The second one is the security of ground stations and ground systems. Ground systems are what's operating and sending commands to satellites up in space. They're also vulnerable, and hacking into these systems could compromise the functionality of the satellites, so making sure those systems are intact. The third thing they mentioned was employing standardized cybersecurity responses and protocols, so making sure there's a standardized encryption protocol that all and standards that all satellites adhere to. The fourth one was managing supply chain risks. The development of satellites require multiple working pieces. It's like a huge puzzle, and each piece comes from different manufacturers. So there needs to be some kind of policies and security guidelines in place in order to mitigate risks, especially with the amount of components that are needed to develop satellites. And then they also mentioned physical layer security. So this is protecting satellite systems from tampering and avoiding the introduction of rogue components that could compromise the functionality of a satellite. And we'll also be diving into subsystems later on in this module, which could be stolen or tampered with, which can cause the entire satellite to malfunction, because I'll be mentioning in the future, a lot of components within the satellites communicate with each other and communicate to the onboard computer. And lastly, they mentioned avoiding unauthorized access attacks. So this is telemetry, tracking, and a command protection, which I'll be diving a little bit more into in the next episode. So diving into the components that make up a satellite, we have the frame, which is the structure that holds all the subsystems and components together. Then we have the solar panels, which is responsible for providing electrical energy to satellite components. They work by harnessing and retrieving solar energy from the sun and converting that to electrical energy and then distributing it towards all the sensors and components on the solar panel. And then we have the onboard computer. This is responsible for managing all the control operations on a satellite, processing data from the multiple sensors and control systems on the satellite, and then sending that data to and from Earth. Then we have the thermal control of the satellite. This regulates the temperature of the satellite to protect its components. The space environment is extremely harsh, so this control system is integral for maintaining the temperature of extremely sensitive components that make up the satellite. We also have thrusters. These are important for moving and configuring the orientation of the satellite and moving it from point A to point B, and also changing its attitudes, such as its orientation, like yaw, pitch, roll. We'll be talking a little bit more about that soon. We also have communication systems that make up the satellite, such as the transmitter and receiver. The transmitter and the receiver are used to send and receive communications from ground stations on Earth. We have the antenna, which actually conducts this communication process by translating the data that is processed on the satellite into radio waves for the transmitter and vice versa for the receiver, which takes in radio waves that are sent and transmitted by ground stations on Earth and translating that into data that can be interpreted by the onboard computer on the satellite. Some satellites also contain radar, which is similar to a transmitter, but it uses pulses of microwave radiation to send information. Most satellites also contain radio GPS, which communicates with other GPS-based satellites to get the location of the satellite over Earth. And some satellites also include a camera, which gets footage using the light from the Earth's surface. When light from the sun reflects on the surface of the Earth, it gets processed by the camera, which is used to conduct imaging. There are a wide range of satellite sensors, which are employed depending on the type of satellite, but the main ones include optical sensors. So these sensors senses for visible, near-infrared, and short-infrared waves to form images of the Earth's surface. There are radar sensors, which detect for imaging by using radio waves and retrieving quantified measurements of the surface of the Earth by getting information about the reflected radio waves that are sent out. There's also thermal sensors, which capture the heat radiation emitted from the surface of the Earth in order to monitor for temperatures on the surface and retrieve elevation maps of specific terrain, such as high altitude or low altitude terrain. There are also sensors called LiDAR, which stand for light detection and ranging. This technology utilizes laser pulses in order to get 3D data output. You might have used some apps on your phone that use LiDAR in order to get 3D scans of objects. This is the same concept, but just employed in satellites at a much broader distance from Earth using strong laser pulses. And lastly, we have microwave sensors. Microwave sensors use really long wavelengths, and these long microwave electromagnetic waves can penetrate through things such as ice and vegetation in order to conduct remote sensing applications such as agriculture and drought monitoring. In conjunction with satellite sensors, satellites also host a broad digital infrastructure. It all routes down to the onboard computer, which handles, it's like the brain of the satellite. It handles everything, including communication systems, processing data from multiple input sources like sensors and navigation protocols. It's responsible for handling operations within subsystems of the satellite, and much more. There's also platform units, which are units involved for constructing the satellite. So they can also be referred to as subsystems, which I'll be talking more extensively about. These are just used for general purposes and activities conducted by the satellite, such as thermal control and regulation, supplying power to different components of the satellite, propulsion for orientation changing and attitude and leveling, and much more. Software also comprises the satellite digital infrastructure, and it is responsible for operating the underlying programs and various functions of the satellite. So it's the code that's running on the satellite to pretty much control everything that's going on. And then finally, we have payloads, which are mission-specific instruments, commands, and objects carried on board the satellite to carry about specific tasks. So let's talk a little bit more about satellite computing hardware, since it's extremely important. Like I mentioned before, the onboard computer is pretty much like the brain of the satellite and controls everything. And some of the functions it's responsible for handling include control law implementation, processing payloads that are sent to and from the satellite, handling communication, not just with various components within the satellite, but also to ground stations, and also interpreting, handling, streamlining with data that gets passed around within the satellite, and interfacing with sensors as well. The onboard computer can also be broken down into the following modules. It includes the switching module, the telecommand, telemetry, and time command module, processor module, the input-output module, and the local mass memory module. We'll dive more into the technicalities of this later, but I just wanted to mention specific components of the onboard computer if you're interested. That being said, let's dive a little bit more into the broader space system and how it works. So, more broadly, a space system is a system that works together in order to achieve a specific mission in space. I know it's pretty abstract, but it pretty much encompasses every spacecraft you're going to deal with, and it consists of three main components. The first is the ground station, which is any infrastructure or device on the ground that transmits and receives signals from a spacecraft in order to maintain communication with it and send commands to it. The second main component is the space vehicle. So this is any vehicle in space. It doesn't have to be a satellite. It could be a rocket, whatever. And it just has to be a device in space that is able to transmit and receive signals from a ground station. And the last component is the communication link. This is the link that connects the ground station and the space vehicle, where it allows for data to be transferred between not just the ground station and the space vehicle, but also between space vehicle and space vehicle. So it pretty much handles all the communication that goes on within the system. Okay, so let's talk a little bit more about the ground station. And ground stations are a series of systems to command and control satellites within space and process their data outputs. They have two primary functionalities. One is command and data handling. So they initiate commands and execution directions to spacecraft in the air, alongside sending payload data, which is just code or any set of instructions telling the satellite or the space vehicle to do something. It's also responsible for handling payload controls, which handles and collects information that is transmitted by the satellite. So I just wanted to touch a little bit upon satellite and ground station communications. We'll be talking about this more extensively in the course because it's such a huge threat vector. And communication between a satellite and a ground station involves the exchange of data between satellites and ground-based facilities. It doesn't have to be the huge radio antennas you see on the ground, like the S-band, the K-band antennas. It can also be general purpose transmitters and receivers that are used more by hobbyists. That can also be considered a ground station and satellite communication. But any communication between a satellite and a ground station has 4 working parts to it. The first is the uplink, which, if you look to the picture on the left, is the communication link where a ground station sends up signals to a satellite. It goes one way. The downlink, which is the opposite, where the satellite sends communications back down to Earth to a ground station. The main component that handles the communication aspect of this is called the transponder. And this device is used to convert the received signal to another frequency and retransmit it via the downlink. So it's pretty much like a relay, relaying data just on another frequency. So there's no frequency overlap. And lastly, there's a lot of data processing and tracking systems in place. So ground stations process the data that is retrieved by satellites in order to maintain a communication link that is continuous and to track the satellite down whenever necessary. I just also wanted to go over an example of a satellite system architecture. There's multiple different satellite system architectures in place, and it really depends on what type of satellite you're dealing with. But an example one is one to the left, which deals with mobile and telephone services. So breaking it down, we have the Earth station, which is the central command and control system for the satellite system, and it manages the mobile stations and radio resources, such as the frequency bands and so forth. There's also the mobile switching center, which interfaces with the cellular network and is typically managed by the Earth station. Next, we have registrars, which their primary function is to secure and authenticate users, making sure that bad actors don't exploit these systems. And then lastly, we have the public switch telephone network, PSTN, which is connected to the Earth station via a gateway, and this is what is used to route calls to cellular devices. So you can see that satellite systems can be broken down into many working pieces as demonstrated here. And this is really important, especially if you're running a digital forensics scenario or any kind of investigation of an attack. It's to break down the satellite systems and to make multiple working pieces so you know what's exactly is going on with a specific attack that occurred. Hello, everybody. Welcome to Lesson 2 of Module 1 of the Aerospace Cybersecurity Satellite Hacking course. In this lesson, we'll be going over information extraction methods so you can target and get selective information about the satellite at hand. So here's like a general informational structure layout of a typical satellite. The first bit of information you can get is spacecraft design. So this includes pretty much all the components that make up the the spacecraft, such as the software, firmware, any cryptography methods, the data bus, thermal control, power, and so on. The second portion is made up of the communication section. This includes all the communication equipment needed to operate and communicate with the ground station, channel scanning functionality, uplink and downlink frequencies, which are the frequencies being used to communicate with the ground station, and proximity operations. So what kind of firmware or systems are in place in order to detect when something is close by. Thirdly are launch details. So this includes the date of the launch, the location where the satellite or the launch vehicle was launched, any affiliated organizations involved with the launch, protocols in place, the launch vehicle, and much more. Then we have the supply chain side of things, which encapsulates business relations, any delivery mechanisms that were used to supply satellite components, the software, the firmware, the hardware, and much more. Then we have the infrastructure, which consists of the ground station, any ground services, other affiliated spacecraft like the launch vehicle, and the facility where the satellite was launched. And lastly, there's telemetry, which we're going to be focusing on a lot. This contains orbital details, attitude, passing period, GPS locations, and much more. So let's talk a little bit about space-based open source intelligence. This focuses on what information we can obtain from a space system using publicly accessible data. Open source intelligence, which is a common cybersecurity term, stands for OSINT, and it's the practice of collecting relevant information using data sets and websites available to the public. So this can be found using a typical search engine, a query, or references from other websites. There's a lot of ways you can find these publicly accessible sources. When we're talking about OSINT in context of satellites, we can derive information about satellites from a wide range of sources in order to obtain data such as satellite imagery, information about launches, incident analyses, and telemetry information. So some of the general things you can obtain from a satellite by applying your OSINT skills are the name and identifier of the satellite, any operators and operating organizations, the mass and dimensions of the satellite, so how big it is and how much space it takes up in space, the mission, program, and intent, the coverage area, so how much coverage it has over Earth. This is really useful for communication satellites. Any instruments and components it uses, because there's different types of satellites with a wide range of applications. This is really important to figure out what sensors and components it has for it to function. And lastly, the manufacturer. Typically, satellites have multiple manufacturers at hand because they're made up of many different components, and each component can be supplied via different manufacturers. You can also obtain mission information about a satellite. So this often consists of the mission purpose and intent of the mission at hand. So whether it's for scientific research or communication services, that's often listed. Any onboard instruments it has to fulfill its mission. So if it were to be a research satellite, it'll probably have like a LiDAR sensor or a radar sensor. Also, typically, if it's for scientific purposes, it'll have an explanation of the research it's conducting. And then the target and area, so where it's going to be deployed and what area it's going to cover over. It also lists any partners affiliated with the mission. Also contain documentation about different components alongside how they're going to be employed within the space environment, and also public outreach. You can also extract a lot of orbital details using publicly accessible datasets. I think this is one of the easiest informational sets you can get access to. And examples of some of the orbital details you can get are the satellite's position in space. So these include the typical Keplerian elements, such as the semi-major axis, eccentricity, inclination, so forth. The type of orbit the satellite is in, so whether it's in low Earth orbit, medium Earth orbit, geosynchronous orbit, polar orbit, the ground track of the satellite, which is the path of the satellite above Earth, and the passing time and period. So you can figure out what time a satellite is going to pass overhead of you. You can also extract really specific spacecraft details using OSINT. Some examples include the software, where you can possibly get access to the source code, any associated binaries, version numbers, and operating systems that are used within the spacecraft. Firmware as well, which could include the device of the hardware, the configuration of the firmware within the hardware device, the vendor, and how old each component is. There's also different data buses that are at hand, and typically you can get the protocol of the data bus, any controllers that are used to make the data bus function, and details such as power levels, connectors, and so forth. You can also get information about various subsystems located within the satellite, such as thermal control, power, maneuvering, propulsion. And lastly, you can get information about the organizations that are affiliated with the satellite and the designers behind it, alongside the physical locations where the satellite was assembled. Another set of data you can extract using open source intelligence is communication information. This can include cryptographic algorithms that are used by the satellite to communicate between its various subsystems and also with the ground station. So this would include a type of cryptographic algorithm at hand, any private keys. It can also contain key frequencies, such as the uplink and downlink frequencies alongside the beacon frequency. It also can contain communication data about the ground station and what ground station it's utilizing for communication purposes, the mission operation center, and communication equipment such as antenna configuration and the shape of the antenna, the telemetry signal type, any details about the beacon polarization, and the transponder specifications as well. We can also get launch details about a satellite. So this includes location of the launch, which includes the country and the site. So typical examples would be like the Kennedy Space Center, the Vandenberg Space Force Base, and the Baikonur Cosmodrome, which is in Russia. There's also affiliated organizations involved in the launch, such as NASA and SpaceX. They also include information about the specific launch vehicle, which was used to launch the satellite into orbit, and whether or not it was expendable or reusable. Also contained the amount of time it took to launch and any flight termination procedures in case of emergencies and safety components affiliated with the flight termination sequence. You can also derive supply chain data. This can include the supply chain manufacturers for the software and the firmware running on the satellite. So some examples of companies are Analytical Graphics, which writes systems, toolkits, software for satellites, Kratos Defense, which is more focused on telemetry, tracking and control, and command and control solutions, Clyde Space, which mainly writes more for attitude control within satellites, and Space Nav, which provides space software for tracking of spacecraft. Hardware and components are also part of the supply chain, and they're typically developed by large defense companies such as Northrop Grumman, Lockheed Martin, and Boeing. There's also information about business relations you can derive using publicly accessible data sets, and you can use this to get information about contractors that might have been used along the way, and also affiliated third-party organizations. You can also use OSINT to get information about the architecture and infrastructure layout. So this includes the ground station and components that make up the ground station, such as antennas, the data processors, any radio modems, signal generators, and tracking system software. You can also get spacecraft architecture connections as well, such as any proximity operations and assets, commercial or militia, that it's utilizing, and also extract information about the launch facility and any control centers that are involved within the launch, alongside specifications for launch pads and assembly buildings involved with the launch. And lastly, you can derive telemetry data from satellites using publicly accessible data sets. This can encapsulate a lot of things, but put concisely, you can get the positioning and orbital data, which includes the attitude and altitude of the satellite, any orbital parameters, and the trajectory. You can also get the orientation of the satellite, which include yaw, pitch, and roll, which it's at angular rotation over each of the 3 axes, and any angular rates and speeds. You can also derive power and battery monitoring levels, temperature levels, communication statuses, the health of each of the various subsystems and components, and payload data from onboard sensors. You can also obtain product specifications, and I highly recommend referencing specification documents because there are really great resources for retrieving extremely specific information about a satellite. So typically when I'm conducting open source intelligence on a satellite, I typically try to find a product specifications document by doing a search engine query. And as you can see to the image to the left, you can get a wide range of extremely specific details, usually dimensional details, the type of sensors that are being used and how they function, the altitude, and a lot of other data for the positioning of the satellite as well. Another note about cherry picking your information from publicly accessible data sets is to pick out relevant information based on the threat vector and intention of the attack you're analyzing. There's a lot of accessible data sets about satellites out there, surprisingly, but usually you want to hone in the informational data sets you're using to the mission at hand, because there's so many data sources you could analyze. You want to really boil it down to some of the threat vectors you're studying. So I put some examples on the side. One is unauthorized access. So let's say you're having an unauthorized access attack from a ground-based hacker. Then if I were the investigator of the situation, I would look for spacecraft details and telemetry data in order to pinpoint any vulnerabilities the hacker might have exploited. If it's a communication protection scenario, what I would do is look through the orbital details of the satellite, because typically communication attacks must happen within a specific range of the attacker. So looking for the timing and where the satellite was positioned in orbit is really helpful, and any communication equipment that make up the satellite, such as the transponder and antenna configurations, alongside the encryption standards that are in place. And lastly, if it were a general forensic scenario, I would recommend looking over the general information about a satellite using commonly available sources, looking through the general architecture layout, and obtaining mission information. Welcome back. This is lesson 3 of module 1, which is the reconnaissance-focused portion of this course. In this lesson, we'll be talking about satellite subsystems and attack surfaces. So there's 4 main attack surfaces involved with satellites. The first is the space segment, which includes the spacecraft in space, and these types of segments are vulnerable to payload control, malware, and distributed denial of service attacks and denial of service attacks. Secondly, we have the user segment. This consists of equipment and devices utilized by users on the ground to interact with space systems. So this is often used by like mobile applications or general GPS application services. And these services are vulnerable to denial of service, malware infestations, and spoofing. Thirdly, we have the link segment, which is the communication channel that facilitates the data that connects the user and space segments. This is vulnerable to a wide range of communication-focused attacks, such as command intrusion and replay. And lastly, we have the ground segment. This consists of infrastructure and systems that's running on the Earth that supports operations of the space system. It's usually used to send over commands and controls to facilitate the space segment. And this is vulnerable to hacking and hijacking. So let's talk about the first and main attack surface, which is the space segment. Satellites in space face many of the same vulnerabilities, such as embedded devices like IoT devices, and they consist of multiple vulnerable subsystems, which include the attitude, determination, and control, which controls the orientation of the satellite in space, command and data handling, which facilitates the commands given to the satellite by a ground station, electrical power and distribution subsystem, which is the subsystem responsible for distributing electricity to different components throughout the satellite, the propulsion subsystem, which manages the propulsion thrusters within the satellite, which is widely used to reorient the satellite and change its position within its orbit. The structures and mechanism subsystem, which is the overall structure. This can consist of communication structures such as CAN bus and different protocols that tie everything together, and also the physical structure of the satellite. The telemetry tracking and command subsystem, which is responsible for handling position-based and telemetry-based information and general reconnaissance about where the satellite is located within space and the commands it processes in relation to that. And lastly, the thermal control subsystem, which, like it sounds, manages the thermal environment of the satellite in order to regulate its temperature in relation to the space environment. So let's talk a little bit more about what a subsystem is and the bus subsystem that connects everything together. So a subsystem within a satellite is a functional unit of a larger system. So satellites are incredibly complicated systems consisting of many different components and pieces that all tie together in order to make a functional vehicle that's in space. And this can consist of many different subsystems, such as the power systems, communication equipment, propulsion, etc. Everything a satellite needs for it to contain all of its different disparate functionalities. So how do these subsystems work together? So Subsystems are able to work together and collaborate by communicating with each other via a bus. And a bus is just something that connects all the subsystems together so they can communicate and send data to one another. They have a coordinated control and data sharing protocol through the bus in order to ensure data integrity and to meet mission intents. So every satellite, depending on its functionality, will have a slightly different bus system depending on what protocols it's using and the mission intent. And lastly, like I mentioned before, a bus is a communication pathway that connects all the subsystems together to make a broader and holistic satellite system. It is largely responsible for facilitating the data exchange and control within a functional and networked environment. So a little bit more into detail about the different subsystems I mentioned before. The attitude, determination, and control subsystem helps guide the orientation of the satellite using thrusters and different mechanisms such as torquers. The command and data handling subsystem manages the underlying data processes and the onboard computer system. The electrical power distribution subsystem stores, generates, and distributes electrical power throughout different subsystems in the satellite. Without this subsystem, all the different components of the satellite won't have the power to run. The propulsion subsystem is mainly responsible for managing the movement and coordination of the satellite within space. It includes components such as thrusters, engines, and propulsion devices to adjust the orbital positioning of the satellite. Then we have the structures and mechanisms subsystem. This consists of the physical structure and mechanical components that make up the satellite. Some examples of components within this system include the satellite frame, the antennas, and solar panels and arrays. Then we have telemetry, tracking, and command subsystem, which manages the communication between a satellite and a ground station. It sends telemetry data back and forth from Earth, which is able to track the satellite's location. And then lastly, we have the thermal control subsystem, which maintains a consistent temperature within the satellite in order to withstand the extreme environment of space. Because in space, things can get really cold and hot, so we need something to regulate that. I put a little diagram to the left here, and you can see all the different subsystems within this example diagram, and you can see all of them connect back to the subsystems I linked here, and they're all connected together via a data bus, which allows for data to be exchanged amongst these different systems. So let's go into depth on each subsystem and how it works. Firstly, we have the attitude and orbital control subsystem. Its main functionality is to manage the propulsion system and give it commands in order to orient the orbit and the attitude of the satellite. It's also able to adjust and orient the solar arrays and change its axis. It has a 3-axis control of satellite attitude. Attitude defines the orientation of the satellite, so it's yaw, which is a rotation about the z-axis, pitch, which is the orientation about the x, and roll this way. And it has also features a 1-axis control of the solar array. So it allows the solar panels to rotate to face the sun more or less. The components that make up the system consist of attitude measurement devices. The first set consists of the digital Earth sensors, which controls the pitch and the roll of the satellite. There's sun sensors, that is responsible for adjusting the yaw of the satellite, and 2-axis gyros. It also features a propulsion and solar array mechanism, which consists of everything that is needed to move and orient the orbit of the satellite, such as pressurized tanks, thrusters, and pressure transducers and valves. Also has wheels and magnetorquers alongside safety mode mechanisms, which allows for shutdown or safety fault detection via the software and electronics unit. On the left is an example of an attitude and orbital control subsystem on the European Space Agency's satellite, the MEDOP-A. Second subsystem is the command and data handling subsystem, and this is mainly responsible for managing data flow throughout the satellite, executing commands instructed by the ground stations, and processing and collecting data from all the subsystems, such as the sensors, and so forth. The necessary components for this subsystem consist primarily of the onboard computer, which is made up of many different components, but it has a power supply, a processor, and memory, static and dynamic. Also consists of software, and there's multiple different levels of software that's running. There's the operating system that's being run by the onboard computer, alongside flight software in order to instruct and guide how the commands should be processed by the satellite, and command and control processing. It also features input and output interfaces alongside storage for pertinent data commands. This features a variety of ports, including ports for serial communications and analog to digital converters, alongside digital to analog converters as well. To the left, I included an example of a typical command and data handling system for the ION-F nanosatellite. You can see it processes a wide range of things. It's continuously gathering data from all the subsystems in order to instruct its processes. Thirdly, we have the electrical power and distribution subsystem. This subsystem is relatively straightforward because it's not really processing any data. It's just finding a way to get energy from the sun and convert it to electrical energy, which can be utilized by the satellite. So the main functionalities of this subsystem consist of distributing electrical power to all the different components in the satellite, storing that power for later use, and powering each load. The necessary components that make up the system is the solar array, which consists of a bunch of solar panels arrayed together to get power from the sun, batteries and battery chargers, and once that electricity is harnessed from the solar energy of the sun, it goes through the power conditioning system, which consists of voltage regulators, DC to DC converters, and DC to DC inverters in order to generate low voltage direct current, high voltage direct current, and alternate current to be distributed throughout the satellite. Next up is the propulsion subsystem. As you might have guessed, this is responsible for coordinating the movement of the satellite, maintaining its position and directionality within its orbit, and combating these forces called perturbation forces. This is forces caused by gravity from other celestial bodies or other forces that might be within the space environment, and all satellites have to account for these forces. So it does this by 3 main components. The first one being motors. It has a variety of actuators and motors, such as the low thrust actuators, the high thrust motors, and a perigee kick motor, all to move the satellite throughout its orientation in its orbit. It also needs propellant. There's different types of propellant a satellite can use depending on what engineers want to serve for its functionality. This includes chemical propellants, electrical propellants, and cold gas thrusters. And finally, you need propellant tanks in order to store the propellant within a regulated environment. There's also a structures and mechanisms subsystem. It's a more holistic subsystem describing storage and housekeeping for all the operating subsystems. So you can think of this as the house of all the components that contains everything that makes and operates the satellite. And this can consist of many different types of structural components and materials, the main ones being the structural framework, the solar panels, communication equipment, hinges and deployment mechanisms, insulators such as thermal blankets to provide insulation, latching and locking mechanisms, and shock absorbers. Next up, we have the subsystem for telemetry tracking and command. This is responsible for collecting and transmitting real-time telemetry information collected from the satellite, and also sending commands to and from the satellite to the ground station on Earth, and also providing monitoring details for mission operators. This consists mainly of communication equipment, such as the transponder, the transmitter and modulator, receiver and demodulator, antenna, a telemetry encoder, and a command decoder. Lastly, we have the thermal control subsystem, and this is responsible for regulating the temperature of the components to prevent overheating or overcooling. This does this by dissipating excess heat that's produced by satellite components and also insulating very sensitive parts of the satellite from the harsh space environment. Components that make up this subsystem include thermal protection components, which consist of thermal blankets, multi-layer insulation, and thermal coating. Components that control and monitor the temperature environment within space, such as sun sensors and temperature sensors, and also components that dissipate excess heat that are produced by the components on the satellite, such as the radiator and heat pipes. So just to give a broad general overview of the satellite bus, since it's incredibly important for understanding internal satellite communication, is that it's a modular and standardized framework for satellite structure, not only for handling and combining all the physical components of the satellite in a cohesive manner, but also handling the digital data that is extracted from them as well. The bus interface of a satellite connects all the different subsystems together and serves the main functionalities of exchanging data between each of the subsystems, also distributing commands and instructions to each of the subsystems and telling each of the subsystems what to do, coordinating activities in relation to the mission and what should be coordinated by the mission operator, checking for errors along the way in order to prevent widespread failures in the satellite, and also transmitting telemetry data that is collected. So different buses can have different architecture depending on the satellite and what it's used for. And it can vary widely in terms of design, size, and functionality. In general, architecture design of a bus architecture within a satellite is meant to integrate all the subsystems together to coordinate a specific mission operation, depending on the use case of the mission. And it does this by providing mechanical support and protection for the satellite components on the physical layer, and also removing any redundancy, interference, and ensuring the integrity on the data layer. It also coordinates a lot of the data flow between each of the subsystems. It does this by retrieving data from sensors, different instruments in the satellite, payloads, and the onboard computer, processing that digital data via a means of encryption, compression, and error checking, and also storing relevant data within storage devices on the satellite, such as solid-state recorders or memory modules. So there's a wide range of space communication interfaces, which are standardized connections and protocols that enable data exchange between different subsystems in a satellite or any spacecraft. Some generic interfaces, and generic interfaces are just a foundational mode of communication utilized by space systems for allowing connectivity and general data flow. It offers low to moderate data rates, and it's often used for command and control and telemetry handling. This includes the CAN bus, the ARINC 429, and the other ones I listed there. The second broad category of communication interfaces are high-speed and backbone interfaces. These provide more high bandwidth data connections and are really useful for subsystem communication within spacecraft. It's often used as the underlying backbone structure for connections in order to ensure low latency and fast data rates. Lastly, there is application-specific interfaces, which consists of SpaceWire, DVI, and other ARINC protocols, which are often used for aviation, more or less for space systems, but it's also relevant for aerospace security. And application-specific interfaces provide very specialized functions for subsystems that are tailored more towards mission objectives. So this is the one out of the three that varies most depending on the functionality of the satellite. And they include features such as a high degree of customization, and usually the data that is transferred between the subsystems is very high in quality and is specialized for data handling. So just a general overview of subsystems in general. Yes, satellites are extremely complicated, but in order to understand them at a more fundamental level, especially if you're inspecting a satellite subsystem or something that either went wrong, so you're trying to troubleshoot a satellite due to an attack or during a digital forensics scenario, it's a lot easier to analyze scenarios like that if you break down the problem and try to hone into which subsystem went wrong. So just some general subsystem identification tips is to firstly get access to remote sensing and telemetry data. If the sensing data and telemetry data indicates information about a specific subsystem, so for example, if it includes power levels, then it's more likely to be part of the power supply subsystem. Or if it includes orbital element information, then it might be within the attitude and orbit control or the telemetry tracking and command subsystem. So it really helps you hone in which subsystem went wrong. Secondly, is to review the satellite documentation and specification details. A lot of documentation and specification details provided by manufacturers include really specific information about their various components located within subsystems, which can really help you identify which component within the general subsystem had an error or went wrong or was malfunctioned. Lastly, just apply general OSINT techniques. So this could be auditing manufacturers and operators that created the components that make up the satellite in order to look into key subsystems to identify what happened during an attack scenario. So I just wanted to go over some exploitation scenarios that could happen for each subsystem. So for attitude control, a lot of exploitations happen for getting access to control the satellite's orbit and orientation. And if this subsystem were to be compromised, a hacker can alter the satellite trajectory and attitude within its orbit. If the command and data subsystem were to be exploited, this could allow for malicious command injection within ground station communications, which allows for data tampering and executing malicious payloads up to the satellite. If the power distribution subsystem were to be hacked into, this could alter the satellite's power generation capabilities, cause massive power outages within its components, and possibly render the system useless and malfunctioned. If the propulsion subsystem were to be compromised, this can lead to alterations in the orbit because the propellant cannot be utilized anymore or the thrusters don't work, which could cause collisions with other debris or satellites. If the telemetry, tracking, and command subsystem were to be hacked into, this allows for eavesdropping and interception of communication information and telemetry data that's being sent, and can also allow for unauthorized interference via jamming and spoofing. Lastly, if the thermal control subsystem was exploited, this could compromise the thermal management capabilities of the satellite, leading to overheating or freezing of components. Let's talk about the second attack surface, which is the link segment. And this consists of communication links between different space systems. And the main link types that handles communications is the user link, which is the communication link that connects satellites to customers and general purpose applications. The uplink, also known as the feeder link, which is the link that goes from the ground station to the satellite. There's also the downlink, which is the communication link from the satellite back to the ground station, and the crosslink, which is the link that connects different satellites within a constellation or formation, allowing for different satellites in space to talk to each other. These links follow different communication protocols depending on the service and functionality. Common protocols include the Space Data Link Protocol, which is widely used for satellite communications, the Transfer Frame Protocol, which is used more for point-to-point communication between ground stations and satellites, and the Advanced Orbiting Systems Protocol, which is a high-rate data transmission between spacecraft and ground stations. These systems also have a data processing and routing component to them. The data processing portion allows for the formatting, compressing, and error checking of incoming satellite data to the ground station. The routing system is responsible for routing packet transmissions, because usually when a satellite communicates to a ground station, it sends data via packets. So it manages those packets. It also handles traffic distribution and checking for failures. And lastly, it's also capable of network management, so it can monitor performance and security audits. So the main vulnerabilities within the link segment are threefold. The first is attitude control, which can allow for unauthorized control of a satellite's orbit and orientation, which allows hackers to compromise the satellite's trajectory and orientation in space. The command and data system is also very vulnerable, which can allow for a command injection via ground station communications, data tampering, and by executing malicious payloads. And lastly, the power distribution system can also be compromised, which allows for malicious command injection and data tampering. The third attack surface is the user segment, and this consists of general purpose items used by end users and people to connect and utilize satellite services. So the typical use cases are internet access, performing voice calls, and television broadcasting. And this can be done using a wide range of equipment, such as satellite TV receivers. There's also satellite phones, also known as sat phones. Very small aperture terminals can also be used to connect up to satellite services, and GPS receivers. And the user segment is typically pretty regulated and has a lot of compliance risks associated with it. The main ones being regulated by the FCC and the ICU, which is the International Authority, which regulates the radio frequency spectrum for all modalities of satellite communication. Also, all end users must comply with international standards established by the CCSDS, which is like a main authority within satellite and general space communications. And also data protection regulations, such as the General Data Protection Regulations, establish strict privacy rules about what can be done in relation to satellite communication. So key vulnerabilities within the user segment are also threefold. The first one is technical vulnerabilities. This consists of inadequate encryption mechanisms, intrinsic firmware vulnerabilities, and insufficient authentication. The network aspect is also very vulnerable, which could allow for data flow interception and insider threats using general purpose user equipment to gain unauthorized access. Although there are regulations around it, unauthorized personnel can evade or break compliance regulations or find a loophole within those regulations established by credible organizations in order to hack into these systems via the user segment. Lastly, the final attack surface we have is the ground segment, and this encapsulates all the terrestrial-based infrastructure for communication with satellites. And the infrastructure and operations behind the segment are that ground stations are typically equipped with huge dish antennas and communication equipment established by communication links. They also feature command and control centers, which plan, monitor, and execute all satellite operations. And they also contain data processing and storage centers, which decode, distribute, and archive data to end users who communicate to the infrastructure. The ground segment has a wide range of security protocols, and they also implement authentication systems to prevent unauthorized access by hackers. They also typically integrate intrusion detection alongside encryption protocols to secure data transmissions. And there's also compliance and regulations associated with the ground segment as well, where ground segment infrastructure have to comply with national and international regulations regarding spectrum licensing, privacy compliance, and a whole wide range of regulations. Key vulnerabilities within the ground segment include unauthorized access, where unauthorized access could be allotted to malicious users who are able to gain escalated privilege to the ground segment via a ground station or social engineering techniques and get access to private data and abuse the system. Ground segments are also vulnerable to network attacks via malware, denial of service, unauthorized access, or general data breaches. And lastly, the communication portion of ground segments are highly vulnerable for interference by various electromagnetic sources like radio and so forth, jamming, interception, and eavesdropping, alongside spoofing via ground-based sources. So to encapsulate everything, a higher level overview. So all these 4 segments I mentioned all work together to provide guidance and communication with satellites. This is usually referred to as the topology of the space system. And the space segment is primarily responsible for data collection and data transmission, and it contains all the spacecraft and satellites launched into orbit. The link segment, put simply, is defined by the communication links between the space segment and the user segment. This includes all the communication channels, protocols, and data transmission technologies that are responsible for handling communications. The ground segment is made up of facilities that operate satellites, which are located on Earth. They control, monitor, and communicate with satellites and spacecraft in the air and space. And lastly, the user segment represents end users of a space system, which utilize the services of the space segment, which is typically used for general use case purposes within various applications like phones, GPS receivers, and so forth. Hello, welcome to Lesson 4 of Module 1 of the Aerospace Cybersecurity Satellite Hacking course. In this episode, we'll be talking about orbital elements and 2-line element sets. So an orbit is something that is a closed path a celestial object follows, and many things can follow an orbit, but usually it's some kind of satellite. So, for example, we can have naturally occurring satellites like the moon, which orbits around the Earth in a closed celestial path. We also have satellites that do the same. So let's talk about coordinate frames, and this is how we grid things in space in order to find a specific object of satellites and other celestial bodies. And we can obtain the instantaneous trajectory using Cartesian coordinates. So for the position plane, which is where the satellite is located in each axis, we have the x-axis, the y-axis, and the z-axis. And we can also get the instantaneous trajectory, or the velocity, which measures how fast the satellite is moving in each axis. And this is also defined as the velocity in the x direction, the velocity in the y direction, and velocity in the z direction, as shown to the image on the left. So in terms of coordinate systems, there are two main types of coordinate systems for an orbit that pop up a lot, especially for satellite hacking CTFs. This is the Earth-centered inertial, which is where the origin is centered on the Earth, and it does not rotate with the Earth, so it remains stagnant. It doesn't move at all. And you can see the ECI frame is the second image here. The second type of coordinate system that is widely used is the Earth-centered, Earth-fixed. This rotates with the direction of the Earth, so as the Earth rotates, this plane will rotate alongside it, along the rotation axis. It is centered at the equator rather than being centered at the center of the Earth, and its XY plane matches alongside the equilateral plane. So let's talk a little bit about timing in space. So we follow a conventional timing format here on Earth, which is the Universal Coordinated Time, UTC. And this is a very standardized timing system for timekeeping here on Earth in order to make sure that everything is deployed at the right time. But it is not an exact measurement of time because it's based on the rotation of the Earth. So time in space is highly dependent on where you're situated within space-time. So there has to be different timing standards for space-related applications. Two really popular space-related timing standards are the Julian date, and the Julian date is widely used because it's a timing scale that is independent of the rotation of the Earth, and this is widely used for orbital motion descriptions and making calculations of astronomical research in orbits. There's also terrestrial time, which is a timing system typically used to predict the position of orbital objects as an observer from Earth. So it's an Earth observer-based timing scale, and it's widely used for space observation and navigation. So let's talk about epochs. Epochs will pop up a lot, especially within CTFs. And an epoch, put simply, is a fixed point in time used as a reference for measuring time intervals. So in order to calculate an epoch, you need to select a reference moment, measure the amount of time has passed from that reference, express it within a standard format, like the timing standards I mentioned before, or within dates, and then apply the epoch at the end. So I did a quick example with the Julian date 2000, the J2000 timing standard epoch. So first I picked a reference moment, so I just picked an arbitrary date. So it was January 1st, 2000 at 12 terrestrial time. And then I measured the amount of days that passed since that reference moment, which was 8,766.5 days. And I made sure to choose a standard format to express the date as. I just chose days. And then I applied the epoch by running through a series of calculations, which gave me 2451553.5 J2000. So this can be applied for a wide range of timing standards. I just wanted to show you an example of one that's pretty common. Right. So let's talk about orbital elements. This is imperative for understanding positions of satellites and where they are located within an orbit. So orbital elements are parameters and identifiers used to describe an object in orbit. And they have two broad categories. They're the Keplerian elements, which is an idealized orbital model. And it contains parameters to show a satellite's position in orbit within an idealized version of the elliptical orbit, discounting other factors within space. And some values include the semi-major axis, eccentricity, and inclination. Don't worry, we'll be talking about these more in depth in the next few slides. And then there's also the perturbation elements, which account for the perturbations and external forces from other celestial bodies in space. And this orbital model accounts for effects such as gravitational effects from other celestial bodies that might be modifying the orbit and other slight deviations to the standard Keplerian idealized model. And you'll see some of these values include the true anomaly and mean motion. So let's go over some key orbital terms, which is useful for understanding orbits and the Keplerian elements. So we have the minor axis, which you can see on the illustration to the left, is the shortest line of distance within an orbit. So it would be right here. There is the major axis, which is the longest line of distance within an orbit between 2 points. So this is like the longest distance, so it would be the major axis. The periapsis is a point in the orbit that is closest to the central body. So here, if we have a central body, which is the sun, periapsis would be here. And then the apoapsis is a point in an orbit that is furthest away from the central body. So the central body is the sun, apoapsis would be right here, because it's the point in the orbit that's furthest away from the sun. So let's talk more in depth about Keplerian elements. So these are specific parameters of an object's orbit around a celestial body, and they can describe a wide range of things. First, its orbit size and shape. So this consists of the semi-major axis and eccentricity. We can also describe the orientation of the orbit using inclination, right ascensation of ascending node, and the argument of perigee, and also the location of the satellite with the true anomaly. Before I dive more into the specifics of the Keplerian elements, I just also wanted to mention the spherical grid system. We use the spherical grid system on Earth in order to describe points on Earth via a coordinate system. You might have seen this on GPS, or if you ever have like a globe model in your room, you probably see little check marks along each side of the globe indicating the latitude and the longitude. So key terms for understanding this grid system is longitude, which is how north or south the location is from the equator. So you can see here as we go up, these values of longitude increase, and they also increase in the opposite direction as well. We also have latitude, which indicates how far east or west location is from the prime meridian. So the prime meridian is like this vertical line that splits the globe into two portions, and indicators of latitude would be just how far west it would be. So it increases as we go westward, or how far east. So it increases also as we go eastward. Also, other generic terms include geocoordinates. So this is a specific position on the grid system, and it's indicated by the latitude and the longitude. So here it would be 20, 10, because our latitude is 20 and our longitude is 10. There's also things called parallels, which are lines of latitude parallel to the equator. This. And we also have meridians, which are lines of longitude that run north to south from the north to south poles. So these would be the meridians. I also mentioned the equator, which is a horizontal line right here that splits the north and south hemispheres. And we also have the prime meridian, which is located in Greenwich, which is a vertical line that serves as a reference for all other longitudinal lines. So let's dive into each of the Keplerian elements. First, we have the simplest, which is the semi-major axis. And this defines the size of the orbital ellipse. And In order to calculate it, it is half the largest diameter, the major axis of the orbit. So in this example, the major axis would connect the periapsis and the apoapsis, so this entire line here. The semi-major axis is just one half of that, so it would just go from the center of the ellipse to one point of the major axis. We have eccentricity, which defines the roundness of the orbit. And it's calculated by getting the square root of 1 minus b squared over a squared. B is the semi-minor axis, and a is the semi-major axis. The semi-minor axis is 1/2 the minor axis, and semi-major axis is 1/2 the major axis, the longest point of distance in an orbit. And in order to get a perfect circle eccentricity, where the orbit looks like a perfect circle, like shown here, you have an eccentricity of 0. If you want an eccentricity of an ellipse shape, which is still considered an orbit, you'll have the eccentricity be bounded by 0 and 1. And the greater the E value, the more eccentric it's going to be. So as the E value increases, the more and more stretched out the orbit will seem. And we can also define different trajectory methods using eccentricity. So in order to get a closed path and fully circular orbit, that would be an eccentricity of 0. In order to get still an orbit, which is a closed path, but a more rounded out shape, you'll have an ellipse orbit, which is between 0 and 1. A parabola, which is not considered an orbit anymore, but is considered a trajectory, is when E is equal to 1. This is an open trajectory, as shown by the red line on the image below. And then the hyperbola, it's when the eccentricity is greater than 1. This is an open trajectory, and it's a more exaggerated version of the parabola. Let's talk about inclination. Inclination is defined as the tilt of an orbit. And this is calculated by getting the angle between the Earth's equilateral plane and the plane of the orbit. So let's say our equilateral plane is right here. If a satellite were to be right here, we'll have like a 30-degree inclination as we calculate the angle of the equilateral plane and the between, and get the angle between the angle of the plane of the orbit. There's different types of inclinations and categories of it. In order to for an orbit to be classified as prograde, the inclination angle must be between 0 and 90. And this is where the orbit velocity is in the same direction as the Earth's rotation. You can also have retrograde inclination, where the inclination angle is between 90 and 180. This is where the orbit velocity is in the opposite direction of the Earth's rotation. And we also have a special case of inclination categories called the polar orbit, where the inclination is exactly equal to 90. And this is a special case where the satellite covers all points of latitude. So you can see here, we have a prograde orbit, which is in blue, a polar orbit, which is in red, and a retrograde orbit, which is in yellow. All right. This is like the most complicated, at least it sounds the most complicated out of all the Keplerian elements, but it's not too bad, which is the right sensation of the ascending node. And this is the angle between the vernal equinox direction and the ascending node. So let's cover all the terms before I dive into the technicalities. The ascending node is a point in orbit where the satellite ascends northward in an orbital plane. Let me explain. So let's say we have an orbit here of a satellite. The ascending node is where you have an orbital plane right here. It's where it intersects the orbital plane going upward or northward. So as you can see, let me trace the path of the orbit with my mouse. It's going upward, all right, here. So we consider it an ascending node. The descending node is the opposite. It's a point in the orbit where the satellite descends southward. So the descending node in this case would be here. We have the satellite change directions from going northward to southward. Now the satellite's going down in orbit. It would be right here. Because it's going southward, it's going down, and it intersected the orbital plane. Lastly, we have the vernal equinox, which is the ascending node of the sun's orbit. So the Earth orbits the sun because the sun is bigger and it's the core component of our solar system. So during points of orbit, we have equinoxes, and the equinox is the ascending node of the sun's orbit. So as you can see, I can follow the orbit. Right here, the orbit of the Earth is going northward, it's going up, and it intersects the orbital plane of the sun. So that would be classified as the vernal equinox. And all the right sensation of the ascending node is the angle between the vernal equinox direction, which is shown right here on the image, and the ascending node. So just getting the amount of angle between the 2 points. We also have the argument of perigee, which is the angle between the ascending node and the periapsis of the orbit. So the perigee, or the periapsis, is a point in the orbit which is closest to Earth, or the central body. So you're just getting the angle between the ascending node, which is where the orbital plane intersects the northward climb of the satellite. So the ascending node in this picture is right here, and the perigee, the closest point of the orbit. And you're just rotating around and calculating the amount of degrees you have to rotate to get to that point. In this case, it's 270. Then we have the true anomaly. This is the angle between the periapsis, the closest point of an orbit, and the satellite's position, measured from the center of the central body. So here we have the distance between Earth, the central body, and the perigee, which is the closest point of the satellite's orbit. And then we're just getting the angle between that line and the line of distance from the central body, Earth, to the satellite. So here's a quick video visualization of each of the Keplerian elements. I know it's a little bit much in the beginning, but as you start doing more CTFs, labs, and exploring space systems in general, these will become more intuitive. And you can always do like a quick Google search and reference diagrams. You don't have to have this memorized or at the back of your hand. Just make sure you use them as needed based on the application at hand. So that's the semi-major axis. The eccentricity, the roundness of the orbit. Then we have inclination, the tilt of the orbit. Then we have the right sensation of the ascending node. The angle of periapsis. The true anomaly, the angle between the position of the satellite and the line between the perigee. Okay, let's talk about ground tracks for a moment. Ground tracks are a 2D representation of a satellite's path over the Earth's surface. Usually when we visualize a satellite, it's within a 3D diagram, but a ground track lets us transpose the 3D orbit of a satellite over a two-dimensional map to see where, like which landmarks it's passing over and what locations the satellite is passing in a more intuitive way. And typically, it looks kind of like a wave function here, and it's indicated by latitude and longitude. There's also different types of orbits, which vary depending on the different orbital elements and configurations. The ones we're going to be talking about include geostationary orbits, geosynchronous orbits, low Earth orbits, medium Earth orbits, semi-synchronous orbits, and sun-synchronous orbits. There's a really great graphic here on the side I would recommend you look over. You can pause the video and look over this because it's a really great graphic. And we can move on to each of the different categories. So first we have geosynchronous orbits. And this is a type of orbit that matches the pace of the Earth's rotation to remain at the same point above Earth. So put simply, it matches the Earth's rotation speed in order to remain stationary above, or seem stationary at a specific point above Earth's surface. So this is where you want a satellite to remain at the same point over time, usually used for imaging and remote sensing. Geostationary orbits are a subset of geosynchronous orbits, but they are circular and orbit above the Earth's equator. So you can see we have a fully circular orbit here that's orbiting around the Earth's equator. Then we have low Earth orbit, and a satellite can be categorized within the low Earth orbit category if it's an Earth-centered orbit with an altitude of 2,000 kilometers, which is 1,200 miles or less. And since it's closer to the Earth and there's less distance between it and the Earth, it will typically travel faster than satellites at a higher altitude. We also have medium Earth orbits, which is the next step up from low Earth orbit. And it's an Earth-centered orbit with an altitude ranging from 2,000 kilometers to 35,786 kilometers above the surface of the Earth. Then we have semi-synchronous orbits. This is just a circular orbit that has a period of 1/2 of a day. So it will have a period of 12 hours. So in order to make one revolution, it'll just take 12 hours to do so. And that's considered semi-synchronous. Lastly, we have sun-synchronous orbits. This is a special case of anything that orbits the sun. And this is a polar orbit, so it has an inclination of 90 degrees with the sun. And you can see that in the image below. So in order to control where a satellite is positioned within orbit and its orientation in orbit, satellites host a subsystem called the Attitude and Orbital Control System. And this subsystem is responsible for handling the processes of controlling the orientation and orbit attitude of the satellite using a variety of sensors, actuators, and software. So it's capable of rotating the satellite along the roll rotation, the pitch rotation, and the yaw rotation. So let's talk about a specific set of satellites, which are GPS satellites. GPS stands for Global Positioning System. And these are a set of satellites used to determine the location of something on Earth. You probably use it all the time with the various applications on your phone. These satellites are located within medium Earth orbit and are approximately at an altitude of 20,200 kilometers. They orbit around Earth twice a day, and they are arranged into 6 congruent planes around Earth. So users on Earth can see at least 4 satellites at a given moment, which is imperative for getting your location via trilateration. So let me talk a little bit more about trilateration. So this is a system that GPS satellites use to pinpoint where you are located on Earth. So to abstractly walk you through this, satellites essentially, all they do is transmit a signal that your GPS receiver detects. They don't need to really have any data associated with it, because as long as your GPS receiver is able to get the signal from a satellite, it can calculate both the time and the distance measurement. And getting the signal from 3 satellites allows you to pinpoint a precise location at the intersection. So you can see here we have 3 signals from each satellite, and the intersection is right there in the center. And this allows for pinpointing. Since the world is 3D, and this is just like a 2-dimensional example, we need more than 3 satellites to pinpoint a location. So it's usually 4 or more. Now let's talk about identifiers of specific satellites. All satellites have a designated NORAD ID. This was established by the North American Aerospace Defense Organization, and it's a satellite catalog number associated with each satellite, and it's used to identify the spacecraft in orbit. You can also have descriptors of satellites in orbit by what's called a 2-line element set. Pretty much all satellites in orbit are required to transmit this information, and this is a very standardized data format, including details of orbital elements for a satellite. And we can break it down here. The top, it's broken down into 3 lines. The first line is the name of the satellite. The second line has the satellite number and the designator. We have the international designator and the number, the epoch year, and the Julian date. So date information here. The first derivative of mean motion, second derivative of mean motion, and the drag term, the ephemeris type, the checksum, and then on the final line, we have the satellite number reoccurring, the inclination, and other Keplerian elements such as the sensation of the ascending node, eccentricity, argument of perigee, mean anomaly, mean motion, and the revolution number. So I would say that you don't have to memorize all these values, but the key values of a TLE on line one are the catalog number, which is a unique identifier for the object, and the classification type, so it'd be right here, which indicates the type of object, such as a satellite. I would say the international designator is also really important, which contains the launch year and number and the piece of the launch. On line 2, I would say most of the Keplerian elements are really handy, so they make it really easy for you by putting them all within a single line. So this includes the inclination, rate of sensation of ascending node, eccentricity, argument of perigee, mean anomaly, and mean motion. If you want to look into more of the specific values of a TLE and what they mean, it's going to take me forever if I try to define everything for you. Celestrak has a really great documentation website for important values of a TLE. So I highly suggest you check out this resource if you're interested in learning more about these values. Hello everybody, welcome to lesson 5 of the first module of the Aerospace Cybersecurity Satellite Hacking course. In this lesson, we'll be having a more hands-on and interactive demonstration of open source intelligence tools for extracting data about satellites. Right. Firstly, a word about getting satellite information. We're going to be employing OSINT, which stands for Open Source Intelligence, which is a technique for extracting information from publicly accessible data sources in order to obtain data for a specific purpose. So in this case about satellites, we're going to be getting information about supply chain providers, launch locations, and affiliated organizations, satellite components, product specifications, satellite imagery, remote sensing data, and much more. So tools that can be used for satellite data sourcing include general tools. So these are tools in order to obtain comprehensive information about a satellite. This can include data such as satellite missions, location points, capabilities of the satellite, and so forth. There's also communication-focused tools, which are used for monitoring and analyzing communications, such as frequencies and regulations around specific communication between the ground station and the satellite. There's also visualization tools, which are used for visualizing telemetry and orbital elements of a satellite, such as its ground track, Keplerian orbital visuals, etc. There's also imaging focused tools, which are able to access data from satellite sources. Examples include terrain mapping, general mapping of remote sensors, and location photos. There's also remote sensing focused tools that provide access to data sets collected by sensors on satellites. Some examples include scientific data collection, which can be a wide range of specifications, and environmental monitoring. And lastly, there's tracking tools that enable the monitoring of satellite movements, its positions within its orbit, and orientation. So the first resource I have on this list is N2IO. N2IO is great for getting just general information about a satellite. So we can escape here and visit the website. I'll actually show you guys through the site. So N2IO, let's say we want to track the International Space Station. So go to International Space Station. And you can see there's a wide range of satellites. And there's like the NORAD ID. So each satellite has an identification code, the international code, the launch date, and the period. You can get information about a specific satellite by clicking on it. So let's say we want information about the space station. Here it shows the ground track above the ground, its latitude, longitude, altitude. It also includes pass information, so it contains the start azimuth and the specific timing, the coordinates of it, and how long it's going to take to pass over your current location. It also has apogee and perigee orbital information alongside other Keplerian elements such as the inclination, the period, semi-major axis distance, launch date, launch site, and the International Space Station, which is the source of the information. Also contains communication frequencies as well. As you can see, there's a wide range of frequencies you can use to connect to the International Space Station. So it has the uplink, the downlink, beacon link, the mode, and the call sign, and the status of the communication band. The second tool, oh yeah, and one thing I forgot to mention about N2IO is that it also contains TLE information if you scroll down far enough. So right here, we have the 2-line element set, which I mentioned before in the previous episode, includes a bunch of orbital information about the satellite and also contains the source of it as well. Next resource is Celestrak, which hosts a wide satellite catalog, which is extremely useful. So let's visit that site. And here, into the satellite catalog, you can input the name of the satellite or the NORAD ID or the international designator. I'm going to use the name. And let's just run this on the International Space Station again. Click submit. And you can scroll down and we're met with a wide range of data points. Let me zoom out. And here we have the international designator, the catalog number, the name, source, so what country or what organization launched it. You can also figure out more about these by clicking on the little icons here. You can find out the launch site. So you just like get the name of this, copy it, and then find it here. So this was launched at the Air Force Eastern Test Range in Florida. Also the operation status, if it's a plus, it should be operational, minus non-operational, decayed, unknown. There's a lot of statuses you can look through. And I think Celestrack also hosts TLE information as well. So you can just click the little document icon right there and you'll be met with a TLE. Okay. Moving on. Celestrack also has box score information. So if you go to this link, here's the box score information, and this is just general information about specific regions and organizations and how many satellites and payloads they have in orbit, which are decayed, total active satellites, debris. So you can just see like, look through like the failure rate of each organization, see how they're doing in terms of satellite deployments and their missions. And you can look through their success rate, see in order to make relevant predictions about each organization. I just thought this was really interesting. Next up for Celestrack is their launch sites tool. I think this is personally one of my favorites because it lets you pinpoint. So let's say before, like we found a satellite that was launched out of the Air Force Eastern Test Range. So I would just click this one. And I would be met with, I'm not sure if you guys can see this, with a map just by clicking here of the test range site. So it will be possible for you to track down where specifically the satellite was launched out of using this tool. And you can click on each point and like zoom in and figure out where the launch site was. So it's really good for extracting positioning information. If you're more interested in getting satellite communication data, I would recommend KVH. KVH is a company that hosts a wide range of satellite tracking frequencies. So if you look through their site here, you can see they have a list of satellites and communication information. So let's say we pick this one, the AsiaSat 3S. We can find the frequency of the satellite, the symbol rate, the code rate, network ID, and specific antenna information. So we'll be able to extract whether or not it's a vertical or horizontal antenna, the band of the antenna, the DVB, the decoder types, and the orbital positions. We'll be talking more in depth about satellite communication in the next module, so you'll be getting a thorough understanding of what each of these mean. But for now, I just wanted to introduce the resource because it's really helpful for extracting communication information. The next resource I have on this list is the NASA Space Science Data Archive, and this hosts a bunch of launch information and detailed descriptions of what each satellite is and its mission intents. So let's say ISS, any discipline, submit, and we can find the International Space Station. Here, we're met with a lot of information, like just background documentation about the satellite, where it's been, personnel behind it you can contact. So this is really helpful. What disciplines it fits under, funding agencies, really important, like which agencies funded it, the launch date, the launch vehicle, the launch site, the launch mass, alternate naming conventions for it, and a really, really long detailed description of background information, which is incredibly helpful for getting a wide overview of satellite functionalities. The next one is for obtaining telemetry and payload data. It's called Orbiting Now. They have a really nice interactive website. So let's say we want to look through a low Earth orbit satellite. This will load all the information. And here we go. For the sake of this tutorial, I'll just pick the first one. And it'll load a bunch of telemetry indicators about the satellite. So we get the latitude, the longitude, the altitude, how fast it's traveling, its ground track. It also provides sources as well. The altitude graphs, velocity graphs, TLEs, and a TLE history, which is really helpful because it provides like an index of previous TLEs that have occurred and been recorded in the past. You can also get payload data about the satellite. So how many objects it's found over time and information about each payload. So yeah, overall, this is really helpful if you want to look for specific details and graphs and visuals about orbital information and payloads that have been deployed on the satellite. Next up, diving more into remote sensing visuals is the NASA Earth Data Archive. So here they have data access tools, and you can scroll down, and I typically use the world view one to get information, although they host like a wide range of resources and tools. And yeah, you can pretty much figure out what you want depending on the scenario and which satellite you're investigating. Let's say you're investigating like a meteorological satellite and want to look at clouds. Then I would click that, and it gives you like a cloud forecasting alongside like timing here. You can change. You can also change the base layers, show more details, events, and also here you go. You can like see different meteorological events that have occurred and also download data as well. Click this, and then you can download the data. So yeah, very helpful for getting remote sensing data. It has a ton of information, and it's very helpful if you want to like specify the time and get up-to-date meteorological data. The next tool is the NASA Earth Observation. And this is for hosts like a wide range of remote sensing data sets. It isn't as visual as the previous one I showed you, but it's still extremely comprehensive. So let's say we want to get, there's like a lot of options here. Solar insolation, remote sensing data. Then I would click here. and it shows the solar installation of the month. You can download it as a JPEG and specify the grayscale and the color scale. Also down here, you could change the year and the month you're trying to analyze. So like this is January, but let's say I wanted to get the year before. Then I would click another month and you can see it change over time. So yeah, it's very cool. And it also includes information about the data set as well. Next up is EO Portal. This is for obtaining information about satellite missions. So let's say I wanted to get mission information about the Aditya L1. So it will specify a quick overview of what the satellite is and its mission status, the launch date and the end of life date, and the agency that's coordinating the launch. You can also get overview about specific components of it, like sensors, references, and launch information. So it gives you a really long and detailed background information as well. Spacecraft specifications, subsystems, really, really useful. Also gives you diagrams, the bus management unit. So this is an incredible resource for extracting subsystem information alongside just an overview of the mission and what agencies are behind it. Right. Google Earth can also be used for getting imagery from satellites. Since Google Earth uses satellite imagery to get these high-resolution photos, it's great for getting just general photos and specifying like longitude, latitude, and getting a better spatial awareness of where the satellite is located within space. So on the side here, there's different options. You can like, scroll around, rotate. You can also search for geocoordinates and different landmarks. So let's select this down. You can also adjust the overview of the map. You can turn on clouds. I typically tend to turn on grid lines because it helps me a lot with my research. There's also a ruler tool on the side you can use to measure distances. So yeah, this is very helpful, especially if you're trying to track down where the satellite's going to be and just want to get like general imaging data. The next one is the Sentinel Hub, which hosts public satellite imagery data from a wide range of satellites. So this is just like a host of a bunch of data sets and collections. So let's say I just wanted to get land cover mapping information. So I just click that. You can click details to get more information about it. Here we go. You get specific descriptions of what research data is being conducted, the resolution, and band information, scripts, providers, and so forth. I typically use this whenever I'm investigating a scientific satellite, because usually scientific research satellites and remote sensing satellites are listed within this collection. Next up, if you want to get more detailed imagery, I would recommend the USGS Earth Explorer. And here it gives you like a wide map. You can specify the state, the encoding method, feature name, and it gives you a bunch of coordinates and mapping information about satellites. You can get cloud cover ranges. So there's a bunch of data sets it gives you access to. So I recommend looking for this data set feature. You can look through aerial imagery and apply the data. There you go. And you can see like where it's scanned over and obtain details about it as well. And it gives you like a huge metadata list. Very, very helpful. Next up, we have Zoom.Earth. This tool provides weather maps and images. So you can see on the left-hand side, there's going to be a mini bar, and we can pick from live and HD satellites alongside radar, precipitation, wind, temperature, humidity, and pressure. So let's say I wanted to look at humidity. You can look through different regions of the Earth. And you can also change the timing as well. So this is really useful for getting meteorological-based data. There's also the NOAA web portal, which is the GOES satellite-specific imagery and remote sensing values. So here, this is like a bunch of regions that were inspected by the geostationary satellites deployed by NOAA, which is a nationally recognized meteorological institute. And you can see we can get infrared images, visible images, and water vapor images. So let's say I wanted to get the infrared imaging of Alaska. I would click that and give me an image of it alongside relevant timestamps at the bottom, what band was used, and what state it's being looked over, which is Alaska. Cool, and it also has other options as well. You can get visible information, water vapor information. So yeah. The next one is Orbit Mapper. This is widely used for satellite tracking. So this shows a list of objects that have been sent into space, launches that have happened recently. So let's click on launches. And it just provides just a general overview of satellite information. So the orbit dimensions, live positions of the satellite, and a height graph if you want to generate one. Also gives you launch schedules as well. So it's a pretty neat website for obtaining general information about missions and orbits. Next, we have a visualization tool, which is orbital mechanics. This is great if you want to like map out and look at what the Keplerian elements of an orbit look like on the spot. So here we go. We're presented with a demo of the Earth. And let's make an orbit here. And these represent the 6 Keplerian elements. Semi-major axis, eccentricity, inclination, and so forth. So you can adjust these according to the TLE. Usually want to use this tool in conjunction with a TLE provider. So I typically use it with N2IO. And the first step would be just to like specify the satellite and then use N2IO to get the TLE of the satellite, which contains the 6 Keplerian elements in the bottommost row. And once I derive the Keplerian elements from the TLE, I just plug and play into this tool in order to figure out where the satellite is located and visualize it. Next, we have SatNow, which gives you really specified descriptions of components on satellites. So you can pick between the various subsystems like attitude control and determination, electrical components, bus platforms, propulsion systems, command and data handling systems, communication systems. So let's say I wanted to get or look into like the power system of a specific satellite. So I'll go here and I would click solar cells. And I would just do like a little bit of previous research on what solar cells are being used by this specific satellite by using another website. And let's say it's using the space qualified triple junction solar cell. So you would click that and it gives you a description of it. You can download the data sheet, which is really helpful for getting dimensional data. And it gives you the mass, the area, the thickness, a bunch of information that makes up the component. So whenever you want to inspect a specific component within a subsystem of a satellite, SatNow would be your go-to resource. Then lastly, we have Space Bandits. This is just a general informational site about startups in space. Usually there's not a lot of information about some smaller scale companies within the space environment. So this is really helpful for that. And you can click on whatever organization you're auditing. And it gives you information such as the year it's founded, its social media profiles, personnel behind the team, and funding and the scale of the company. All right, so now that I just showed you some of the main tools I know, I just wanted to provide some general tips for finding sources. The first tip is to check for the reputation of the sources and make sure it's from a credible organization. Also, governmental databases such as NASA and the European Space Agency databases are super helpful and they're extremely credible. I would also recommend sifting through resource references in academic papers because usually they tend to use credible data sets and databases as well. Also, pay attention to data sources utilized by space news outlets. You can find some hidden gems by looking through those. And I would also recommend exploring open source software programs and the application programming interfaces they integrate, because usually they're using APIs from a credible database. And lastly, a bunch of space forums and online discussions discuss reputable sources, and there's some tools that just pop up all the time, so I recommend looking into those as well. Lastly, vetting your OSINT source. Make sure you check for the source reputation, make sure it's not from a sketchy organization, and make sure it's at least from a credible space-based agency. Make sure you evaluate the source expertise and the people behind the source, so developers who develop the site, and the backgrounds of their development experience. I will also pay attention to the publication date, so make sure, because sometimes data sets are not up to date with the most recent year, so making sure that's clear. And also checking for citations and references in the source. So a couple of great ones I showed you in this lesson were N2IO. They were also integrating sources with the data they were providing. So that's a really good green flag. Also performing fact checking as needed by referencing other sources. So typically you don't want to just hone in on one source. You want to use multiple sources in order to confirm that the information being given is correct. And also look for public reviews of the data source online and see how researchers and developers are reacting to it. Welcome to the last lesson of the first module. In this lesson, we'll be going over Python programs for satellite reconnaissance. So this will be a more hands-on lesson where I'll be walking you through some interactive tutorials and Python programs you can utilize to do some of the OSINT demonstrations I mentioned before. Okay, so why Python for cybersecurity? The reason I chose Python for this course, other than other reasonable alternatives such as C or Golang, was because it has an extensive library. So there's already lots of cybersecurity tools that are written with Python. All of the open source programs out there already are written in Python, and it's a very simple language to work with. It has a minimal learning curve, has a very straightforward and simple syntax because it is a higher level language, making it really easy to pick up on if you're a beginner. It also features more robust capabilities such as built-in memory management. So whenever you're writing code or a program with Python, you don't really have to worry about managing your memory. Okay, so one general tip I wanted to give before we dive into looking over programs was to make sure you read over the documentation for each program before diving in. And some tips I have is to scan over key sections for each repository or program we look over. There's going to be a document called a README. And the README, if you scroll down, is like a general informational document about a program. And READMEs are segmented into key sections, which are delineated by titles and subtitles. READMEs also host a table of content section, which includes like a table of including links to different sources or different locations within the documentation, which I usually find really helpful. Also, like I mentioned before, read over headings and subheadings. This gives you a really nice general overview of the tool and its capabilities. I also think looking over the installation and setup section on the README, if it has one, is really, really useful because it'll walk you through the setup instruction based off of your operating system or different versions on your machine. It'll go over configuration details, any prerequisite knowledge you need to have, and so forth. So in order to find that, look for installation and getting started sections. Also, usage and examples, like I'll show you as we walk over some of the programs in this lesson, are also super useful because it helps you understand the software and the library and what it's capable of. And lastly, if the tool does host some kind of API documentation, I would recommend looking over endpoints and descriptions of endpoints listed in the documentation website or the README as well. Cool. So let's make sure one of the prerequisites of this course was to have Python version 3 and pip 3 installed. So let's make sure you guys have that. In order to do this, open up your terminal. On Mac, it's just you go down to your terminal menu. I already have it open. And for Python, just type in version. And right now I have Python 2.7, so you can use Python 3 if that's the case. Yeah, and that's what you're going for. You want Python version 3, not 2. For pip, it's the same thing, just pip in front of it. There you go, and you should be presented with an output that looks something like this. If for some reason you don't have Python or pip installed, I would refer you to the Python downloads website. It's python.org/downloads, and you can download the release that's latest for you. Okay. So I wanted to walk, before we go about demonstrating the program on our own machines, I wanted to walk through some really useful programs that have already been custom built and managed by other people within the community. And the first one is AstroPy. We can look through the GitHub and the documentation here. And it's essentially an astronomy and astrophysics core library for Python-based projects. So we can visit the GitHub here. Okay. So if you scroll down, you'll see a README. This is what I was referring to. And here they have a general description about the project. And usually when I'm like trying out a new project or program, I'm looking for any kind of documentation website they have. So it looks like they have a documentation website listed up here. And there you go. So you'll be presented with installation instructions. If you have a pip installed and if you want to install this program, it's pip install AstroPi. We won't be installing this programs. I'm just showing you guys some of the useful ones I've used in the past, because this lesson would be way too long if we went to downloading each one and showing examples for each one. But here, if you were to install AstroPi, you would do pip install AstroPi on your terminal. And then I would recommend looking into, if a program has an example gallery or tutorials or documentation, I would recommend looking into those. So here you can see they have a bunch of pre-built programs you can utilize. And generally they do show you how to set it up. So you say you would open up an IDE and then follow along with the instructions they provide. You can also use something like an online version of an IDE, like Jupyter Notebooks, which I find really useful, especially for research purposes. Yeah, they also have example tutorials on their website as well, and documentation. So this is, if you're looking for anything specific, I would recommend looking into here and they will show you how to do it. Cool, so that's AstroPi. The second one I wanted to mention was PolyAstro, which is a Python library for interactive astrodynamics and orbital mechanics, focusing on speed, reliability, and quick visualization. So it's really good for visualizing. If you want to visualize a satellite target in orbit, this is what I would use. So you can visit their website here. And you can see they also list their documentation page. If you scroll down on the README, you can see what it's generally capable of. So it includes features such as orbit propagation, solutions to complicated orbital-based problems, conversions between position and velocity vectors, and classical orbital elements and orbit plotting, among others. It focuses on interplanetary applications, but also is used to analyze artificial satellites in low orbit. So there you go. And also another thing to note when you're using a program is the dependencies and requirements it uses. So here it looks like it's using multiple dependencies. So you need to make sure, usually when you run pip install PolyAstro, it'll install these for you. So let's say you wanted to install this library onto your machine. I won't be walking you through implementing everything because I have one demonstration I will be showing at the end of this lesson, but I put it in the terminal here already. Sometimes if your version isn't up to date for Python, like it was on my machine, you'd use Python 3. If it's already up to date, you would use Python. So it would be this command. Cool. And just general documentation, I'd refer you to their website. As you can see, it goes through the capabilities of the tool. And I would recommend looking into their quick start as well. You can see they go over position and velocity conversions and visualizations of things in orbit. Okay. The third one I wanted to go over was SatPy. SatPy is a Python library for reading and manipulating remote sensing data and writing it to a variety of image and data file formats, specifically for meteorological-based satellites. It can also make various RGB composites directly from satellite instrument channels or higher processing output. This was a description from its website. Put simply, it means that on meteorological satellites, on their sensors, they're always retrieving information about the Earth or whatever it's monitoring within a garbled piece of data. So usually when you get data from those specific instruments, it's in a really unreadable format. So what this tool does for you is that it takes that data and it converts it into something that's readable or viewable, such as like an image, which is called an RGB composite. So let's check out their website and see what it has to offer. Okay, so I really like SatPi's documentation site because it makes things really, really clear. So here you can get a general description of what it's capable of in terms of its RGB composite types and instrument bands and products it supports. Just to note, with meteorological satellites, they have different bands and different instruments, so you need to take that into consideration when you're using a scientific Python library like this one. So here you get a list of its dependencies, and I just pulled up its installation page. So I wouldn't recommend using Conda. So you would scroll down and you would see pip-based installation, and you would follow the instructions here. In terms of downloading data from its different sources, here they provide a list of data sources they support. So they have the NOAA goes on AWS, Google Cloud Platform, and there's data browsers for each one. Yeah, so if you want to go about using this tool, I would recommend going to their examples page here and looking through their quick start. And I already pulled that up. And you can see they walk you through setting up a very simple page where you read over remote sensing data. So this is something you would get from a publicly available data set. So like one of the meteorological OSINT web pages I suggested in the previous episode, I would typically use like a NASA database for remote sensing or NOAA for meteorological sensing. And then you would download it, you plug it into the glob, and then you'll get an output like so. Okay. The next tool is CCSDS-Pi, and this is a input-output interface for reading CCSDS data in Python. So CCSDS stands for the Consultative Committee for Space Data Systems. These are like the big guys when it comes to space-based standards, and they pretty much just established a file or data format for satellite-based data transfer, and this tool lets you translate that information. And CCSDS, it's typically used for many governmental-based organizations. So NASA and the European Space Association typically uses this format. So let's go to their documentation website. Here we go. You can see like a general description here. And if you want to install it, you would run pip install CCSDS-Pi, and they pretty much put an example script here. So you just copy paste this into any script you have, and they just read over what a typical packet following the standard would look like, and then they load it into a TLM file. The next one is GNSS libpy. This is a modular Python tool for parsing, analyzing, and visualizing global navigation satellite systems, like I mentioned before, GPS satellites and so forth that are encapsulated under this constellation of satellites, and it states their estimates within space. It also provides a handy modular framework for allowing users to quickly prototype and visualize GNSS algorithms. So there's specific algorithms that allow you to describe the orientation and configuration of GNSS satellites, and this lets you visualize that. So let's head over to their documentation page. Here you can get general information about the tool. You can also visit their GitHub repository. And if you want to install it, you would run pip install gnss-lib-py. And then I would recommend checking out their tutorial section. Here we go. There you go. So you make sure you import it. And then you get an example data file. And you can access values of it, visualize it. Yeah, so I just recommend looking through. They have a parser as well as custom-based algorithms, so you can look over both of these too. And then lastly, the final tool I would recommend is EOReader. EOReader is a remote sensing open source Python library for reading optical and SAR constellations. You can load bands and get spectral indices for different sensors on satellites. So if you open up this website, there we go. So whenever you're investigating a remote sensing satellite, I would recommend looking into EOReader. So you can see they support both optical constellations as well as SAR constellations. And if you want to install this, it would just be pip install EOReader. And I would recommend looking into their example scripts they listed here and here. They also have documentation as well and a basic tutorial you could look over. Okay, so with these programs, they typically depend really on the type of satellite you're investigating and what specifications you have. So I made a very simple, streamlined environment for we could try out a Python program so you know the steps to go through in order to test out a tool like this one. So what we're going to be doing with this task is we're going to be tracking the International Space Station, and the objective will be to track down its live location and telemetry details, so where it is configured in orbit, where it is relative to us, when it's going to pass us, and plot where it is within its orbit in space and over Earth using some of the tools and programs and resources I mentioned in previous episodes. Okay, so let's first get the TLE of the satellite. We're going to be using Celestrak to do this. So go to this page in Celestrak. So it's Celestrak/NORAD/elements. So it'll be under space stations. Oh, there we go. And there we go. And we're going to be tracking the first one. So this is the TLE for the one we need to track. And then now we're going to be interpreting the TLE. So this is where we are going to be using a custom Python program that I made for one of my previous satellite hacking workshops. This just makes it a lot more easier and streamlined, since it doesn't have a lot of dependencies and it's really nice to walk through as a beginner-based program. So whenever you're met with a GitHub page like this for a satellite hacking tool, you go code, copy this, and then open up your terminal. So my terminal open here. And you can download this program into any folder on your machine. So I'll just do it in desktop. And let's do git clone. This just downloads the program from GitHub onto your machine. So now I have a folder called Satellite Hacking Workshop, so I'll just cd into it. Wonderful. Okay. So this tool has a script section. So we're going to cd into scripts. And there's, I think, two programs I created. We're not going to be doing the GNSS spoof one. We're going to be doing the Trackasat one. And before we run a program, we need to make sure we have everything installed. Usually, for a Python program, it'll have a requirements.txt file. For this one, I forgot to include one, so we'll just manually install everything. But in general, if there is a requirements.txt file, you just run pip install and put the requirements file there, but we'll just walk over everything. So the first command is pip3 install, and we're going to be installing this library. We're handling the mathematics of calculating an orbit. I already have it installed on my machine, but it'll show you like a list of things that it's doing when it's downloading. And once you have that downloaded, the second thing is NumPy. Okay, so make sure you have those two downloaded. And now, once you have it downloaded, run Python 3 trackasat.py. And it should be giving you like a list of questions. I'll make this a little bit bigger. Okay. So this is when we need to go back to our TLE and paste in all the details. So for the first one, it would be ISS Zarya. So paste that in. Paste in TLE line 1. Paste in TLE line 2. And you should be presented with, assuming you plugged in everything correctly. If not, just let me know in the comments. You should be met with a bunch of information about what we were able to calculate. And here we have the time offset, the radians per second, offset to apply. We get the satellite name, international designator, and also other really interesting mathematical information, such as the longitude and latitude, B-star drag term. Yeah. So now with this information, let's visualize its trajectory in orbit. So we use the orbitalmechanics.info site for that. There we go. And then let's put in the name of the satellite. So ISS Zarya. Into the orbit name, add orbit. Perfect. And now we can plug in our values. The semi-major axis for this tool is always pretty weird, so I tend to do that one last. But let's plug in eccentricity, and you can round. Usually like this tool isn't very calibrated, so. Okay, yeah, I rounded it down to 0. Inclination, 51. Okay. We have our argument of periaxis, which is W. We have our right ascensation of the ascending node. And our true anomaly to describe the position of our satellite in orbit. And then finally, this value usually just maximizes here, but we'll see what it does. Yeah, it just puts it to the maximum. So just drag it all the way here. Okay, so now if we zoom out, we should be able to see our orbit. Here, and our satellite is, on this tool, it's really a little bit harder to see, but your satellite is the red dot along the white ring. And you can like change this value here to see where your satellite will be in other moments of time. Yeah, and this is like the mean anomaly, so it's the only value related to the position of the satellite. So we can just drag it around and see where it will be. And usually the International Space Station is consistently orbiting around and has a velocity, so this will only give you a snapshot. It won't give you an animation, but it's good for general pinpointing. Okay, now that we've visualized our orbit using the Keplerian elements, in this tool I made it really clear that these are the 6 Keplerian elements and that I've calculated it. Now let's plot its ground track. So like I mentioned before in the previous episodes, the ground track is a 2D representation of where a satellite is over a map. So I would recommend using a tool called GeoPoint Plotter, which lets you just quickly map geocoordinates. And note the longitude and the latitude. So for this one, the format's a little bit wacky. So we'd do 30.34561, comma, which is the latitude, which is the longitude, pardon, and then the latitude, which is 14.0918 points. And you can see where it's over Earth at that moment in time. Just right here. You can adjust the point size and the point opacity as well. Whenever you're using an online tool, feel free to like play around with it. Okay, cool. The second thing I wanted to point out was its ground track. There's another great tool for that, which is located at this link. And if you scroll down, you get a ground track visualization of your satellite. So in order, the 3 main things you need to plot a ground track are the semi-major axis, how high the satellite is above in orbit, its eccentricity and inclination, which is listed in the tool, semi-major axis. So if you go into here, change the inclination to be your inclination number. So for ours, it's 51.64. So just put it. Yeah, that's about it. And its orbital altitude, that's going to be its semi-major axis. So 6796. Yeah. So you can get like a rough estimate of its ground track on Earth, above Earth. All right. One thing I did want to go over before ending this lesson was looking over some of the Python code. If you have an IDE installed, you can use an IDE. So I have VS Code installed, but you can look over this on like a general text editor. I won't be running over the code. I'll just be going over the logic. So let's see here. I'll run code, track, sat, pi. Okay, so this is just a rough program I put together. I won't be going too deep into the math. You can look into more orbital math stuff yourself. Typically, when you usually don't have to do any math. You can use libraries like I mentioned before, like AstroPy, to do the math for you. Okay, so here you can see I imported the libraries that I needed. The main ones being NumPy and FM. And here I just defined variables for the square root function, the pi function, sine, cosine. These are called functions. In programming, functions are just like a block of code that is meant for a specific purpose. So this does like TLE verification, splitting of the TLE, and then general calculations. And here, this is just doing the work of printing everything out on our terminal for us to see. So if I go into my terminal, this is what it's doing. It's just printing it out. And then all the math takes place here. So we have our timing math, calculating the timing difference, getting the period, calculating the semi-major axis, getting the true anomaly, converting it to degrees, and then printing it everything out. And this is just like an example. So I typically use examples to test out my program, so that's what I included there. Yeah, just feel free to check out this program in your own time if you're interested in how it works. But I just wanted to walk you through some of the code because it is important. If you're testing out a program and you're trying to troubleshoot it, or something goes wrong and you want to pinpoint what exactly is going wrong, looking for the code is a really readable indicator for troubleshooting and debugging. So some final notes I wanted to conclude this lesson with was a process overview for using programs. Firstly, make sure when you find a program to list over its functionalities by looking over its README and reading over its documentation on GitHub. Then try to locate, like I showed you guys in the examples, locate the documentation website and look for specific usage instructions. Then try to find example code snippets. And typically those websites have multiple code snippets and examples. So it's just about finding the right one for your use case. And then try to go the extra step of understanding the code. So once you have the program downloaded on your computer, you can just walk through the process I showed you with my tool, which was to look over it with an IDE and audit it and trying to piece together what it is used for. And then finally, you can customize it, write your own program using some of the libraries I showed you, importing them, and making your own open source code bases. And then and then you can share it with others, or craft it for understanding specific satellites. It's all about piecing together different programs and accessible libraries for your use case. The thing about hacking satellites is that it's highly variable depending on what system you're trying to hack into or what system you're trying to understand. So you really need to piece together what each tool or program does and put it together depending on your use case and scenario. And so just some general tips about finding programs for satellites. There's a lot of pre-built tools out there, so you don't really want to reinvent the wheel if there is already a tool or a solution for it. This just saves a lot of time. So I would recommend using the GitHub search functionality. So GitHub is a website that hosts a lot of open source programs, and make sure you search through it and find open source Python programs or any language you're familiar with. And you can put topics and captions such as like satellite or aerospace, and that's usually enough to filter things down. You can also visit the Python package index, which hosts all the Python packages and provides documentation for each one. And lastly, get involved in online forums and research. Typically, researchers, they know what they're doing, so they typically stick to a same list of libraries that are standardized and widely documented. So I would look into that if you're having specific troubleshooting problems or want to know which library to use for your own use case. Hello everyone, welcome to Module 2 of the Aerospace Cybersecurity Satellite Hacking class. In this module, we'll be covering satellite communication systems, and in this lesson specifically, we'll be going over the foundations of how these systems work. The reason why I chose satellite communication for Module 2 is because of its imperative nature to understanding satellite infrastructure. One of the most reliable access points we have to understanding satellites, and one of the most convenient, is satellite communication, because we can use any radio system we have in place alongside online tools in order to extract a lot of information from satellites. We'll be going into this a little bit deeper, but we can reverse engineer firmware. We can look over what's telemetry is being sent down from the satellite. We can look over remote sensing images. We can look over commands being sent to the satellite. So we can intercept a lot of information just by being able to analyze the communication that takes place between satellites. And in order to get that to the point of that with our penetration testing skills, we need to have the conceptual overview of how these satellite communication systems work. So this module is dedicated to understanding communication foundations on a more conceptual level, and then on the next module, we'll be diving deep into applying that into practical knowledge so we can reverse engineer and intercept communications and do a couple of simulated scenarios of what an attacker would do in a scenario of eavesdropping scenario, or how an attacker could exploit these systems to jam satellite infrastructure, so we can better understand how things work from a communications perspective and what from an attack-based scenario, so we can better safeguard these systems. So a bit of an overview of the communication that takes place between satellites. So when we're looking at a communication flow between satellites, we're mostly focusing on two elements. We're focusing on the ground station, and we're also focusing on the satellite. So the way the data flows between a ground station and a satellite can be denoted by these terms. So we have the uplink, which is when a ground station sends up communications to a satellite, and then we have the downlink, where satellites send data back down to a ground station. And there's two methodologies where communications can take place. There's one-way communication where it's just a simple broadcast. So there's no bilateral or two-way communication. So the data can only flow one way, like in the scenario to the left. And then there's point-to-point bilateral communication where there can be a two-way stream of communication between a ground station and a satellite. So I wanted to briefly cover electromagnetic waves because they're almost foundational to understanding a lot of the underlying technology behind satellite infrastructure. Satellites use radio waves to communicate with each other, which are intrinsically electromagnetic waves. So EM waves are electromagnetic radiation that describes oscillations of electric and magnetic fields. The electromagnetic waves consist of a magnetic portion and electric portion, and the electric and magnetic portion, as shown in this image in the left, are perpendicular to one another. And there's different ways we can measure these electromagnetic waves. There's two main characteristics. There's the frequency and there's the wavelength. So if you look to the diagram to the right, we can see as we go more to the right, we have more compressed waves together, meaning that there's a higher frequency. So there's more, within a given amount of time, we have more oscillations. And wavelength, it's pretty obvious like how long the wave is. So as we go to the left, wavelength increases. And satellite systems, satellites usually, they're all the way up in space. So we typically want to use portions of the electromagnetic spectrum that are high wavelength, low frequency. So radio is perfect for satellite-based applications because they're less volatile compared to higher frequency electromagnetic waves. And we're going to be looking further into how radio waves are segmented further into bands and how they are allocated depending on the function of the satellite. So intrinsically, satellites use radio waves to receive and send signals to and from Earth. That's the underlying scientific principle they use to send communications back and forth to one another. All right, so we covered the scientific principles of how it works. So what's the technology that actually allows for communication to happen? So we talked a little bit about the communication infrastructure, a little bit in the first module when we covered communication subsystems, but I wanted to dive into it a little bit further. So there's about 5 main components that comprise a communication subsystem of a satellite. Firstly, we have antennas. So antennas are devices for transmitting and receiving radio frequency signals for communication. And these are mainly just responsible for maintaining stable communication links, and they can be used for different frequency bands. Depending on the function, you might want to use a different frequency for your antenna, because you want to avoid collisions of frequencies. So you want to use different frequencies for different antennas, and antennas can be configured and engineered in a way so they operate on different frequencies and have different functionalities. There's also the command and control system, which is also referred to as the C2 system, which is responsible for managing the commands sent to the satellite and also sending back down telemetry data. So this could be data received from the sensors, like error messages, data, and so forth. There's also the transponder. The transponder is just a relay component. So it relays information that it gets. So just repeats information that it gets, but on a different frequency. So let's say it receives data on a frequency of like 2 gigahertz. It would repeat the same data, but it would relay it on a different frequency. So it gets it from a 2 gigahertz, then it will relay it on a 3 gigahertz frequency. And it does this by utilizing principles such as frequency shifting and signal amplification. Don't worry about it. It's a little bit technical, but we'll dive a little bit deeper into it when we talk a little bit more about modulation techniques and radio wave modifications. There's also the transmitter. This usually can be referred to in conjunction with the antenna, but I wanted to separate it a little bit further. So the transmitter is responsible for processing data and then modulating it into a carrier signal at a frequency. So it takes data in binary from the computer located on the satellite, and it transforms those bits of data into a wave so it can be sent back down to Earth. A receiver, on the other hand, does kind of the opposite of what a transmitter does. It receives radio frequency waves from a ground station and then demodulates it, so converts the waves into binary data, and then by separating it from the carrier signal. So there's two types of satellite communication methods. So the first type is radio frequencies. Most spacecraft communication systems rely on radio frequencies, and they typically operate within the range of 30 megahertz and 60 gigahertz. So that's a pretty wide spectrum. And it's mostly allocated for specific purposes. And they operate by sending out electromagnetic waves to and from antennas using through a specific channel. So a channel refers to where the data travels through, and in this case, it would be the atmosphere of Earth and space. And that factors into like a lot of things about the quality of the signal, which we'll discuss later on. Another method for relaying information via satellite communication systems is free space optical systems, FSOs. And the advantage of FSOs over radio frequencies is that they offer higher data rate flows by transmitting electromagnetic waves at a higher frequency. This is referred to as the optical frequency. And they usually use infrared bands within the range of 1064 or 1550 nanometers to transmit data. Although it does offer a higher data transfer rate, it has a narrow bandwidth, meaning that it has a little bit more accuracy with its directionality. However, because it has a narrower bandwidth, you have to be more precise with the motion control of free space optical systems compared to radio frequencies. Because radio frequencies, they take up a little bit more bandwidth, giving you more caliber to and more leeway in terms of the directionality of the antenna. So let's talk a little bit more about radio frequency systems because they tend to be the more dominant communication modality. So there's the communication architecture and the radio transmitter layout I wanted to talk a little bit about. So within the communication architecture of an RF system, we have the radio transmitter, and this is needed to convert data from bits into electromagnetic waves and then transmit it over a communication channel. So a transmitter on a satellite would transmit information from the onboard computer through space. And then there's the free space communication channel. That's just a fancy word for saying where the data flows through. The data flows through space and it flows through the atmosphere of the Earth. And this modifies a lot of things about the characteristics of the radio frequency wave, which alters not only you as a reconnaissance or a personnel who's looking into analyzing satellite communications, but also engineers who need to work around certain factors introduced by the environment the data flows through And the two most common ones are the space and the atmosphere. And then lastly, we have the radio receiver. This receives what was sent by the transmitter, and it captures it on a channel, and it demodulates it. So it receives data via a electromagnetic waveform, and then demodulates it, converts it into digital data that a computer can process in order to obtain a legible output data format. So looking further into the radio transmitter layout, we have the data interface. This is a connection where digital or analog data, so this could refer to like audio, video, telemetry data, and so forth. So it could be inputted into a modulator, and once that data is within the modulator, it gets encoded into a high-frequency electromagnetic wave. And then once it's turned into an electromagnetic wave, it passes through a power amplifier, which increases the output radio frequency power of the signal, so it can pass through a free space environment. And then lastly, that RF power is sent to the antenna, where it is transmitted to another receiver on the ground or to another satellite. Talking a little bit more in depth about the radio receiver. So you can think of the radio receiver layout steps as the inverse of the transmitter. So first, the receiver has a receiving antenna, which continuously listens for electromagnetic waves, and then routes, whenever it receives an electromagnetic wave from another satellite, it routes the signal to the receiver, and then that signal is then passed through a low noise amplifier. So this is used depending on the functionality of the satellite, but when it is implemented, it's used to minimize the thermal noise in some frequencies and increase the signal strength of the input. So it's amplifying the important part of the electromagnetic wave signal that's relevant to the satellite. Then we need to convert the waveform into a digital data form. So it goes through a demodulator, which converts the received electrical signal into interpretable digital data, which can be processed by the onboard computer. So a little bit of an overview of frequency bands. As I mentioned before, 30 megahertz to 60 megahertz is a typical range for spacecraft communications. Lower frequency bands are typically allocated for the following characteristics. They have lower attenuation, meaning that things in the environment are less likely to impact it. So they're a little bit stronger and more resilient. They have a larger coverage area, and since they're lower in frequency, they're less volatile, so they can penetrate through more atmospheric conditions, such as like rain or cloud coverage. However, the cons of it is that it's prone to crowding and it has lower data rates. On the other hand, we have higher frequency bands, and higher frequency bands are usually used for applications that require higher data rates. However, they tend to be more accurate and precise because they take up less bandwidth, meaning that there's less traffic, it's less crowded. However, they're more prone to signal attenuation, so things in the atmosphere are more likely to impact the integrity of the signal. They have limited range, and sometimes line of sight is required. So frequency ranges are really important for understanding the functionality of the satellite and for a lot of communication interception scenarios. So I wanted to define some of the common terms that you would need to understand them. So frequency band is a specific segment on a radio spectrum assigned for a specific purpose. A frequency range is the span of frequencies from the lowest to highest, on the spectrum. So to the left, we have a frequency range, and you can see it's partitioned into specific bands. The term bandwidth means the data transmission capacity of a frequency range. So how much data a specific frequency range is able to transmit. Satellite service is a communication or broadcasting service. A radio spectrum is a range of frequencies used for wireless communication. So it's a more specific definition of a frequency range, but applied to radio signals. And then we have the optical spectrum, which is a range of spectrum, including visible light and beyond, used for optical communication. So these are the two the spectrums you should know for understanding satellite frequency ranges, because they typically operate on the radio spectrum or the optical spectrum. So let's talk about frequency bands. So radio frequencies are split into bands for specific purposes, and the bands include very low frequency, which is 3 to 30 kilohertz, low frequency 30 to 300 kilohertz, medium frequencies 300 to 3000 kilohertz, high frequencies 3 to 30 megahertz, very high frequencies 30 to 300 megahertz, ultra high frequencies, and so forth. And you can see it depicted on the left here by this diagram. These frequency bands are more consistent. We'll go into satellite frequency bands in a second, which are less congruent to one another, but these are more standardized. So you can see they are evenly split apart. All right, so satellite frequencies are specific portions of the radio frequency spectrum, so it's more specialized for satellite applications. And they were determined by the IEEE, the Institute of Electrical and Electronics Engineers. And the bands include the following. We have the L band, which is 1 to 2 gigahertz, the S band 2 to 4 gigahertz, the C band 4 to 8 gigahertz, X band 8 to 12 gigahertz, KU band 12 to 18 gigahertz, the K band, and the KA band. So typical satellite services that could be provided using satellite communications include navigational satellite services. So this is typically used for applications such as GPS, which provide navigation, positioning of where you are located, and timing applications. There's also mobile satellite services, which are typically used for mobile communication devices, such as mobile phones or mobile terminals, which allow for live streaming of voice data. There's also fixed satellite services, which are services that are situated on ground stations, such as broadcasting and data transmitting. There's also direct broadcast satellite services, which are just applications such as TV based on satellites and radio broadcasting. And then there's VSAT, which stands for Very Small Aperture Terminals, more of a commercial-based satellite system, where it's a communication system comprising of small dish antennas and transceivers. So I wanted to talk a little bit in depth about each of the bands and what they are used for. So the L band is typically used for sea, land, and air communication handling. I also found this diagram on the left really helpful. So as you can see, as we go to the right of the satellite band spectrum, you get a higher throughput, and the antenna design will be modified depending on where which band on the radio frequency spectrum you want to listen into. So as you want to listen into higher frequencies, antenna sizes get smaller, band spectrums get larger, and as the radio frequency increases, signals are more susceptible to rain attenuation and rain fade. So the L-band is typically used for lower satellites and military-based satellites. Some GSM mobile phone providers use the L-band. Satellite TV providers also use L-band. And a famous satellite called the Inmarsat is located on the L-band. There's also the S-band. S-band is from 2 to 4 gigahertz, and this is typically allocated for radar and communication systems, typically used for public organizations. So we have NASA, which uses the S-band to communicate with the International Space Station. The mobile satellite service also operates on the span's band fragment. There's also agricultural remote sensing satellites and just scientific sensor-based remote sensing satellites as well, which use this band. The C-band is from 4 to 8 gigahertz, and this is used for communication satellites such as feeds and TV networks. This band is also utilized by marine ship communications, raw satellite feeds, and the fixed satellite service. Next, we have the X-band, which is from 8 to 12 gigahertz, and this is typically used for military services and civilian-based applications. So things like air traffic control operate on this band. We also have weather monitoring services. The fixed satellite service also uses this band as well. We have common TV providers, and the uplink for SATCOM, which is a very standardized satellite communication infrastructure, operates on this band. Next, we have the KU band. So the K band is a relatively large segment, but it's broken into 3 parts. We have the KU, the K, and the KA. The KU is the first part. It operates on the 12 to 18 gigahertz frequencies, and it's typically just used for communications. So we have applications such as radar operating on it. We have a lot of communication satellites, TV providers, and the fixed satellite service as well. The K band operates on the 18 to 27 gigahertz frequency, and this is also used for communication satellites and other miscellaneous services. The fixed satellite service uses this. We have radar systems as well, many communication satellites, and it also serves the downlink for SATCOM. Lastly, we have the KA band, which operates from the 27 to the 40 gigahertz range, and this serves communication satellites, also has high-definition satellite TV providers up there, two-way mobile services, and also the fixed satellite service. So let's talk a little bit about the system architecture of communication services. I talked a little bit about these components briefly, but I wanted to dive in a little bit deeper and show you guys a little bit about what's under the hood of these communication systems. So firstly, we have the radio and the demodulator and the modulator. I talked a little bit extensively about this, but essentially the transmission side modulates, codes, and amplifies the electromagnetic signal, while the receiving end demodulates and decodes the signal. So once a signal is modulated, it gets coded, so makes it harder for bad actors to intercept it and decode communications rather than having just plain raw data being sent. And that makes the receiver have to implement a decoder as well. There's also the mixer, which is a component that changes the frequency of a signal. And an up converter alters the frequency to be higher, while a down converter does the opposite. It alters the frequency to be lower, which is part of the mixer. There's also the filter, which removes interference and other signal alterations that could have altered the signal throughout its course through space or the Earth's atmosphere. We have the amplifier, which amplifies an antenna signal to strengthen it so it can be processed more finer. The antenna, which transmits signals fed to it by the transmitter and then receives signals propagated across space. And then lastly, we have the encryption system, which encrypts the data transmitted by the transmitter in order to provide secure communication across space. Diving a little bit into antenna systems, there's two main types of antennas. We have fixed antennas and deployable antennas. Fixed antennas are a little bit more convenient because they don't require any power. They are stationary. And some examples of common fixed antennas used on satellites are patch antennas, monopole antennas, array antennas, omnidirectional antennas, and horn antennas. There's also deployable antennas, which do require power to operate. However, you can configure their position. And some examples include parabolic reflectors, whip antennas, reflect antennas, turnstile antennas, and helical antennas. Antenna design depends a lot on the functionality that you want for the satellite. However, you can break down specific specifications of antenna design into the frequency, which denotes the range of electromagnetic waves these antenna can receive, and frequency. Engineers alter the satellite antenna a lot depending on what frequency they want it to receive. So this impacts the size, the gain, and the construction. Typically, higher frequencies necessitate larger antennas. There's also gain of an antenna, which is the ability for the antenna to focus signal in a specific direction. And in order to modify the gain of the antennas, engineers have to change the antenna type and the dimensions of specific components of the antenna. There's also the data rate. The data rate specifies the rate which the data can be transferred. This impacts many things, such as the modulation scheme, the bandwidth, the gain, and the signal to noise ratio. And then there's also the directionality of the antenna, which is its ability to focus its signal in a specific direction. And this impacts many characteristics of the antenna, such as its beam width, the antenna type, and any alignment mechanisms it uses. There's also transponders. So a little recap, what they do, they receive signals, process signals, amplify them, and then retransmit the signal to another frequency. And what makes up a transponder is an antenna, which transmits and receives signals. There's also a duplexer, which receives an uplink signal and then transmits it to the downlink. Transponders often have a low noise amplifier, which amplifies signals and increases the power from the uplink. There's a carrier processor, which handles the frequency down conversion of the uplink to minimize interference. So it reduces the frequency of the uplink in order to reduce any noise or any adjustments to the signal. And then there's also the power amplifier, which amplifies the power so it can be transmitted strongly down to the downlink signal. There's two types of transponders. There's single conversion and regenerative. Single conversion transponders receives microwave frequency signals, converts it to radio frequency signals, and then amplifies it to process data. Regenerative transponders are the same as single conversion. However, they include demodulation and modulation of the downlink signal to improve the signal to noise ratio. A little bit about the communication coverages of communication systems on satellites. So there's the aperture, which is the size of the antenna surface that transmits and receives electromagnetic waves. There's polarization patterns, which affect the orientation of the oscillations of electromagnetic waves, which impacts communication coverage. There's antenna radiation patterns, which is the radiation pattern of the antenna, which influences the coverage area and the shape of the signal back down to Earth. Environments can also impact the coverage of satellite communications. So this can include weather conditions, conditions of the atmosphere, perturbations such as gravitational forces and other external influences. The constellation arrangement can also influence communication coverage as well. For specific satellites like the GPS constellation, they are arranged within a specific manner to provide continuous coverage. There's also different constellations as well that optimize for other things. Diving a little bit into the ground station, so we covered most of the communication systems operating on satellites, but ground stations have communication systems as well that they use to process data that they get from satellites. So typically ground stations have a transmitter, an encoder for the transmitter, a receiver, a decoder for the receiver, and an antenna. Very similar to satellite communication systems, but a little bit of variance here and there. So for the transmitter, it transmits signal via an uplink, most of the times the C-band, to communicate with a satellite. And it uses modulation with intermediate frequency and then upconverts the signal. So it converts the signal to a higher frequency. It also includes an encoder, which encodes the transmission and makes the data contain error checking with bits. So it typically adds a few bits to the end of the data that it's sending. So once the receiver or the satellite gets the data, it's able to check the integrity of the data using the error checking bits. The receiver receives signals via the downlink from a satellite and then amplifies it using a low noise amplifier, down converts it into a lower frequency, and then converts it into data, demodulates it. And receivers typically have an embedded decoder, and the decoder is responsible for decoding the data with error-free binary by utilizing correction bits sent to it from the satellite. And lastly, ground stations have an antenna, which transmits and receives electromagnetic waves for communication. And it's usually comprised of a feed system and a reflector. Hello everyone, welcome to lesson 2 of module 2 of the Aerospace Cybersecurity Satellite Hacking series, where in this module we will be focusing on satellite communication systems. During this lesson, we'll be covering link design and communication protocols implemented by satellite systems in order to transmit data in an effective manner. So let's go over satellite links first. So a few terms we already covered is the uplink and the downlink, which is the link from the ground station to a satellite and vice versa, from a satellite back down to a ground station. This is the most basic kind of link you will get in a satellite link, a network. There's also things called crosslinks, also referred to as inter-satellite links. And this is in a situation where there's two satellites in a constellation that want to talk to one another. So when two satellites exchange information, that's called a crosslink. There's also links called feeder links. Feeder link is a specific kind of link used for broadcasting, where a ground station sends data to a satellite, which is then retransmitted to multiple other ground stations, which is demonstrated by the demonstration image on the left, where we have a feeder link from a ground station, and then that data from the feeder link is retransmitted to a bunch of other ground stations. So lastly, there's the user link, which is the link between a satellite and a user device. This is usually a type of link to use for commercial satellites, where let's say you have a VSAT terminal that listens into a satellite. That would be considered a user link. So let's go over a couple of key terminology before diving in. So firstly, there's something called a footprint. A footprint is a location on Earth where the satellite provides coverage. There's modulation and demodulation. Modulation refers to the encoding of data into a carrier signal to transmit. And demodulation is the opposite, where electromagnetic wave signal is decoded from a waveform into a digital data format. There's a term called latency, which refers to the delay in signal transmission between a satellite and a ground station due to specific physical constraints, such as the environment. And there's beamforming, which is a specific technology used to focus a satellite signal into a specific area in order to minimize the amount of interference from the environment. So let's dive into a couple of characteristics of antennas on satellites. So antennas on satellites typically have 6 factors that influence their quality. There's the equivalent isotropic radiated power, or also denoted as the EIRP, transmission losses, the link power budget, system noise, carrier to noise ratio, and atmospheric effects such as rain attenuation. So let's dive a little bit deeper into each one. So let's go into the most complicated term, which is the equivalent isotropic radiated power. And put simply, it's the measurement of radiated power of an antenna in a specific direction. So let's cover isotropic antennas. So isotropic antennas is an idealized antenna model used as a reference for antenna design. So in this image here, an isotropic antenna is perfectly circular and is not elliptical at all. This would be like a perfectly circular like antenna model. And we have here a practical antenna, which puts a gain on it. So it puts like a direction and a specific power to the satellite in order to the antenna to give it a specific directionality. So the EIRP refers to the power that an antenna radiates in a specific direction relative to this idealized isotropic antenna model. And it states that the max power output is equal to the direction with the highest antenna gain. And you can quantify this using a simple equation. Usually when you get data specification sheets, they do state the EIRP for an antenna. Let's go over transmission losses and signal attenuation. They both mean the same thing. You typically hear signal attenuation a lot in terms of like anything radio frequency related. So just know that transmission losses are the same meaning as signal attenuation. And it refers to the loss in signal strength as a signal passes through an environment like space. So these losses can be categorized into 2 main categories. There's propagation losses and there's local losses. Propagation losses are losses when a signal travels through an environment like space. And local losses are losses that are caused near a specific ground station, so it's more localized. And there's free space losses, so losses within the vacuum of space. Although that sounds a little bit counterintuitive, yes, signals can get attenuated within a space environment. There's also atmospheric losses, which can be categorized into ionospheric effects, which relates to effects from the upper atmosphere, the most prevalent being the Faraday rotation, which is induced by the Earth's magnetic field. There's also tropospheric effects, which are effects from the lower atmosphere, which can include a wide range of things, most commonly being rain. You hear a lot about rain attenuation. There's also gas blockage, sky noise, and depolarization, which can also induce transmission loss. And as for local losses, there's equipment losses, so satellite communication systems, the power and other effects intrinsic to the components themselves can cause a loss in signal power. There's also environment losses, such as the temperature, humidity, climate, etc., which also need to be taken into consideration when you're thinking about signal attenuation. Let's talk about noise. So noise is something that degrades the quality of a received signal. So when you hear a lot about antenna design, specifically for satellites, they're often trying to minimize noise. And a couple of key terms is noise spectral density, which is noise per power unit, and the noise temperature, which is the temperature of the noise generated by a specific component. And it's used to measure the performance of a component on a satellite. So there's receiver components on a satellite, which are electrical components within the communication subsystem that can cause noise due to their thermal operating temperature. So electrical components inherently generate some kind of heat off of their functionality, such as amplifiers, mixers, oscillators, whatever they are. They generate heat, which could reduce the quality of a signal transmitted by a satellite. There's also the cosmic microwave background of space, which is pretty cool. This is essentially radiation background that originated way back from the Big Bang, and it still impacts satellite components operating at microwave frequencies. There's also atmospheric noise, which is Earth-induced and originates from sources such as electrical discharge within the atmosphere and temperature variances throughout the day, which could introduce noise to a signal. So let's talk about ratios used to quantify antenna quality. So there's the carrier to noise ratio and the signal to noise ratio. And for the carrier to noise ratio, it measures the power of the carrier signal, which is the main signal type, relative to the noise of the system. And the signal to noise ratio measures the power of the desired signal, so not the entire signal, just the desired one, relative to the total noise of the system. I also wanted to talk a little bit specifically about rain fade. So you hear this a lot throughout the ham radio community, and rain fade is what degrades a lot of radio quality because of the rain and poor weather that are caused by the climate. So in terms of attenuation, it's caused from water droplets, which some droplets are large enough to absorb electromagnetic waves, which can cause signal diffusion and drop-off. It also impacts the system temperature. Rain increases the signal noise temperature of a satellite's downlink, which degrades the signal. And rain also can depolarize signals from the downlink of a satellite. Because of the shape of the water droplets, it causes some kind of depolarization, which leads to signal drop-off. Let's talk a little bit about antenna shapes and types. The antenna shapes are configured for a wide range of specific applications. I can go on and on about different shapes that antennas can assume, but a couple examples are omnidirectional antennas. Omnidirectional meaning like full coverage. It provides 360-degree coverage and broadcasts in all directions. There's also parabolic antennas, which are really good for long distance point-to-point coverage for high focus and gain. Although it has low bandwidth, it provides a really high focused directional signal. There's also helical antennas, which have circular polarization and preserves the quality of the signal. Horn antennas have a large bandwidth, so less directionality, and they're often used alongside parabolic antennas to reduce the amount of interference and increase the quality of the signal. And lastly, there's patch antennas, which are a type of antenna with a compact form factor, which features a low profile and low mass. Let's talk a little bit about modulation schemes. This is important, especially if you're thinking about decoding satellite communications. And modulation is a way to represent digital data into radio waves. because we can't really, there's no really great way to send bits throughout space, you need to transform it into a wave. Modulation is the art of which we transform that digital data into radio waves, and there's different ways about doing it. So one way is amplitude shift keying. This is the transmission of data by changing the amplitude of the carrier signal. So you can see demonstrations of each of these. So here we represent data by changing the amplitude. So we have 0, 1, 0, 1, 0. Zeros have this kind of amplitude, and then 1 have this amplitude, 0, 1. There's also phase shift keying, which encodes data by shifting the phase of the carrier signal. So here we have 0, and then here we shift the phase in order to indicate data. We also have frequency shift keying, which encodes data by switching between carrier signal frequencies. So let's say here we have for 0, a lower frequency. For 1, we have a very, very high frequency, 0, low frequency, 1, high frequency, 0. And then lastly, there's the quadrature amplitude modulation, which combines amplitude shift keying and phase shift keying to simultaneously transmit bits of data. So it's like a combo, all-inclusive of the features of ASK and PSK. There's also error correction coding that is included in the modulation process. And error correction is used to overcome the impacts of noise and interference. No matter how great environmental conditions are, you're always going to have some kind of noise and interference that's intrinsic. So there's different ways of integrating error coding. So when a receiver receives data that's transmitted from a satellite, it can check for errors and things that might have been messed up. So there's 2 main ways you can do it. There's the forward error correction method, which doesn't require any retransmission. And there's different methodologies. So there's low density parity checks, which includes linear block code. There's BCH, which corrects multiple errors within a 1-word code. There's the convolutional turbo code, CTC, which is multiple parallel codes to perform error correction, and then the Reed-Solomon for non-binary block codes. Going into each of them is beyond the scope of this course, but you can see that these are the types of FEC error correction coding schemes that are used. There's also automatic repeat requests, which requires retransmission to check for errors. There's the stop and wait method, which transmit 1 data packet before acknowledgement. And then there's the selective repeat method, which transmits multiple data packets before acknowledgement of those packets. So let's dive into link budget. So link budget is essentially just a performance sheet outlining the characteristics of a satellite's communication system. And typically in a satellite data sheet, it comes along with a link budget for its antenna and communication systems. And typically the characteristics that a link budget includes the frequency that the communication system operates on, the bandwidth, the modulation scheme, the coding scheme, the size of the antenna, the gain of the antenna, the directionality and the pointing of the antenna, the polarization of the antenna, the transmit power, its sensitivity, noise, and a lot more. So you can derive a lot of really interesting information from this sheet by performing a wide range of calculations. Most of the time it's calculated for you, and you can also use online calculators like the one I linked here to calculate specific characteristics of satellite communication systems. But you can derive a lot of useful information by using some of the equations I showed you earlier. You can get the signal strength, the antenna dimensions, the signal to noise ratio. You can derive the modulation schemes, data rate, transmission losses, frequency band the satellite is operating on, the EIRP, brain fade, regulatory compliance, and the total cost of the system. And a typical link budget would look kind of like this, where it's all outlined neatly for you. So another really great resource when you're diving into the reconnaissance phase of satellite communication systems. So the link process follows through phases of signal flow between the communication links. So we have the transmitter, which first modulates the data and then encodes it before it is transmitted across a communication channel. There's going to be specific mess ups that happen to the data as it travels through the communication channel, as attenuation and noise are introduced. And then lastly, we have the ground station component, which has antenna gain and receiver sensitivity in order to receive the data in a high fidelity format. So engineers select antennas for their satellite communication subsystems for a wide range of applications, and it can depend on a lot of things, but these charts really help. So things you need to take into account: specific atmospheric conditions and attenuations. So let's say you're trying to minimize for atmospheric attenuation, then you would use a lower frequency system. Range attenuation, also lower frequency, works better. If you want to mitigate free space loss, you would use a high frequency antenna. Same goes for bandwidth. If you're trying to optimize for the cost and complexity, you would go for a lower frequency design. The size is minimized if you're operating on a higher frequency, and the antenna gain is higher on a higher frequency. And typically, frequency ranges depend on their general applications. So things like mobile satellite services operate on a lower frequency, while broadcast satellite services and fixed satellite services operate on a higher frequency band. And you can see that outlined in this image here. And mission selection outlines also really help. So I picked out this diagram here, and you can see that depending on the type of mission a satellite is pursuing, such as Earth observation, educational purposes, there's specific recommended bands that satellite occupies, and then the gain of the antenna influences the antenna shape and the specific band it operates on. So this is also useful just by getting the category of the satellite. So like, let's say you want to track down a surveillance satellite, you would look into recommended bands, and it automatically like helps you hone down and figure out what radio band or frequency the satellite is operating on and what gain it might have. So these are all really great knowledge processes you can go through in order to figure out what communication systems is being operated on satellites, just by knowing what the satellite is used for. So let's do a hands-on lab and analyze a communication system. We're going to be reading over the information provided by an open source datasheet from the CubeSat 6U antenna system. And this CubeSat 6U was developed by a company called Aerospace. You can read more about it on their webpage here. So firstly, let's do a general reconnaissance search. So I just searched up this satellite system online, and I came up with their manufacturer website. So I looked through it, and I just got general information about it. It gives you information about the mass of it, the power, the payload space, the payload interfaces, the power bus. And here you can see, you can get access to information about their communication subsystem. And I will also look into the ADCS as well and the command management, since they tend to be integrated with the communication system. You can see here like affiliated communication systems with it. And I was able to find basic communication info just by looking through that page. And I was able to find a little interesting information. So it has two components, that operates on the ultra high frequency range, 340 to 680 megahertz, with an integrated antenna release system, and a very high frequency range from the 130 to 210 megahertz with an external antenna release system. And it uses two rigid printed circuit boards connected to a coax cable. It's compatible with the 6U structure, uses a dual pole design, and there's two product specifications, one for the ultra high frequency and one for the very high frequency. So I was able to get access to the data sheet for this just by looking through online sources, like I mentioned in the first module. And here, typically satellite companies just dump a lot of data in here that you're able to analyze for investigative purposes. And the main sources of information I was able to get were performance and characteristic sheets. So I was able to get the absolute maximum ratings. So if you go back in here, yeah, so it shows you the maximum operating temperature, the supply voltage needed for components, the resistor, the burnout, all of which can be exploited if you were able to get access to the onboard computer. You could change the temperature to exceed any of these and possibly cause a malfunction. Same with resistor voltage. It goes over electrical characteristics, so it operates on the 3.3 volts. It has a supply current of 50 milliamps, and it offers burn resistors as well. This is the radio performance characteristic sheet, which is a communication subsystem specific, which is important. So this gives us the impedance of the radio frequency, the power, and the frequency range that the antenna operates on, which is super important. So the minimum is 395, we get 450 megahertz, and the temperature range of the system. We also get the physical characteristics, which gives you a nice overview. So we get the mass of the system, how much space it takes up. And it also gives you a little bit of information about the polarization technique. So we know that it is circularly polarized. So yeah, whenever you get access to publicly accessible data, I would just recommend looking over their data sheet because you can extract a wide range of specifications from it. I was also able to extract modes of operation, so specific to the antenna. So for this one, it has three modes of operation. There's the right-hand circular polarization, left-hand circular polarization, and the hybrid, which combines the two. And for the right-hand circular polarization, it connects input one, and so you can see it connects input one and then terminates the others using a 50 ohm resistor. And the electromagnetic wave rotates in a clockwise direction. Left hand is the inverse, so it connects input two and terminates the other using a 50 ohm resistor. And it causes the electromagnetic wave to rotate in a counterclockwise direction. The hybrid connects both inputs, and depending on which one is being activated, right hand or left hand applies, and only one input can be used at a time. This data sheet also included radiation pattern charts, which are really interesting to see radiation patterns and influxes within them, and to derive directional characteristics of antenna radiation. So I was able to get charts for the realized gain over degrees. So depending on the direction, like how powerful the antenna was, you can see like near the 180, 200 mark, the antenna communication is really powerful, but then it drops off as it gets to like 300 degrees or 30 degrees, which is really interesting to see for both the modes, left hand and right hand. And then these 2D polar plots are often used to visualize gain and directions of antennas. So you can see visually which directions that the antenna systems are most powerful and weak. And lastly, they also provided 3D visualizations as well, just useful for general reconnaissance, in my opinion. So you can see in a 3D format for each of the modes, right hand and left hand, how powerful the antenna is directionally. It also went over a little bit about ground unit architecture. Some data sheets do this, some don't. This one did it, and it overviewed that it used 2 AX100 radios to communicate with the satellite. Interesting to know. And there was one radio for very high frequency signals and the other one for ultra high frequencies, because as we saw, just by generally looking over it, it had 2 frequency modes of operation. And the satellite can use both radios simultaneously for 2 separate conversations. So it will be a half duplex. So it's kind of like talking over a radio where only one person can talk at a time. So that's one mode it can operate on, or a single conversation where both sides can talk and listen to each other simultaneously, which is a full duplex communication. Hello, everyone. Welcome to Lesson 3 of the second module of the Aerospace Cybersecurity Satellite Hacking course. In this lesson, we'll be talking in depth about payloads deployed by satellites and data handling formats and techniques. So let's talk a little bit more in depth about the command and data handling subsystem. So I went over this briefly within the first module, but I wanted to take a deeper dive into its functionalities and components that make it up. So this subsystem is responsible for managing commands and sending data via the downlink to ground stations. It's made up of 2 core components, which is the command handling component and the data management component. The command handling component is responsible for retrieving, vetting, and moving around commands throughout the various subsystems on the satellite. So it sends around instructions to different subsystems, tells each component of the satellite what to do. And it handles the commands that are instructed to it by the ground station. So all the commands are sent to the satellite through a ground station, and this subsystem just listens in for those commands and then makes sure that the satellite follows through. The data management component of this subsystem is responsible for collecting and processing data that's collected by the different various instruments and sensors that are located on the satellite. And it's also responsible for formatting the data that it receives, storing it within its respective storage systems, and transmitting that data down to another ground station so it can be processed and analyzed by researchers. So let's talk about the specific functionalities that comprise the command and data handling subsystem. So all instruments and sensors generate a data set that needs to be transmitted to users on the ground. And however, when that data is retrieved from the sensors, it's often within a very unfamiliar format. So it needs to be formatted, it needs to be parsed, it needs to be modified in such a way that it's more interpretable and more standardized. So it's not like a big garble of data, so researchers can sift through it much more effectively. So this is made up of 3 steps. Firstly, you need to make sure that the data is formatted properly. And the way you structure satellite commands and messages is by adhering to proper protocols around satellites and making sure that data they collect from these sensors follow a specific structure. So when someone on the ground gets this data, it's structured and neat so they can look for it really quickly. You also need, these subsystems also need to know how to parse packets of data. And parsing means extracting information from a received data packet to ensure that the data is properly handled. So whenever data is sent to the command and data handling system, it needs to know how to interpret that data, and it does that by parsing it. Lastly, there's the transmission portion, where once the packets are correctly formatted, they need to be properly transmitted down to a ground station, which involves a wide variety of things such as power control, the configuration of the antenna, and modulation schemes that it uses. So let's talk a little bit more about data formatting, because there's many ways you can do that when a command and data handling subsystem is processing data that's being collected by the various instruments on a satellite. So as you can see, I listed a couple of the most common formatting standards. I would say the most common is the CCSDS standard, which stands for the Consultative Community of Space Data Systems, and they created a framework for space packet data handling, which includes a wide range of features such as data encapsulation, making sure they include details about the telemetry, and information about the packet itself, so metadata. There's also the FITS format, which stands for Flexible Image Transport System. And this is commonly used amongst scientific and astronomical research-based satellites. And the thing that makes this format unique is that it supports multidimensional arrays and metadata, making it really useful to transmit really high fidelity and detail-based data that's often collected by the scientific research satellites. There's also NetCFD, which stands for Network Common Data Form, and these are typically employed by Earth observation satellites. This system is optimized to store array-oriented scientific observations. So you see a lot of remote sensing and meteorological-based satellites employ this format. There's also HDF5, which stands for the Hierarchical Data Format version 5, and this system is optimized to store complex data, such as satellite imagery and data that requires the use of multi-dimensional data sets. So whenever a satellite's collecting a wide breadth of data, this format is commonly used. There's also more standardized formats you might have heard of in the past, such as JSON and CSV. This is often used when satellite designers are focusing more on simplicity and readability of the data. If you've ever played around with a JSON or a CSV file, you know that it's very simple and readable. And this allows for satellite telemetry and application-based information to be transmitted in a very interpretable way. A little bit more about data parsing. So parsing involves analyzing raw data that's collected by various instruments and decoding it and organizing it into a readable format. So this could be data that's received from a ground station or data that it's retrieving about the environment using its sensors. So for telemetry and asset decoding, telemetry and assets are typically decoded or compressed in order to minimize the amount of bandwidth that's consumed. You really want to make sure you compress all that information into as small of a space as you can so it doesn't consume that much bandwidth. And parsers on the satellite or on the ground station have to make sure that they take this into account as they captured various telemetry packets that are being sent to it, because they're often in a compressed format, so you need to make sure you decompress it and not lose all the value that's embedded within the packet. There's also format interpretation, which is another important step a parser has to take into account in order to figure out which format is being used by the satellite in order to interpret the data correctly. And it often does this by reading through a packet metadata. Whenever a packet is being sent and interpreted by a satellite, it contains a segment which includes its metadata, which is information about itself. So a packet would have information about itself, like the date it was sent, what format it's using. So parsers typically read it over the packet header, which includes this metadata, in order to figure out what format it's using. So maybe it might be using the FIT standard or the CCSDS standard. So before you go about parsing, you need to know which one it's using, or else you can't interpret the data properly. And lastly, there's metadata extraction, which I talked briefly about. And data packets usually contain a lot of metadata that's associated with them. And this includes timestamps, location data, where it was sent from, details about the instrument that should be taken into account when interpreting the data. So metadata is really important for contextualizing the setting of the data and making sure it's whatever you're interpreting is properly calibrated, so you're not making any hiccups in understanding the quality of the data. All right, so there's a lot of ways you can transmit data throughout space as well, and different satellites use different transmission methods, and this can depend on the type of data that's being sent, the coverage of the satellite, and various system requirements of the components on the satellite. So there's many ways you can do this, but four of the most common are high rate and low rate information transmission, HRIT, and LRIT. This is a direct mode of transportation of digital data, typically used by geostationary satellites to users. And the difference between high rate and low rate is the bandwidth. The bandwidth for the high rate method is about 10 megabits per second versus the low rate, which is 256 kilobits per second. So high rate tends to consume a little bit more bandwidth than the low rate, which allows it to have more information packed inside of it. For the high rate and low rate picture transmission, this is typically used for transmitting media assets such as pictures or photos the satellite may have taken. And this is a direct transmission of digital data that's often employed by low Earth orbit satellites to consumer users. And the data rate and the bandwidth is the difference between the high and the low rate. The data rate for the high rate is 0.5 megabits per second versus the low rate, which is 150 kilobits per second. So the high rate is a little bit faster than the low rate. Then we have automatic picture transmission. This is often used by weather satellites. I know that the NOAA weather satellite constellation, such as the GOES, uses this standard. And this is an analog signal transmission used to send images of the Earth's surface. This transmission takes place in the very high frequency band. Then there's the digital video broadcast standard, which is often used for television broadcasting. It uses a digital modulation scheme, such as and the MPEG compressing tool, in order to send high quality data with as much efficient bandwidth use as possible. So a lot of consumer-based dish antennas, whenever you're listening to satellite television broadcasting, is using DVB. So there's multiple levels of data processing that takes place, depending on how high-grained and straightforward you want the data to be. And these degrees show the level of processing that's involved and the refinement of the data. So level 0, this is just like plain raw data. These will be the data will be reconstructed and unprocessed at full resolution. So if you just want the data straight up as it is, this will be level 0. For level 1, it's a little bit formatted. So you still have that unprocessed and restructured data, but it includes some details about that data. So it'll include timestamps. If it's a research satellite, it'll probably include the spectra, additional notes about the data, and so forth. Level 2 is when you include a little bit more information, such as the geolocation that's retrieved by the geolocation sensor, and it'll just include sensor units as well. For level 3, this includes the level 2 data, but it'll also include chronological summaries, so little timestamps indicating what happened during moments of time. And then level 4, which is like the most processed and refined level, includes a model output, including a higher level analysis of lower level data. And I also wanted to note that these levels can be different and can have different interpretations depending on the satellite system being observed. For this one, I used the NASA data processing outline, but depending on the system you're analyzing, it can have more levels. I know some have like 5 or 6 levels as opposed to 4. 4 is the most common I've seen, but you just want to make sure you focus on what satellite system you're researching and the organization that runs that satellite, because different organizations have different data processing levels and schemes that they follow. All right, so how do we get command and data handling information? So as I mentioned, you can use a lot of online resources in order to get the data that's processed by the command and data handling system. So make sure some of the resources I would recommend when you're trying to learn more about the command and data handling system of a satellite is through sifting through satellite data sheets and manuals. So just search up the satellite, see what command and data system it's operating with by looking through its data sheet and then diving into it a little further, because they tend to have specification documents for each of their various subsystems. You can look into the specifications for the command and data handling. There's also research papers and publications out there that talk about various satellite systems, so you can possibly have luck by looking into research papers that talk about the satellite you're looking into. Space agencies and organizations typically release publicly accessible information about satellites. And then you can also, there's a more clever way of doing this, which requires a little bit more skill, but you can tune into the satellite and try to reverse engineer their signals. And by reverse engineering and decoding their signals, you can find a lot of information about the command and data handling system and how it formats that data, how it decrypts and encryption schemes it might have been using, sensor details. And also when you're looking into command and data handling system, make sure you look into the CDH, the CTP, and the onboard computer information. Those 3 subsystems are highly interlinked, so make sure you're not only focusing on the command and data handling system, make sure to look into how it interacts with the onboard computer, because most of the time you're communicating with each other all the time. And some of the so I included an example where I researched into the GOES-R series satellite, and I was just looking through data sheets and manuals they had, and they had a specific section on the manual that talked about the onboard computer. And when they talked about the onboard computer, they're inevitably going to be talking about the command and data handling processes it uses. So in the last paragraph there, I was able to extract that it uses the packet data format of the CCSDS right here. I was also able to find the transmission type. So it said that it uses space wire adhering to the IEEE 1355 standard. And I was able to figure out the data parsing standard. So it uses a space wire router card to do that in order to retrieve all the instrument science data. And then I was able to get the downlink format where it said it uses RDL, just a raw data link. So they're just sending raw data, pure, unrefined, level 0 data through their onboard computer. So let's talk about data flow within command and data handling systems. So the first step is data acquisition. This is where data is collected by the various sensors and instruments located on the satellites, which collect a wide range of environmental data in order to be processed. And once this data is collected, it goes through a processing method where that raw data is looked through by the onboard computer, and it is altered, it is changed, it is parsed, and it is formatted according to the communication standard that was established by the designers of the satellite. So this could be through SpaceWire, and it's sent to the various, and uses that communication standard to be sent throughout the satellite and to be managed and processed further. There's also command validation that takes place within a satellite. And this typically uses the command and telemetry processor as a gateway for the uplink and downlink data flow and making sure that there's no screw ups in the data. So whenever you want to make sure that before you receive something in the uplink or send something down in the downlink, you want to make sure that the data is not corrupt, because that could screw up a lot of what's happening within the various command and data handling subsystems. So what it delegates a lot of tasks to the command and telemetry processors to look for the data, verify it, make sure it isn't corrupt before either sending it down or accepting the data from a ground station. There's also redundancy management systems. A lot of satellites have a redundancy management card, which monitors the status health of all the various components, as well as the onboard computer, to make sure that everything is going well with the onboard computer before it processes anything. Because there's a lot of things that could go wrong if there's something that's corrupt about the onboard computer, and it might have some issues processing the data, which could lead to a wide range of repercussions. Let's talk a little bit more about signal demodulation and processing. As I mentioned before, signal demodulation is a process of converting electromagnetic waves, which is transmitted by a ground station or another satellite, into digital data so it can be interpreted by an onboard computer. So this processing setup is as follows. So it goes through signal reception, where it receives the modulated signals from the ground station. And then from there, after it retrieves the modulated signals, it goes through a frequency down conversion process where the signals are down converted into a high frequency, into a lower frequency. And then once it's converted down to a lower frequency, it goes through the demodulation process where digital data is extracted from a modulated carrier wave. Once the wave is turned into a digital format, it goes for error correction, because you don't know what things could have messed up the data throughout its route for the atmosphere and for space. So the onboard computer goes through various techniques of error checking, such as CRC and FEC. And once the data is checked for any errors, it goes for bit synchronization, where all the received bits are organized together and aligned with a clocking signal. And then once bit synchronization takes place, it goes through decoding and symbol timing recovery, where the data is decoded And then the alignment of the clock with the incoming signal rate is aligned together. So you maintain the integrity of the transmission. So it's like synchronization of everything. And then making sure that you have symbol timing recovery in place to make sure that the data integrity is preserved. And then lastly, the command and data handling system goes for data processing and routing, where everything is demodulated and decoded, and it's transported to various subsystems of the satellite to carry about instructions. So there's a wide range of differences between the type of data that's sent via the downlink and the uplink. Through the uplink, commands are being sent from other ground stations. You also have control signals and orbital alterations, which are specific commands telling the satellite to change its orbit. A lot of attitude control commands are being sent this way. And also, sometimes for the uplink, you can initiate software updates on the firmware that's being run on the satellite and change any configuration of the sensors and how that data is being processed. For the downlink, a wide range of telemetry that's being collected by the satellite, so like its speed, like where it is in orbit, is being sent down. There's also sensor values that's being collected about the environment that's being sent, the status health of all the components and subsystems, operation logs, and environmental data. So in terms of data handling, it's fourfold. So we have data generation, which collects signals from incoming telemetry data. And examples of components that does this are imaging devices, spectrometers, which handle data about light, radars, and sensors. There's the data interface, which is responsible for transporting data throughout the satellite. And examples of data interfaces include communication links and data interface protocols. There's data storage mechanisms, which offer both long-term and short-term data storage systems. So most satellites have a solid state drive and data compression techniques in order to efficiently store data. And lastly, the data processing unit, which manipulates measurements or data within the satellite. So this could be image compression techniques, data filtering, and analysis mechanisms. Let's talk about the onboard computer. So the onboard computer can be split into various components. And one of those components is the TMTC board. It stands for Telemetry and Telecommand Unit. And as you can tell, this is a part of the onboard computer that is delegated specifically for processing telemetry that's collected from the satellite and also telecommands that are sent to the satellite. And you can break this apart into multiple components. So there's the RX and the demodulator, which receives signals and demodulates it into their respective digital data representation. There's the receiver and the command decoder, which chooses the appropriate receiving channel to get that information from, interprets that signal, and then translates them to be processed by a CPDU. The CPDU is a command processing and distributing unit. This is a unit within the onboard computer that is responsible for processing the commands, distributing them throughout the satellite, and executing them. So it's like the moderator that oversees everything and tells each of the subsystems what to do. And lastly, there's the transmitter, TX, and premodulators, which firstly processes signals using techniques such as signal conditioning and filtering, and then modulates that data and sends it via the transmitter. The onboard computer also hosts a processor module, and the processor module, pretty complex component, handles a lot of things. but you can break it down into its various systems. It's pretty much responsible for handling the computing tasks of the onboard computer. So it has a memory management unit, which translates virtual addresses into physical addresses in memory, so it stores a lot of data. There's the system general mode, which optimizes resources among different subsystems. So it's constantly thinking about how the data should be distributed and how it can be optimized, how sending the commands to different components on the satellite could be optimized. There's the reconfiguration manager, which coordinates the settings and the parameters of various subsystems. There's the telecommand unit, which processes telecommands that are received from ground control systems. And then there's the watchdog timer, which monitors the health of the processor. And then there's the FDIR, which stands for Fault Detection, Isolation, and Recovery, which detects for any anomalies or faults within any of the satellite subsystems, so the processor on the onboard computer can act accordingly. So the onboard computer also hosts an AOCS computer and remote instruction sets. So the AOCS is a specialized computer for managing the attitude, the orientation of the satellite, and orbit control systems. It stands for attitude or orientation orbital control. And the responsibilities of this system is for command distribution and control. So it manages telecommands in order to initiate actions, such as adjusting the attitude or orbit of the satellite. It's also responsible for retrieving real-time information from various sensor inputs of the satellite. And then it's also responsible for obtaining reliable communication from the onboard data handling bus in order to facilitate data exchange throughout different remote devices. Let's talk a little bit about the OS5 model. If you're coming from a cybersecurity background, you're probably familiar with this model. And this is a space communication, and this is often employed amongst space communication protocols. And it's just good to know these layers. So whenever you're talking with someone, you can refer to what system you're talking about adhering to this model. So you have 7 layers in this model. There's the physical layer, which focuses on the transmission, like the physical aspect. So the physical transmission of signals through space. So examples of things located on the physical layer include radio frequencies, modulation schemes. There's the data link layer, which focuses on framing data packets, addressing them, and doing any error detection within those packets. An example of this is the CCSDS protocol. There's the network layer, which routes and addresses data between different systems. An example of something on the network layer is the internet protocol. There's the transport layer, which manages data flow and the retransmission of any corrupted data. An example of a protocol standard that adheres to this is the Space Communication Transport Protocol. There's the session layer, which manages communication sessions, and different custom session management protocols can be produced depending on the system. There's a presentation layer, which is responsible for translating, encrypting, and compressing data. So a lot of satellites have their own data compression standards. And then lastly, we have the application layer, which focuses on the application software that uses that data. So examples of this would be spacecraft firmware and ground station software that looks at the data and then processes them in order to run some kind of application. So let's talk about data packet protocols. So as I mentioned before, there's different communication protocols that are used to transmit data via satellite links. I mentioned the CCSDS Space Packet Protocol. This is the most popular and robust protocol for packetizing data transmission within space systems and satellite applications. There's also various other ones, such as the AX.25, which is used for a lot of amateur radio-based satellites. And it transmits data within a pretty discrete and formatted manner. There's also the DVB-S2 standard, which stands for digital video broadcasting. A lot of television broadcasting satellites use this. And it transmits data within an efficient modulation standard and includes inherent error checking. So it's often used to send efficient data, and that's why it's used for video distribution. And lastly, there's the PPP data packet protocol, which stands for the point-to-packet protocol. And this is used for direct point-to-point connections between two systems for data transmission. So when you receive data, it's often packetized and depending on the format, but I wanted to go over a packet structure and how you would go about decoding it and reverse engineering it. So by looking through the telecommand unit of a satellite, you can probably figure out what manufacturers will probably list what packet standard it uses, like the example I showed you before. And you can delineate a packet into the following structures. So there's the packet header, which includes metadata. It's often fixed size, so it's consistent amongst all packets. And you can extract the version number, the type of service the packet is providing, and the packet sequence control by looking and analyzing the packet header. It's often pretty easy to decode because it stays stagnant and all the data is fixed in size. So it's really easy to read over. There's the application data field, which includes the telecommand function code, the telecommand source and destination ID, telecommand time, and a wide range of other things depending on the packet protocol structure. There's also error control, which is part of the packet, which includes error detection data and error checking data. So you can modify the packet and figure out if it contains any errors. There's the secondary header, which contains a little bit more information about the packet and the data field. So in order to tune into a satellite, you need to make sure you know its communication links. And this is mostly coming down to your OSINT skills in order to find the satellite uplink and downlink information. Most satellite uplinks and downlinks are publicly disclosed, so you need to do a little bit of research in order to find their frequencies. Make sure you know what frequency band it operates on. Just by looking for the frequency range and getting its value in gigahertz, you can figure out what band it's operating on and its bandwidth as well. Make sure before you try to establish a communication link with a satellite, you note its direction of the antenna, like where it's pointing, its passing periods over your location, its frequency, its bandwidth, the polarization of the antenna, data rate, and the modulation that's being used. I also wanted to note some tools you can use to interpret packets. We'll be diving into some of these tools a little bit further in the next module, where we go about decoding and reverse engineering some data that's transmitted by satellites. But you can use the following open source programs to decipher communication packets. There's the Wireshark CCSDS dissector, which is a Wireshark script that's specific for dissecting CCSDS packets. There's the ECSS, which is the European Space Association's packet protocol, and the CCSDS Space Packets Library, which is a Python library that's specific for making packet implementations and decodings of those standards using Python. So if you're doing any like unique Python research, or you have a Python environment that you want to like get a live stream of packet data from, I would use this. And then there's PUSLib, which is an implementation of telemetry and telecommand packet utilization standards. So in that previous example, I showed an example of the a PUS telecommand packet. So whenever and it's a pretty common standard that's used by a lot of satellites. So whenever you want to decode a standard like this, it's a little bit more specific. There's libraries out there for that as well. Yeah, so a general overview of what would happen in an interception scenario. So first, you would go for the reconnaissance phase. This is where you're conducting open source intelligence about all the components, especially the command and data handling subsystem and the onboard computer, in order to figure out how the satellite is processing its communication. Then you would get satellite tracking information. So you would figure out when the satellite is passing through you, what time, and where it's going to be in orbit. Then you intercept the satellite signal using any technology you have access to. Once you get access to the signal, you go about eavesdropping it, which includes demodulating the signal and decrypting it. And once you're able to decrypt the data, you will see that the data is structured within a specific packet and figure out what that packet format is. Most likely it's CCSDS, or it might be another proprietary packet format. Analyze that packet, and then you'll be able to extract a lot of information from it. And also, if you get access to communication with the satellite, what bad actors do is that they figure out like the packet structure. They go about spoofing packets. So once you understand the packet structure, you can adhere to that structure and transmit data via the uplink to send or inject malicious commands via a covert channel. So a lot of bad actors follow this process so they can figure out what packet structure or data format it's using, so they can conduct a spoofing attack or an injection attack much more readily. So a lot of companies need to figure out the inherent vulnerability of, hey, like an attacker can just figure out what packet structure you're using and adhere to that structure and send up malicious data. So that's very important to take into account as well. Hi everyone, welcome to the last lesson of Module 2 for the Aerospace Cybersecurity Satellite Hacking course. In this last lesson, we'll be talking about satellite network architectures and inherent vulnerabilities within satellite networks. So I want to focus in on one type of satellite called the VSAT because it's pretty easy to define a satellite network architectures with those in mind. So a VSAT stands for very small aperture terminals. If you've ever seen some kind of dish antenna for a consumer-based satellite, that's a VSAT. It's used within small Earth stations to transmit and receive data, telemetry, and video over a communication satellite network. It has a transceiver and a simple interface allowing for translucent communication between a satellite and the ground station. So VSATs can have different network types depending on how the terminals are arranged. There's two types of network architectures. There's dedicated services. Dedicated services do not need a central hub to communicate. They communicate on a single carrier per channel basis. There's also shared services, which allow for multiple networks to interconnect within a time division. So let's talk about different network topologies. A network topology is like different arrangements and configurations you can have between a satellite communication link. So the most basic one is point-to-point. And this allows for direct communication between two satellites within a direct coverage range. This is often used for bulk data transfer, so things such as video, voice, etc. And point-to-point network topologies uses a multiplexer standard, where each station has to have a modem. These can be established pretty quickly upon a short notice. They're very easy to configure and alter. And the transmission range can range from kilobits to megabits. Star networks are a little bit more complicated, but they allow the satellite to receive inputs from different VSATs on the ground, and they mediate all communications through a central satellite. This is the most commonly used network topology because it allows for really great flexibility and transmission of data to take place in both directions. However, a data source cannot directly be transmitted from one VSAT to another. So these two can't communicate and these two can't communicate. It has to be routed through a central hub. So in this case, the satellite in the middle would be considered the central hub. This is really good for utilizing bandwidth and operating within a pretty flexible network. The second type of topology is the mesh network. This allows for intercommunication of multiple VSAT terminals. So there's no central point of communication between these VSATs. So you can see there's no centralization. They all can directly talk to one another. And this allows for direct connectivity, saving time because you avoid the double hop that's required for this one, or it has to hop here to here. These ones can just hop readily between each other. So this makes this system less prone to errors and very scalable. However, you do have to compromise a little bit of the bandwidth in order to get these benefits. The next network type is a combination of both star and mesh topologies. It's called the hybrid network. And this allows the central hub to send data to remotes, VSATs here. And these remotes can communicate with each other via a single hop. So you can see they can communicate with one another. And this is often used for large-scale and industrial applications. However, you have to consider that it is a little bit more costly to set up this kind of infrastructure, and it is more prone to error because of its inherent complexity. I also wanted to mention that within the consumer satellite infrastructure system, vulnerabilities can find roots all the way down to the household. So most satellite operations rely on technology, especially consumer-based like internet service providers, find roots all the way down to the household and its devices located in the household. And like we mentioned before, uplinks and downlinks to the satellite are often transmitted through open telecom network security protocols, making it really easy to decode and understand those communications. This also makes it easier for IoT devices, Internet of Things, embedded systems that use internet in some kind of way in order to get data or provide a service. And IoT devices that specifically utilize satellite communications are vulnerable to attacks. So let's break down some of the household networks and devices that use satellite systems. So firstly, satellite routers are very common, and these enable consumers to connect to the internet using satellite communication. So you might have heard of Starlink, which provides internet using satellite services. And you could see that what satellite routers are responsible for are encrypting communications between a satellite, authenticating communication and authorizing communication. So making sure that the data from the satellite maintains its integrity and is processed correctly. And also it features firewalls and intrusion detection. So if you were able to look into the router and dissect communication from a router, you can see all these things taking place. However, by inspecting these services, you can also notice a lot of underlying flaws within a satellite infrastructure. What if the downlink data was compromised? Then it can get processed by a router and cause a lot of damage. Let's talk a little bit about modems. Modems, inherently what they do is they convert digital signals from a network into analog signals for transmission. So they're responsible for modulating and demodulating signals that are transmitted over satellites. So all they do is they take in the wave data and they convert it to digital data, or they take the digital data and they convert it to wave data. So some consumer devices that use satellite systems include satellite phones. So most satellite phone providers are Iridium, Globalstar, and Inmarsat. There's also broadband internet applications, HughesNet and Viasat, also Starlink. There's global navigation satellite systems. And these systems depend on which country. So for Russia, it will be the GLONASS network. The European Union uses something called Galileo, and China uses BeiDou. There's also satellite imagery applications. Notable players in that realm are Digital Globe, Planet, and Airbus, and TV providers as well. You probably heard of direct-to-home satellite TVs, so DirecTV and Dish Networks are the most common. So things you need to have in order to set up a satellite consumer application require an antenna, which is used for capturing signals from a specific satellite. Most of the time, dish antennas are used for consumer applications because DirecTV networks utilize dish antennas. However, you can just use a standard antenna like a Yagi or a directional antenna or your custom antennas. I've seen people before create their own helical antennas or turnstile antennas in order to tune into the specific satellite. You also need a receiver. Most commonly, a software-defined radio is used, and this is used for listening to satellites and tuning into different frequencies and demodulating signals, which SDR really helps out with. You also need a computer to connect to an SDR and process signals, pretty obvious, and software. You need two types of software, a software that can predict where a satellite will be passing overhead of you, and another software for decoding and processing signals from a satellite and visualizing it. You also might need a low noise amplifier. A lot of dish antennas come with a low noise amplifier, and this is for strengthening weak satellite signals before they reach a receiver. And lastly, you need coax cables, which connect an antenna to a receiver. So what would be the step-by-step procedure to listening in on a satellite? Well, firstly, you need to understand what category of satellite you want to listen into, because what category you choose can determine a lot of things like the band, the bandwidth, when it's going to pass overhead, the type of orbital configuration it is in. So the main types are amateur radio satellites. I highly recommend these for beginners who want to get into it. There's an entire organization out there for amateur radio enthusiasts that are interested in space-based applications called AMSAT. Also, NOAA weather satellites, pretty easy satellite network to listen into and also get experience in decoding, because if you get communication from a NOAA weather satellite, you can create images of meteorological weather data. There's also scientific satellites you can get to retrieve scientific-based telemetry and data. There's also commercial satellites and military satellites. And choose out of the category which specific satellite you should listen into. And once you have that determined, you can look through sites such as N2IO. And the great thing about N2IO is they have like a category section. So you can look through each of the categories and find a specific easier satellite to listen into, find different configurations and so forth. And once you have that, make sure you have the frequency the satellite is operating on. I found this great resource online. You can go to this link, which has the downlink frequencies of a lot of satellites. So if your satellite is on that list, I would recommend just noting the frequency of that. And then once you have the frequency, you need to understand how transmissions are being modified. So figure out the encoding format, whether it uses analog modulation, frequency modulation, packet formatting techniques, and so forth. And then finally, figure out when the satellite is going to be passing overhead of you, so you can intercept communications with the satellite. And you also should consider other things that might alter the signal as you try to listen into a satellite. So things such as Doppler effect, you should consider. So satellite constellations can be designed in order to provide a specific service. So a satellite constellation is a network of very similar artificial satellites with a common goal in mind. So Starlink would be a satellite constellation. And when engineers are developing these constellation design, they need to account for multiple things. First thing is space traffic management. A lot of satellites operate within low Earth orbit, especially consumer-based satellites. And low Earth orbit is very, very crowded because a lot of companies are sending their satellites up into low Earth orbit. And there's not really a common standard for allocating objects in space. So a lot of constellation designs are proprietary, and it's good to know how they are arranged. They also, whenever you're creating a constellation design, engineers have to account for orbital perturbations, which are factors that affect the orbit of a satellite and can modify it over time. So these are things such as atmospheric drag, solar radiation pressure, and gravitational forces from other celestial bodies in space. You should also consider data relay and distribution. So data relays are satellites used to relay information between satellites in a network. So whenever, it's like kind of like a repeater in radio theory. So whenever a data relay gets data from another satellite, their job is just to repeat it. And they serve as intermediaries for facilitating communication to other satellites and ground stations. And data relays are often used to overcome line of sight and enhance coverage. The most common data relay system is coordinated by NASA. It's the TDRSS, the Tracking and Data Relay Satellite System, which are geosynchronous communication satellites solely for data relaying. When satellite engineers are coordinating satellite layouts, they also need to be thinking about coverage layouts as well. And there's two different types of coverage layouts. You can have global coverage or direct coverage. And global coverage satellites are designed to provide services that span the entire Earth. And these are typically located within low Earth orbit and are geostationary. And their sole purpose is providing continuous coverage for specific regions. And they want to provide international coverage as well. And these allow applications to cover the entire Earth surface. And they offer higher latency because as global coverage satellites tend to be a little bit higher up in altitude, they have more latency, so it takes more time for data to travel back down to Earth, and lower spatial resolution. Targeted coverage, on the other hand, is a little bit more specific and fine-tuned. These are satellites designed to provide services directed on a specific region. So there's different types of orbital configurations that are specifically for targeted coverage, such as geostationary, low Earth orbit, and medium Earth orbit. And these are satellites that can fine-tune coverage into specific regions. And these provide the benefit of having a higher spatial resolution for specific detail monitoring satellites. So you can see a lot of remote sensing and satellite imagery services that want to be really specific and have really high spatial resolution using targeted coverage. However, the drawback of using targeted coverage is that they are limited to a specific area, and however, they do have shorter contact times. So let's talk about the future of satellite communication, because Earth and space communication is relatively new. We've only been up there since the 1960s, and a lot of things are changing. And as cybersecurity is more prioritized within the space-based atmosphere, these new technologies are being implemented, and it's very useful to be cognizant of these developments. So firstly, there's the 5G ecosystem. So a lot of satellites now are being integrated within the 5G network, which provides a lot of added benefits to the previous 4G cellular networks that were in place. There's also reducing technologies for reducing low Earth orbit satellite latency, making communication with low Earth orbit satellites faster. And there's more encryption standards being put into place. I think I might have talked a little bit before that a lot of space companies, you're using proprietary encryption protocols because there's no really standardized universal encryption protocols. However, there's more recent and modern developments being made that provide reliable encryption standards for all satellites to send secure and encrypted data, which is great. And then lastly, I find this personally really cool. There's quantum encrypted satellites. There was this Chinese company who made a satellite using employing quantum mechanics that provide really, really secure satellite communication, like almost unhackable communication links. So diving a little bit deeper into each one. So for 5G networks, satellites have been used widely to optimize coverage for these networks. If you don't know, a little bit of background about 5G, it stands for fifth generation mobile network. And this provides the added benefit of increasing transmission speed and reducing latency within cellular networks. And a lot of satellites are being implemented within 5G networks in order to beam down communications to terrestrial systems from space. These provide the added benefit of having better coverage over remote areas and can be utilized for a wide range of applications such as Internet of Things services. Talking a little bit more about technology reducing low Earth orbit latency. A lot of satellites are located within low Earth orbit. So there's been recent advancements that have been made for these satellites to reduce their overall latency. And there's different ways of going about this. Starlink uses phased array technology, which allows satellites to steer their beams electronically in order to have constant connection with ground stations. Another way is digital signal processing and beamforming, which lets satellites focus and fine-tune their signals in order to reduce interference and improve the quality of a connection. There's a lot of initiatives that are employing these new technologies, most common ones being Starlink and Project Kuiper, which are both great initiatives for reducing latency within their own constellations of low Earth orbit satellites. Let's talk a little bit about improved encryption standards. So there have been way more initiatives to coordinate a universal encryption standard. Some initiatives have been formed by the CCSDS, who played a vital role in establishing standards for secure communication in space missions, including cryptology and encryption standards. NASA has also been involved in creating a more reliable communication standard, specifically for their spacecraft. And one very commonly employed encryption standard is AES, which has been widely used for security communications and has been widely accepted by the space community for providing reliable and secure communications. Lastly, with quantum encryption and integration with satellite systems, quantum encryption inherently allows for an ultra-secure telecommunications satellite because it uses something called quantum cryptography, which implements the laws of quantum mechanics to keep transmitted data super secure. Recent developments around this have been formed by the European Space Agency, which announced a project called the Eagle-1, which will be the European Union's first quantum key distribution-based satellite. As I mentioned before, there was a Chinese satellite launched in 2016 called the Messias, which was able to send quantum encrypted messages from orbit back down to Earth. So there's been a lot of very exciting technologies taking place in the last few years, and I'm very excited to see where it goes. Hi everyone, welcome to lesson 1 of the third module of the Aerospace Cybersecurity Satellite Hacking course. In this module, it will be pretty interactive. We'll dedicate this first lesson to getting a general overview of satellite communication system, and then the rest of the 3 lessons within this module will be completely interactive, where you'll be installing software and libraries on your computer in order to follow along with some of the steps. I really believe that satellite communications, and the reason why I dedicated an entire module to it, was because it's one of the most readily accessible things we have in terms of cybersecurity that we can emulate in a ethical manner. So it's pretty simple to simulate, and it's the most accessible link in terms of satellite security that's easy to access and develop tools for that are open source and online, so you don't really have to pay anything to get access to those tools. All the tools we'll be using in this lesson and within the following lessons are going to be free and available online. Most of them will be open source as well, so you can take a look at features they involve and integrate them as a part of your workflow. So let's get an overview of what we will be covering within this module. So the lessons I dedicated and included in this module will be dedicated to eavesdropping and communication interception scenarios, and also reconnaissance for communications with satellites. And you can break this down into 4 layers. The first one is telemetry gathering. We covered a little bit of this in the OSINT module, where we'll be actively gathering the location and orbital information about a satellite. So we'll be gathering the band type and the frequencies using online data sources and using accessible software in order to plot and predict where a satellite is going to be passing. The second step, once you gather the relevant telemetry for your target, is to listen into the satellite. So I'll be covering a couple of tools and equipment that's on the cheaper side for hardware, where you can actually listen into satellites and how you would set up your antenna and what antenna would be correct application for your satellite. So we'll be talking a little bit about that as well. The third step is packet analysis and dissection. We'll be going over Wireshark in the third lesson, where we'll be getting realistic packet data. We'll be analyzing them and dissecting those packets in order to see what protocols they've employed. We talked briefly a little bit about CCSDS, so there's also a lot of other relevant protocols that are used in sample route space-based networks, so we'll be covering those. And lastly, we'll be covering reverse engineering and firmware auditing. A lot of embedded systems within satellites contain firmware that can be reverse engineered, and by analyzing its raw data, hacks, and binaries, and fuzzing and running unit tests on that firmware, we can extract a lot of interesting information that hackers possibly might employ in a communication interception scenario. Okay, so with that being said, anybody could listen in and hear data from a satellite. You don't need that much to get started. So if you're a beginner who wants to just get your a little bit of experience with listening in on satellites, maybe you don't really have a ham radio license or you're not very acclimated with using radio, it's pretty simple. What you really do need to get started is just a handheld radio. In amateur radio, they call it an HT, so handy talkie, and a handheld Yagi antenna, which is a type of directional antenna. I'll be talking a little bit more about it. And for beginners, for the handheld radio, make sure you get a single dual band handy talkie. In order to get optimal results for the radio, make sure it's capable of attaining full duplex communication. Full duplex is a standardized way of communication for radio. Half duplex is where only one part could be speaking at a time, while full duplex is continuous possibility of communication from both parties. So both parties can speak at a time and they can listen into each other, while half duplex, only one person can speak at a time. You can't overlap the communication, while full duplex, you can. So make sure your handy-talkie is capable of attaining that, because this will become really handy for FM satellites, which encompass a wide range of them. What I started out with when I was first listening into satellites was a Kenwood THD72A. You can also use the Baofeng UV5R, which is a dual band and two-way. I would recommend the Baofeng UV5R. It's pretty cheap. I think it's like $30 or $40 on Amazon. You can get pretty accessibly. I might have one on my desk. Anyways, yeah, make sure you get a handy-talkie. The second thing you will need in order to communicate with a satellite is an antenna. I would recommend getting a handheld Yagi antenna, also cheap and accessible on Amazon. I think I got mine for about $20, so in total it should be at least less than $100 worth of equipment. The reason why I need something more complex than a traditional rubber duck antenna or whip antenna is that communication that's being sent from satellites are often using radio waves that are being emitted all the way up from space, which is pretty far away. So when it comes back down to the atmosphere, all the way down from space, signals from those satellites tend to be pretty weak. And a traditional rubber duck antenna, like one of those like vertical, small antennas, won't be really capable of receiving those signals. So you need something a little bit more robust, and a Yagi antenna is a great option, especially for beginners who want to use it alongside a handheld. And then the Yagi antenna allows you to produce enough gain to hear antennas, to hear satellites from the ground. One Yagi antenna I would recommend getting is the HYS Yagi antenna. This is great if you want to listen in on the International Space Station. That's how I personally started out. I got a handheld radio and a handheld Yagi antenna and listen in on the ISS. This supports the ultra high frequency band from 400 to 470 megahertz. So I recommend checking that out if you're interested. A little bit more about antenna types. I would highly recommend checking out an AMSAT resource called For Beginners, and they have an entire, I think, 30-page PDF going over getting started with radio and radio communications with satellites. They walk you through a lot of examples using amateur radio satellites, which are perfect for beginners, and it's also a great excuse for getting more involved in the radio world as well, because within cybersecurity, RF encompasses a lot of different avenues of exploitation, so I would recommend checking it out. So generally there's two main antenna types. There's directional antennas and there's omnidirectional antennas. Directional antennas, as you can assume from the name, focuses radio frequency energy in one specific direction. The pros of this is that it allows for further transmission and it can pick up weaker signals. But the caveat is that these are highly directional and you need to make sure they are pointed in the right direction or else they won't pick up anything. Omnidirectional antennas, on the other hand, are pretty good for beginners who are looking for cheap antennas they can use if they want to build their own, or they just want a cheap alternative and don't really want to pay attention to making sure that the antenna is pointed in the right direction. This type allows for more leeway in terms of errors because it avoids having a really strong polarization deviation. So polarization is the orientation of the radio wave the antenna is able to pick up. For directional antennas, they can either pick up vertical or horizontal waves, and the deviation between a horizontal and vertical misconfiguration could be as big as 30 decibels, while the ones that omnidirectional antennas picked up, which are circularly polarized, can assume two configurations: right-hand circular polarization and left-hand circular polarization. And the misconfiguration deviation between the two are much smaller. It's only 3 decibels for circularly polarized antennas. So some examples of nice omnidirectional antennas are the Leidenblad, the Turnstile, and Quadriflyer. For directional antennas, Yagi antennas and traditional dish antennas work great. So really, you need to, whenever you're picking out an antenna, make sure to weigh out the pros and cons and what you want. Omnidirectional, if you don't really want to pay attention too much to configuration, you just want to let it stay there and not tinker around too much, is great, but you're also sacrificing the strength of the signal you can attain. If you want a really high quality transmission and you're willing to sacrifice some of the leeway of not pointing it in the right direction, directional antennas would be your way to go. So let's talk about antenna optimization and techniques you can use in order to get the best signal transmission from a satellite. So I mentioned this before, making sure you can use some kind of circular polarization. This highly depends on the type of antenna you choose, of course, but it's typically much nicer to deal with circular polarization because the difference between right-hand circular polarization and left-hand circular polarization is 30 decibels, while vertical and horizontal can be as big as 30 decibels. It's also good to have gain and bandwidth in mind. You need to make sure you know that the higher the gain of an antenna, the narrower the bandwidth. So put simply, if your antenna is really good at picking up specific like low strength transmissions, you're also sacrificing the amount of bandwidth, the breadth of the frequency, the breadth of the signal it can get access to. And this will influence the type and directionality of the antenna you choose to buy. Lastly, make sure you have some kind of high quality feed line. It's highly recommended that you use a low loss coax cable. The reason for this is that by using a low loss coax cable, you're avoiding a lot of avenues for feed line transmission loss. Since satellite signals from space are already weak in the first place, it's already disadvantaged to have some kind of long coax cable that results in a lot of transmission loss. So make sure you have high quality coax cable to connect to. All right, let's talk a little bit about transponders. So the amateur radio community refers to transponders within satellites as crossband repeaters in space, meaning that they're able to receive and transmit what they hear on another frequency and on another band. So they're pretty much repeating whatever data that's sent to it on a different frequency and a different band. One thing to make sure to do and account for when you're dealing with transponders on satellites is Doppler shift. So Doppler shift is this weird physical effect that happens that's dependent on where the satellite is located in space. You're probably aware that like if there's like an ambulance right next to you, the noise from the ambulance is really, really high pitched and the volume is super high, but as it travels further and further away from you, the pitch and the volume of the ambulance diminishes as it gets further away. The same thing applies to satellites. So as a satellite approaches, frequencies will appear higher, so radio frequencies, than it is. As it passes overhead, both the uplink and the downlink frequencies will both appear to drop. And this effect is more prominent on higher frequency and shorter wavelength bands. So usually most handheld radios, if you're using one, allows you to program a range of frequencies beforehand. So before a satellite pass, you would just program in like a list of frequencies to account for Doppler shift, and then change it as the direction of and the position of the satellite changes over time. Another thing to account for when you're dealing with a transponder is an operating mode. So this goes back to our OSINT module. When you're looking for transponder information, make sure you pay attention to the shorthand denotation that it has. So a lot of transponders, they'll be denoted using some kind of like mode and letter sequence identifiers. So for example, like mode U/B would be an example of a transponder operating mode. And this is just a shorthand for uplink and downlink frequency bands. This is just convention, making it easier for people to figure out what band the transponder is using, whether it's like very high frequency, etc. So for example, the mode U/B band, the first letter is the uplink, the second letter is the downlink. So it has an uplink tuned to ultra high frequency and the downlink tuned to very high frequency, which is pretty handy to know if you want to interact with both the uplink and the downlink. Usually, if you're just wanting to tune into a satellite, you would pay attention to the second letter because that's the downlink. But if you want to know the uplink, you just look at the first letter and you would know what frequency band it operates on. Very cool. So another thing I wanted to mention are software-defined radios. Software-defined radios are very nice, cheap, and reliable communication modality for analyzing all kinds of satellite communication. If you don't have one and want to get more into analyzing satellite communications, I would highly recommend you invest at least in an RTL SDR. It's pretty cheap. I think it's about $40 to $60 when I first got it. And all you need, other than that, it would be an external antenna. And what SDRs do is that they contain a radio front end, which has an independent receiver, RX, and a transmitter, TX. And they're both radio chains, and they connect to a digital backend. So the radio front end contains the receive and transmit signals over a very wide tuning range. So you have a tuning range that you can specify, and you're not confined to a single tuning range, and you can analyze a lot of different signals. They're capable of handling very high data rate streaming and recording services. They can pretty much work with waveforms of any frequency, although it is limited by the converter on the SDR. And they utilize a technology called beamforming for improving connections. And usually people invest in an SDR because of its compact size, and they offer a reduced SWAP, which stands for size, weight, and power. I listed two on the side, the RTL SDR and the HAC RF. The difference between the two is the RTL SDR is cheaper. However, it can only receive, so you can't transmit anything. The HAC RF, on the other hand, it can both receive and transmit. So it's slightly more expensive, actually significantly more expensive, but you do have the power of transmitting if you want to. Other alternatives to the RTL SDR would be an Lime SDR or SDR Sharp. There's better documentation about this on the internet than what I can recall right now. So make sure there's different types of softwares, there's different types of hardware you can use, but the general capabilities are the same. Make sure to look at what frequency it supports before investing in one. but I highly recommend you get one. Okay, so when you're listening into a satellite, you need to make sure you pay attention to a couple of things. So firstly is getting the Keplerian telemetry. If you don't remember, this is the orbital configuration of a satellite with all those weird and wacky terms. And you need to make sure that you get a reliable stream of this data and tracking information from a reliable website. We covered a few, like N2IO. Another one I would recommend is AMSAT. AMSAT has a past prediction tool on their webpage, which is pretty nice. And make sure you check that a few times during the day before you want to listen into a satellite, because if you're not dealing with geosynchronous satellites, you only get access to passes chronologically throughout the day. Like I think most satellites usually pass 5 to 6 times over your location. So you need to know where it's going to pass, and also other details like where it's first going to pass, the acquisition of signal, and when you're going to lose connection with it. And those tools provide you with that information as well as frequency information as well. Awesome. So you can also tune into beacons on satellites. Beacons, you might have heard this phrase used within Wi-Fi hacking, is pretty much like an informational billboard of data that's useful for understanding what a satellite does. So typically a beacon on a satellite would transmit a lot of information containing the status health and the configuration of the transponder and what mode it is. Other useful information to note are that principal bands for satellites are used on the 2 meter and 7 centimeter. And then FM satellites, or frequency modulated satellites, are generally used for phone and packet transmission services. And single sideband satellites, the difference between frequency modulation and single sideband is that frequency modulation takes up more bandwidth. However, it contains more high quality data. So usually it will contain like voice data or video data because it takes up more bandwidth, takes a little bit longer to transmit, but it's capable of handling that. Single sideband, it's a little bit more efficient, but it takes up less bandwidth. So you see the data used in single sideband satellites is not as detailed as they are within frequency modulated satellites. And single sideband satellites carry continuous wave data, also phone data, SSTV, and PSK31. Okay. So let's go over what kind of information you can extract from getting radio data about a satellite. So decoders come in various formats, and software running on these decoders are designed to interpret and process signals received from satellites. So typically a good decoder will contain a demodulator, which is compatible with different modulation schemes. It'll contain an error correction decoding suite and a protocol decoding suite. For telemetry frames and packet analysis on signals from satellites, you'll have some kind of telemetry decoder, which takes in this radio signals and then is able to extract telemetry data out of it. There's also more specialized tools like image and data decoders. And you can also inspect the signal using hex analysis to figure out what the data configuration is like. In terms of reverse engineering and general communication analysis, there's lots of payload and firmware auditing tools out there. Usually it's more general purpose. I haven't seen a lot of tools that's specialized for payload and firmware auditing on satellites. They can use generalized tools like Gerda, and there's signal analysis as well. So I wanted to cover a couple of useful tools when you're trying to analyze the communications that's being transmitted from a satellite. So I'll just go over the categories I mentioned before and note a couple of tools that are useful for each. So in terms of decoders for various formats, SatNogs is pretty handy. It's essentially a scalable implementation for satellite ground stations. So if you're dealing with anything that involves a ground station communication, I would recommend looking into that. There's also new radio, very handy, especially because there's specialized plugins you can use with the platform, such as the GR Satellites module, which is specifically designed for satellite signal analysis using software-defined radios. If you're using the SDR Sharp RT software-defined radio, I would recommend getting their software suite, which allows you to monitor and analyze satellite signals in real time. And you can also use more general purpose software-defined radio-based analysis tools like Universal Radio Hacker, which includes demodulation, decoding, and analysis of various satellite communication signals. For analyzing packets and telemetry frames, I would recommend running General HackStump. It's a simple tool. Most people will usually have it installed in their environment, which allows for a hexadecimal display of packet data, which is really handy for reverse engineering and inspection. There's an online initiative called the Open Satellite Project, which offers various software tools and open source programs you can install specifically for satellite communications analysis. And then lastly, for reverse engineering and communication analysis, I recommend getting SatDump. This is really great, especially if you have the RTL SDR. And it also allows for offline data processing. So let's say you get a file that's already like decrypted and you just want to see it and you don't want to get a live transmission, you can also run it for the tool. And it's just a general purpose satellite data processing suite. Gerda isn't specifically for satellite hacking, but it could be used for that purpose. This is when you have access to firmware, binary files, or communication software of any type that's been running on a satellite. You can use Gerda to look through it in order to reverse engineer what's going on. And lastly, Wireshark. We'll be using Wireshark for lesson 3 of this module, and it's really handy for analyzing packets from satellite communications and looking through the packet details and trying to extract data using what we have access to. So in order to find the frequency and the radio information, make sure you go through a procedure that gets the following list of data. It's pretty important that you have access to these before you make a communication call with a satellite. So the first thing is the transponder uplink and the downlink. Make sure you have the polarization type so you know which antenna to use, whether it's like right-hand circular polarized, vertical, and so forth. Make sure you know the bandwidth of the satellite communication system and the data rate. The frequency is a must-have. The downlink frequency, especially if you want to tune into the satellite. A little bit more detailed, but a Doppler shift does occur and it is a real phenomenon. So if you're cognizant of the quality of the satellite transmission and optimizing it, make sure you have a list of frequencies that are programmed into your handy-talkie. Knowing the modulation scheme of the satellite transmission, usually you see it in the satellite data sheet, is also very helpful, and latency and error correction. In terms of satellite tracking, we know that tracking satellites is very important for operating stable communications with it. Make sure you track the elevation angle, which is the angle between the observer horizon and the satellite. The azimuth angle, which is the incoming compass direction of the satellite. Doppler shift, orbital parameters and Keplerian elements. So this would be like inclination, right ascension of the ascending node, and so forth. And the RSSI, which is the received signal strength indicator. The great thing is you don't have to go about calculating and figuring these out all your own. There's already a free and online software out there that allows you to do this. I would recommend N2IO, OrbTrack, and Heavens Above just for online websites. You can get quick access to information. If you're looking, and also AMSAT online satellite path predictions resource is really handy. If you're looking for a more long-term application you can install, JSAT Track is really nice. I showed an image of it on the left, which provides you a lot of like information alongside visualizations of the ground track and the antenna gain radiation. And then Sat Hunter as well would be a nice application to install. Decoders. So a general guideline for satellite decoders, make sure it has the following functionalities. Firstly, you want to make sure it supports demodulation, which is extracting the baseband signal from the modulated carrier wave. Most decoders will have this. Also, make sure it has some kind of error correction built in. This allows for identifying and correcting errors in the received data using error correction codes it receives. And lastly, make sure it's able to decode protocols transmitted by a satellite by interpreting the formatted data according to the communication protocol. Good tools for this is SatDump, which allows for recording, live decoding, and processing of satellite communications and analysis. And the GR Satellites plugin for GNU Radio, which allows for telemetry decoding for amateur radio satellites. So let's talk a little bit about reverse engineering. Make sure when you're thinking of reverse engineering, we can think of it on different levels since it encompasses a lot of things. Firstly is the physical layer. And when you're thinking about the physical layer, the main goal of reverse engineering is converting waveforms into digital data. So any radio waveform that's transmitted or received by a satellite, you want to reverse engineer it in order to convert it to digital data that can be processed. So there's a couple of ways you can do this. There's digital modulation recognition, which uses AI tools to recognize the modulation type based on characteristics of the wave, such as amplitude, frequency, and phase. There's also transmission technique identification, which provides recognition capabilities for MIMO, which stands for multiple input, multiple output, and the direct sequence spread spectrum. A little bit more technical, but if your satellite target is using specific techniques, comes in handy. For the transport network and data link layers on the OSI model, there's a couple of convoluted ways you can do this. It's by analyzing packet data and block codes, but it is helpful for reverse engineering purposes. There's frame synchronization, which looks through, gets predefined synchronization patterns to obtain frame synchronization. So you can synchronize with the frame rate and the data rate. There's also channel code recognition, which is able to recognize and classify between linear and convolutional block codes. And then there's interleaver and scrambler reconstruction, which locates interleavers and scramblers. Scramblers are randomizers within packet data, and interleavers are randomization of value and positions of transmitted data. So like there's different randomization techniques for data that's being processed by a satellite. And in terms of application, session, and presentation layers, the main goal of this is accessing multimedia data, so videos, photos, audio, and so forth, by the communication links established by the satellite. And one way you could do this is using source and code identification, which uses techniques to investigate source encoders using using tools that allow for byte frequency distribution. Another thing I wanted to discuss was the vulnerabilities of satellite firmware. So satellite firmware is vulnerable to something called fuzzing. And fuzzing, what it means is tinkering with embedded software running on satellites to identify vulnerabilities. And this is typically conducted on the satellite payload data handling system, because that's the part of the satellite which handles any firmware or any updates to the firmware. And in order to do this, most modern satellite infrastructure requires making remote access. And the point of using a fuzzer is, what a fuzzer does is that it generates a bunch of inputs and test cases to run on the extracted satellite firmware. So it's like a comprehensive audit of all the functionalities and capabilities of the firmware source code, and it runs it through a bunch of inputs in order to find any errors or corruption within the code, or any unexpected behavior that runs through running a bunch of unit test cases. There's a bunch of different tools you can use. However, research in the past have used fuzzware to test satellite firmware images. And some general tips for this is implying input handling. So this could be telecommand handling, where the satellite receives commands and runs a function according to the command. Is you can imply a lot of these inputs by accessing the firmware source code or the ELF header. By accessing the firmware source code, you can see like the names of the methods being used, and from there make inferences about the functionality of the firmware and write tests accordingly, run it through a fuzzer, and look for unexpected behavior. And once you run a bunch of test cases, you'll start to see any bugs or any unexpected behavior which could reveal crashes and vulnerabilities of a satellite firmware image. Another tool alternative is the AFL++. So we covered a lot of the conceptual ideas behind making a satellite communication. I just wanted to mention a few examples of some scenarios that involve communication analysis of satellite signals. So I think the first and most obvious one would be a dish antenna setup, which uses a format called DVB, which stands for digital video broadcast. And this is usually used for a lot of consumer applications that want to get high rate access to data, which involve videos like TV, satellites. And the hardware for this isn't that much. In order to sniff a satellite broadcast that uses digital video broadcasting, you need a component called a LNB, which stands for a low noise block down converter. And typically, the general consensus is that larger satellite dishes can pick up more signals. So the larger your dish is, the more receptive of it is to radio signals. In terms of an interface, you do need a DVB tuner card, which allows for signals to be picked up by a computer. And what they do is they allow for satellite feeds to be saved into a hard disk, and they can be readily installed as a PCI card. So installing them into a computer shouldn't be that difficult. For feed hunting, make sure you get a feed hunting scanner that's able to scan the environment in order to turn streams of data into readable formats by the user, such as binary and ASCII files. And lastly, you need satellite fishing software, which allows you to download data offline for intercepting radio, video, and internet-based signals. Another example of satellite communication is APT interception and decoding. So APT stands for automatic picture transmission, and this is used by a lot of meteorological satellites like the NOAA meteorological satellite fleet. And in order to intercept and decode these signals, you need 4 core items. You need the antenna, and it needs to be able to be tuned to the 137 megahertz frequency to receive APT signals from NOAA satellites. NOAAs are the main ones you want to decode for weather images. The NOAA 15 ones, and the different satellites run on different frequencies, which I listed. And then you need software-defined radio hardware. You can use any SDR that's capable of reception on the 137 megahertz range. Some options include the LEM SDR, RTL SDR, and SDR Play. In terms of software that's going to be used in conjunction with a software-defined radio, make sure it can compensate for Doppler effect. Usually, most SDR platforms have this capability, and that the WFM mode is selected. Your bandwidth should be around 500 kilohertz. And lastly, you need APT decoder software. So once you capture the IQ and audio signals, you need to decode it using online tools such as the NOAA APT or WX2IMG. WX2IMG, I think, was retired, but there is a new version of it that is accessible. And lastly, there's amateur radio satellites. I would recommend the A091 FM, also known as the Fox 1B satellite. Amateur radio satellite communication reception is also known as bird hunting because amateur radio satellites in space are called birds in the community. And it's a pretty fun way to learn more about making communications and learning about the different communication details that make up an interception. So make sure if you're playing around with this one, you get the latest telemetry and past prediction readings from sites such as AMSAT and N2IO. This specific satellite has a downlink frequency of 145.960 megahertz, and it isn't impacted by Doppler effect as much, so you don't really need to account for it, although you can. And you can make this satellite communication using a handheld and an antenna. So when the satellite is within your line of sight during its passing period, you can obtain communication with it using a small directional antenna like the Yagi I mentioned, or a log periodic antenna. Make sure you point your antenna in the correct orientation as it moves, and these satellites pass about 5 to 6 times a day. And make sure another topic I want to touch upon is identifying the acquisition of signal. This is the position angle where the satellite initially appears above the horizon. The opposite is the loss of signal, which is the position angle where the satellite disappears from this horizon. So you want to make sure you start receiving signals when it passes the AOS, and then trace the path until you no longer can receive. Hello everyone, welcome to lesson 2 of module 3 of the Aerospace Cybersecurity Satellite Hacking course. In this lesson, we're going to be covering a wide range of tools and concepts. So get ready, we'll be analyzing satellite communications using 3 well-known tools, gpredict, satdump, and WX2IMG. So just a general lesson overview, since we're going to be covering a wide range of things. Firstly, we're going to be predicting satellite passes using a tool called gpredict. All these tools are free and open source, by the way, so you don't have to worry about downloading or paying for any of these tools. Then we're going to be decoding automatic picture transmissions from weather satellites to convert satellite communication transmissions to an image using WX2IMG. And then finally, we're going to be analyzing automatic picture transmissions using a tool called SatDub. So a general note of online tools for satellite tracking. So most of the time you want to use online sources for satellite tracking and path prediction, mostly because they're widely accessible and they're free to use and you don't have to download anything. I went over this in the previous module, but some of the recommended tools I would recommend, websites I would recommend visiting is n2io.com. Heavens Above gives you more instruction on how to orient your antenna, and OrbTrack. And this is to get general path prediction data and two-line element sets. So what is gPredict? So unlike the other online sources, gPredict is actually an application you download onto your computer that gives you more robust information about satellites. And it's an application for real-time orbit prediction and satellite tracking that gives you a lot more information than just a general online data source. Some of the features it includes is the ability to display positional data on graphs and plots. It can also predict passes and get information about each pass in many subsequent passes in the future, which is what, while most online sources are limited to just a few passes. And lastly, it offers complete modularity and customization, which is often lacking in online tools. So in order to install gPredict, you need to go to this website, and it'll depend on the operating system you use, but you will go to this page here. And if you're on Mac, you'll use Mac ports to install it. If you're on Windows, you'll go to a source page. I can walk you through what I would do. So I would, if I were on Windows, I would go on SourceForge, and then I would download the tar file, and then I would walk through the instructions shown in the download page. So another tool I would recommend you use is a site called DishPointer. DishPointer gives you specific information of how you should configure your satellite dish antenna if you have one, and it'll give you elevation information, azimuth for the true and magnetic fields, and how you should rotate the LNB skew on your satellite dish if your satellite dish has one. So we can visit the website by going to dishpointer.com. I already have it open. And then you could scroll down to the satellite you want to analyze. Let me see. I can just pick, just for an example, I'll pick Cirrus FM6, and then I can paste in the latitude and longitude. Click search. Here you go. So you can see it'll give you the elevation angle of how to orient your satellite dish antenna, the azimuth, and how you should orient it using this line here. And you can also enable show obstacle line of sight to show any like relevant obstacles that might be in the way, and that might attenuate any of the signal. In terms of antenna and dish setup for satellite communications, some options include a quadrifilar helix antenna. The Nulik GOES weather satellite mesh antennas are really good if you want weather images from the GOES satellites. The double cross dipole and a generic satellite dish also work as well. For setting up your dish for retrieving communications, you can look at the details included in the website DishPointer, where it will show you the elevation, the azimuth, and the LNB skew. And in this case, you would orient the satellite dish 43.9 degrees, which is the elevation angle above the horizon. So it'd be like 43.9 degrees. And then you would rotate the dish 190 to 200 degrees. So that would be 10 to 20 degrees west of due south. So it would be south, and then you would do 10 to 20 degrees west of it. And then if applicable, if your satellite dish has an LMB, you would just rotate the LMB option to be 18.5 degrees. So let's predict a pass using gpredict. When you open up gpredict, you should be presented with a display that looks like the following. And in order to configure this, we need to click File, Edit, Update TLE data from network. This is going to import all the TLE data so your system is up to date. And then one more thing is Update transponder data. This is going to get the most up-to-date transponder information. Cool. So once that is finished, we're going to configure our NOAA satellite constellation. So click File, New Module, and the module name is going to be NOAA. And if you search for NOAA in the satellite section, we want 15, 18, and 19. So I'm going to click 15, 18, and 19 and click this arrow here. Once you have that selected, click OK. Cool, so once you have that, you should go to the NOAA tab and you should be presented with this display. Whenever you select the satellite, it will give you information about it. So, for example, I have the NOAA 15 satellite currently selected, and I'll go over the important details in here. So azimuth is a horizontal angle measured clockwise from a reference direction. We have elevation, which is the vertical angle above a specified plane. We have the range rate, which is the rate of change of a distance between an observer and a target. We have SSP lock, which stands for spacecraft state vector location. It is the position and velocity of a spacecraft in orbit. We have footprint, which is the area on the Earth's surface which is covered by the satellite. We have Doppler at 1000 meters, which is the Doppler effect measured at 1000 meters, and it is in hertz. And lastly, we have the orbit phase, which is the position of a satellite within its orbital path at a specific point in time. In order to get future pass information about a satellite, right-click on a satellite, and then click Future Passes. And this will give you the future pass information and the duration of the path and other various details. In terms of recording transmissions from satellites, I would recommend using a software-defined radio software like GQRX to record transmissions. Unfortunately, we'll be using SatDump, and GQRX is slightly beyond the scope of this course, but if you were to get it installed, make sure you, or any general software-defined radio software installed, make sure you select the correct frequency based off of the NOAA satellite you are observing. So the NOAA 15 downlink is the 137.62 megahertz. NOAA 18, NOAA 19 are slightly different, so make sure you note those. And for the receiver options, for GQRX, it's pretty straightforward, but you'll need to configure it for other software-defined radio softwares. Make sure the filter width is wide. You set the mode to WFM, mono mode. The frequency bar is 0 kilohertz. The reference level is 0 decibels. Make sure the decibel range is 104. Make sure peak detect is clicked, and the low noise amplifier gain is 20 decibels to get optimal results. So let's talk a little bit about APT decoding. So NOAA satellites use a protocol called automatic picture transmission in order to transmit pictures of weather and remote sensing data to the ground user. And this is structured like a broadcast transmission, and it contains two channels. It contains a telemetry channel within its packet frame, and it also contains a synchronization channel. So on here, you can see it has a telemetry frame, telemetry A, and then telemetry frame B, and it also has synchronization to its packet frame as well. This uses horizontal scan lines, and each line is 280 pixels. The image contained within the packet via APT is 909 pixels, and telemetry takes up 100 1171 pixels, and synchronization as well. The transmissions of lines follows a baud rate, which is the rate at which the data is transmitted, of 2 per second, or this would be 4160 baud. So let's talk about WX to IMG. WX to IMG is a weather satellite signal to image decoder. This is used to display real-time images from weather satellites. It's completely automated recording and decodings. It transforms images into map projections. It allows for overlaying maps using adjustable colors. It allows for many temperature and sensor calibrations and command line operations for embedded devices. So we're going to be decoding some automatic picture signals using WX to IMG in this lab. In order to get started, you need to download the raw file. I included it in this GitHub repository. So you go here, and then you can click the download button in order to download the raw file onto your computer. I'm going to download it to my desktop. Looks like I already have it. So make sure you download that. And once you have it downloaded, we're going to be using an online accessible tool that does the same thing as WX to IMG, but it's more straightforward. So this is a generic automatic picture transmission decoder, just like WX to IMG. So here I can click choose file, and then I would select NOAA recording, and then click absolute value, and then click decode. There we go. So if you scroll down, you can see that it was able to successfully decode the automatic transmission files to get these weather remote sensing images here. And you can play around the settings. You can look at different channels like channel A and B, and set like the synchronization. There's a lot of different settings you can play with in order to get different results. So the last tool we'll be covering in this class is SetDump. SetDump is a really robust tool specifically for radio frequency analysis of satellites, and enables us to process the data and transmissions from satellites using a SDR. It's compatible with most types of SDRs. So you can use like a Lime SDR, an RTL SDR, a HAC RF, and when you plug it into your computer, SetDump will automatically detect your software-defined radio and configure it with the software. This is a very robust suite. It enables decoding and processing of data from over 90 different satellites. It supports live decoding of links such as automatic picture transmission, high-rate picture transmission, and so forth. It allows for image and data decoding of NOAA weather satellite constellations and various other satellite constellations. Enables you to overlay the satellite image over a custom map and include layering with other instruments and details in order to get more information. So in this final lab, we will be using SetDump for automatic picture transmission decoding. This will be used to explain the data processing capabilities of SatDump for specifically processing APT transmissions. In order to get started with this lab, you need to make sure you have SatDump installed on your computer. In order to do so, go to this link here, satdump.org/download, and make sure you follow the download instructions for your specific operating system. Once you have that complete, make sure you download the automatic picture transmission raw file if you haven't already. When you open up SatDump, you should be presented with this display here. Make sure you have offline processing selected, and in the input bar for search pipeline, search up NOAA and click the NOAA APT, since we're going to be decoding APT features. Then make sure you select for input file the no recording you downloaded from the GitHub repository by clicking this button. And for the output directory, create a random folder, and you can name it anything. I named it SAT-dump output, and I selected it from this button. And this should be the configuration. Under sample rate, change it from 1 megabits per second to 11.0.25 ksp's, and then click start. This will decode our APT transmissions, and then we can go to viewer and see our decoded transmissions. So in order to see a little bit better, you can apply various different features. I would apply, just play around with these values. Equalize tends to help out a little bit. And you can look for various channels. You can change RGB composites and map out projections if you wanted to using SAT-dump. The purpose of this was mainly just to decode. Once decoding is done, you can go to your output folder and see the output images and other information. So you can see here, we can see the decoded weather images from the NOAA APT transmission. So that was a general overview of how to use SAT-dump in order to decode pictures from weather satellite transmissions. That was a very brief overview of some of the capabilities of SAT-dump. SAT-dump is capable of so much more. It has a lot of different features and supports a lot more satellites. So if you're interested in analyzing communication links of satellites, I highly recommend starting off with SAT-dump, especially if you have an RTL SDR in handy. With that being said, thank you so much for tuning into this lesson. In the next lesson, we'll be diving a little bit deeper into decoding and reverse engineering. Hello, everyone. Welcome to Lesson 3 of Module 3 of the Aerospace Cybersecurity Satellite Hacking course. In this lesson, we will be covering decoding communications from satellite transmissions using Wireshark and New Radio. So just a brief overview of what we're going to be covering in this lesson. Firstly, we're going to be going over DVB. DVB is a very specific protocol used for video transmissions, and it stands for digital video broadcast. So we're going to be covering a very conceptual overview of it, because all the examples and labs we'll be covering in this lesson will be revolving around the DVB examples and transmissions. And we'll also go over vulnerabilities that are intrinsic to that specific protocol. Next, we will be extracting DVB-S2 information and how you can configure that using a new radio tool. And then lastly, we'll be looking through DVB transmissions and packet traces using Wireshark and noting what kind of inferences and details we can extract, and some packet analysis and packet dissection techniques as well. So what is DVB? DVB stands for Digital Video Broadcast, and it is responsible for the transmission of audio and video format using data connections. It has a very specific format for satellite communications, and it is denoted by DVB-S. You might see other formats of DVB that are terrestrially based, so you might see like DVB-T. Usually you want to disregard that if you're focusing on satellites. So the way you know that it's specific to satellites is with a -S at the end of it. And there's a more modern version of the DVB-S protocol, which is DVB-S2, and it's 30% more efficient because of the way it's formatted, but they're both the same protocol. DVB uses a coded orthogonal frequency division multiplexing modulation. You can denote that as OFDM, and it's a pretty fancy way of modulating digital data. We'll cover that in the slides to come. So what is a DVB transponder? So every DVB providing satellite has multiple transponders on board, and they're usually operating on different frequencies. Most of the time, DVB-S transponders operate on the C and Ku bands, but some of them operate on Ka bands as well. So let's talk a little bit about the DVB-S transport stream. So this is a digital format used for transmitting audio, video, and other data using satellite channels. And this stream multiplexes, meaning that it takes in various different formats, such as like movies, it takes in audio, video, and data, newscast, sports programs, and then it feeds it through a multiplexer in order to send it through a single stream. So what a multiplexer does is it takes multiple values and it transmits all those values, combines them together into a single transport stream in order to make things efficient. So this transport stream is a continuous stream of packets carrying dense information, and each packet within this transport stream has a fixed size. So let's do a packet breakdown of a typical DVB transmission. The MPEG format is a standard that's widely used for DVB-specific transmissions. And if you look at the MPEG-2 transport stream and the packet breakdown of it, you can see that it has a synchronization byte that is denoted by 0x47. It consists of 8 bits. And then after that, you have a transport error indicator, which indicates whether or not was an error in the transport of the packet. It also has a payload unit start indicator, which alerts the receiver when to start reading the packet. It has a transport priority bit. It has a PID, which stands for packet identifier, which is 13 bits long. It has a transport scrambling control system, which consists of 2 bits, and it is responsible for scrambling with a key the data contents of the packet. It has an adaptation field control, which is 2 bits, and then lastly, it has a continuity counter at the end of the packet, which is a sequence number of the payload, which indicates since in a transport stream, you'll have multiple packets and multiple payloads. It indicates what number it is within the sequence. So if it's the second packet, it'll be like the number 2. So where is DVB typically used? DVB is typically used for live streaming services, so you might see it on news broadcasts. You can also see it on sports streams and military surveillance as well. So SAT modem is a pretty important topic to cover upon since we're talking about DVB. And it is a communication device on satellites to encode and decode data for transmission. And modems in satellites typically have an intermittent frequency output, which is modulated to the L-band. And the modulated transmission contains signal states to send data. Once the signal is received by a ground station or an antenna on the ground, it is down-converted using a low-noise block-down converter. So let's talk about the IP satellite link, and this is moderated by SAT modem. This is a one-way communication channel for home internet access. And this is typically the first method for satellites to obtain internet connection. And the way this works is there are one-way SAT modems, and it uses the DVB IP protocol. And the uplink is a low-speed connection to the satellite provider, or it's tunneled through the internet. So in here, you can have the uplink that's tunneled through the internet, and then the internet service provider has a uplink to the satellite, and then the satellite processes it through sat modem, and then it sends back data to the downlink to provide internet to the client when the client requests information. Hackers can exploit this IP satellite link by sniffing the downlink communications. So when a client asks for internet services from the ISP, and the ISP provides data via the uplink, hackers can eavesdrop and sniff data that is being sent down to the downlink from the satellite to the client that is using a DVB IP protocol in order to decode and get specific information. Astromodem is another way for a client to get internet access via a DVB. This Astromodem is a two-way modem to obtain internet via a satellite-based return channel. And it uses a uplink that's a satellite which relies on the DVB-RCS protocol. And the DVB-RCS protocol enables for bidirectional communication. And in this case, people who want to eavesdrop or listen in on communications can sniff the uplink and the downlink. So you can see here the client requests, in this case, it will request directly to the satellite and no traffic is funneled through the internet. So it has an uplink and bidirectional downlink to the satellite. And then the satellite asks for information from the internet service provider. Internet service provider gets access to the internet, sends back data via the uplink to the satellite, and the satellite gets the data, sends it to the client via the downlink. So any of these links can be sniffed. So how do you sniff for DVB communications? So like I mentioned before, DVB is a pretty open protocol, so anyone can sniff for these packets since it's often unencrypted. And the general overview of the tools you'll need to unencrypt and decode DVB communications is a satellite antenna that's tuned to the frequency. You'll need an LMB. You also need a DVB PCI card for DVB-S or DVB-S2, which makes it really easy so you can plug it directly into a computer. And then you'll need a DVB analyzer. Usually there's DVB analyzers in the form of software, which you can download. And then New Radio, which is a generic radio frequency analysis tool, but it's also really helpful for decoding signals. And then lastly, Wireshark, in order to look through packets of data that are being streamed through the DVB and then dissecting those packets to get relevant information. So if you want to set up a DVB communication sniffing setup, you'll need to set up multiple tools in order to do so. Firstly, you'll need to tune the DVB card, and then you'll have to find the packet identifier of a DVB packet using a tool called DVB Snoop, which is a command line interface tool specifically for looking over DVB packets. Then you'll need to initiate an Ethernet interface using the packet identifier found using DVB Snoop. And lastly, using that Ethernet interface with a DVB card, you can capture direct DVB packets using Wireshark. So a brief overview of how you tune a DVB card. You first have to set the transponder parameters in the configuration file. So most DVB cards you plug into your computer will have some form of configuration file. You'll need to access that, and you'll need to create a file called channels.conf. And then you'll need to find the transponder parameters of the specific satellite. You can use websites such as fastfinder.com, which will list transponders, and then you'll need to copy over the ASCII text in that list and then paste it into your configuration file. And once you have that done, you can run SAP with the channel configuration and the transponder. So a command line tool would look like this. Once you have those configurations of the transponder of the satellite, of the DVB satellite you want to snoop into your DVB card, you can run commands like DVB scan in order to find the packet identifier. So this is using DVB snoop, and this is scanning for valid packet identifiers. And lastly, you'll need to initiate an Ethernet interface before you can start sniffing in on communications. The way you can do this is through a DVB tool called DVBnet. And you can run a command called dvmetnet-a, and then enter the adapter number and then the packet identifier that was found in the previous step. And then you can find the Ethernet interface by running ifconfig -dvb0 underscore the interface number, and then type in up. And you should get a result that looks like this, where your Ethernet interface is initiated for packet capture. So in order to capture packets, you can use Wireshark or T-Shark, which is a Wireshark variant that's native to the command line tool. And it's just a generic packet capture in this case, where you run T-Shark, and then you enter the DVB Ethernet interface, and you can initiate a packet capture session. So now we've covered how you would conceptually capture packets for DVB satellites. What are some common threats to these satellites? So the main threat to digital video broadcast satellites come in the form of specialized network attacks. So the three most common are DNS spoofing, TCP hijacking, and attacking GRE packets. So DNS spoofing is when there is a misconfigured DNS entry to point to another IP address, causing a domain name server to become spoofed and the receiver session to become confused. There's also TCP hijacking, where a hacker can initiate a TCP session takeover. And lastly, an attacker can attack for GRE packets, which exploits an intrinsic protocol utilized by DVB satellites called GRE in order to get unauthorized access. So let's do a lab using the DVB-S2 protocol. DVB-S2 is like a more modern protocol of the DVB-S system. And in order to do this, you'll need to get info and pass it through new radio. We're going to be dissecting communications using Wireshark. And then we're going to be extracting information and then auditing for common IP attacks. So this is a highly optional lab, since I'm assuming many students here are going to be using their own computers and their own operating systems. So feel free to try this out on your own in your free time. It might require some setup on your own, but I will cover how you would do it. So in this lab, you'll be using GR-DVB-S2RX, which is a specific DVB-S2 plugin for new radio to interpret DVB-S2 signals. So new radio is generic radio frequency and signals intelligence software in order to decode and demodulate signal transmissions. And you can install specific plugins that come with pre-configurations for new radio, so you don't have to do all the work yourself. And this is an example of one for DVB-S2. So a little bit about the plugin. It's a DVB-S2 receiver extension, And it comes with DVB-S2 TX and RX, so receiver and transmitter interfaces with custom configured files. It has flexible source and sync plugins, and it also has an available visual interface as an option. So in order to do this, I would highly recommend installing a tool called Docker. Docker allows you to utilize applications in lightweight portable containers, so you don't have to worry about development environments when you're installing a new tool. In order to install Docker, you can visit this link. Once you have Docker installed, here are the instructional documents for the plugin. And you can scroll down on this page and you'll be led to this tool. And you can just clone the repository, seeding to the folder, and then run these commands, and it should get you running with the plugin. So I want to give a little bit of a conceptual overview of the MPEG format. So whenever you have a transport stream, like with DVB, like I mentioned before, you're going to have specific packets, and that's the packet format that is widely adhered to by DVB-S2 transmissions is the MPEG format. And why it's used is because it's a very popular compression algorithm used for digital audio and video formats. And when you're using these plugins, you'll likely encounter TX and RX, which is the transmitting and receiving, respectively, side of a communication system. You'll also be met with a word called the transport stream. A transport stream is a digital container format for the transmission of multimedia data. Another key term you should know is the IQ stream. An IQ stream is a representation of a complex signal. Complex, like a complex number, includes both real and complex components. And then in the tool, DVB-S2-TX, which stands for transmitter, sends a signal to the DVB-S2-RX, which is the receiving end, which processes it and shows the results in a standard output or in a visual display format. So if you want to use this tool, you'll have to interface with the application. So a quick example that they include in their documentation, which is this usage page here, is to download an example MPEG transport stream. So you can do that if you're on a Windows operating system. You can run wget and then type in this URL and then put the output -o into example.ts. This is a transport stream file. If you're on OS X or Linux, you can run the curl command and set -o for output, the example name, the name of the output, and then the URL here. And you can set up a default transport stream system, so where the transmitter reads the MPEG transport stream file using standard input and then transmits the results into an IQ stream into the receiver application. So the way you do that is run cat example.ts, which contains the transport stream, and then putting two pipes and running the commands here. All this information is contained within the website, so if you have any issues troubleshooting, I would resort to the example commands in the website. So here is a preview of the GUI, which is a visual output of the stream. And the way you can set up the GUI system is to run the receiver command, set the source and the frequency, and then put this --GUI at the end of it, and you should be met up with a visual preview. Cool. So now that we know how to use New Radio, let's go over dissecting communications with Wireshark. In this lab, we will be using Wireshark, which is a widely used network tool to decode and understand DVB-S2 packets. So what is Wireshark? Wireshark is an open source network protocol analyzer. It has a lot of robust features, such as packet analysis. It also includes real-time monitoring and display filtering and search features. You can install Wireshark by going to this link here, and you'll need to expand the latest stable release and click the operating system that you have. Once you have Wireshark installed, you'll need to install an example PCAP file, including DVP traces. A PCAP file is a network trace file containing packets recorded during a session. So this example PCAP file includes DVB transmissions. So you can click the download raw file here. And once you have that done, we can get started with Wireshark. When you open up Wireshark, you should be presented with a display that looks like the following. And we're going to open up, go to File, Open, Quick Access, or like wherever you download the PCAP file noted earlier, the DVS S2 example, and click Open. This is going to show us a network capture of the DVB S2 UDP stream. In order to configure it into Wireshark, it's not pre-configured by default, so you'll need to go to Analyze, go under Enabled Protocols, and we're going to search DVB, and make sure that this checkbox next to DVB S2 UDP is selected. So we're going to click OK. Once that is selected, we can filter for DVB streams because we have a lot of other things other than DVB S2 by searching for DVB S2 underscore BB. We get the baseband packets. And by looking for these, and we can extract information under the packet protocol in order to get permanent DVP packet information. That'll go over a little bit later. So we get the stream input, the user packet length, DFL synchronization bit, checksum, and the user data, which you can decode and reverse engineer. So now that we analyzed a sample packet capture, what is a DVB S2 baseband frame? So we saw that in our packet dissection, we saw a little tab in Wireshark that let us expand the baseband frame. And it shows the output of the DVB S2 satellite receiving equipment. And this protocol depends on the UDP protocol, which stands for User Datagram Protocol for transport. This is a lightweight connectionless protocol in the IP suite. And the baseband payload is GSE and MPE. GSE stands for Generic Stream Encapsulation, which is a protocol for packetized data streams used in satellite transmissions. And MPE stands for Multi-Protocol Encapsulation, which is a protocol for IP data over DVB networks. So Wireshark uses a heuristic dissector for DVB S2 baseband over UDP, and a heuristic dissector reads packets to determine if it's the right dissector. So this dissector in Wireshark just pre-reads every single packet and determines if it meets the criteria to be the dissector, meaning it checks if it uses UDP for transport, and the baseband payload is generic stream encapsulated and uses multi-protocol encapsulation. So, like I showed you before, this is the packet structure of DVB S2. I want to note the adaption mode header. The adaption mode header, which is up here, contains information about the specific adaption mode, such as the modulation scheme of DVB, the error correction coding, and so forth. The DVB S2 baseband frame section contains user data, control information, and signaling data, such as synchronization. So you can see the synchronization bytes, data, and other pilot symbols, and checksum. You can read more information about it on this web archive PDF below. I also wanted to note some protocol documentation. If you're interested in learning more about the baseband protocol and the GSE protocol for Wireshark, Wireshark has extensive documentations on those, so I would recommend checking out their pages. And they describe the field names and give a very rough description and the types and the version numbers as well. That being said, thank you so much for attending this lesson. And the last lesson will be looking a little bit more into reverse engineering, so get excited. Hi everyone, welcome to the final lesson of Module 3 of the Aerospace Cybersecurity Satellite Hacking course. In this lesson, we will be going over decoding satellite communications using a live software program called SatNogs and doing a reverse engineering CTF to learn a little bit more about how you would go about reverse engineering communications sent from a downlink of an arbitrary satellite. Okay, so let's start off by demonstrating SatNogs. SatNogs is an open source global network of satellite ground station. SatNogs has a robust set of capabilities. It is able to display satellite observation data within its network section. It also has a database with a complementary API for obtaining live satellite telemetry information. It also has a client feature for operating ground station controls, especially amongst embedded applications. So one of the core features of SatNogs is its dashboard suite. In its dashboard suite, it contains time series telemetry data for a specific satellite. So on its main page, you can scroll through a list of satellites, and then you can select one to see its radio messages and other frames and information that are being sent down. It also contains packets and beacon messages, status messages, and specific data about satellite subsystems. So a little bit of an overview of the vocabulary that's used within the SatNogs pages. We have a digipeater. So a lot of SatNogs satellites in their listings are AMSATs. So they're amateur radio satellites sent by amateur radio operators. And amongst these satellites, you see a pervading a component called the digipeater. A digipeater is an amateur radio digital repeater that receives, processes, and retransmits digital data. So you can think of it kind of like a transponder, but more amateur radio specific in those terms. There's also VHF TRX, which is a transceiver for very high frequency. Ultra high frequency is also used very commonly. You'll also see things in the listings called APRS messages. APRS is pretty common for emergency services, especially in amateur radio, but satellites have them as well. And APR messages are short digital messages sent using amateur radio via a system called APRS. You'll also see various subsystem telemetry. A common one is the PSU, which is the data for the power supply unit. You'll see payloads and indicators like BDS. BDS stands for the Beidou Navigation Satellite System data. It's a common navigation satellite system you can attain from satellites. And lastly, you'll have a lot of OBC telemetry, which is the onboard computer data. So let's go about gathering communications for a specific satellite using SatNogs. In this lab, we're going to be using the SatNogs dashboard feature to obtain relevant communications from the BDSat-2 satellite. The BDSat-2 is I think an amateur radio satellite that was deployed into orbit. It's a CubeSat, it's fairly small, and SatNogs lists it as one of their satellites. So in order to do this, you need to visit the dashboard. So this is the specific link for the BDSat. You can also go to the dashboard and then search for the BDSat. So let me go visit this link. And once it loads, you can get all the relevant information about the specific satellite. You can see here it transmitted a message. So this uses a digipeater that operates both on very high frequency and ultra high frequency. Here you can see the last user that accessed the digital repeater on the satellite and their call sign. Call signs are identifiers for amateur radio operators. So once you get a license and a certification for amateur radio, you get a identifier, which is typically a 6-letter code, although sometimes shorter if you're more professional, indicating your ID. And you can see who last accessed the very high frequency one and the ultra high frequency one. You can also retrieve telemetry frames, so you can see the amount of frames that were beaconed out from the satellite, the timing of the last frame, so it was about an hour ago, and who the frame was received by. So I think it's some arbitrary ground station because it says ESL lab. And you can see which ground stations have obtained the most frames or messages from this specific satellite by looking through this leaderboard here. So these are all ground stations who are observing the satellite. Here we have this listing of APRS messages. So it's under ASCII telemetry. ASCII is like a text-based format. So whenever you have an ASCII, it's an indicator of a message. So it sends you the time, the APRS message, which is a long list of characters here. You can use an APRS decoder to decode the information. So for example, for this one, it says PSU. So I would just make the inference that this is a message in regards to the power supply unit. Then we have the onboard computer and so forth. And you can see which ground station observed it, which station, and the source. Here, if we scroll down, we get the power supply unit telemetry. So this gives you the battery levels. Go into view mode here. You can get the ground WDT. You can also set filters as well. You can get the uptime, the current being sent through, different channels. Power supply unit has different channels, so you can see whether they are on or off. You get the current over time, the power supply unit temperature, payload temperatures, and you get capacitor bank time. So a lot of different subsystem information, onboard computer stuff. So you get solar temperatures from here, the uptime of the onboard computer. So this is also generally useful for the reconnaissance phase of when you're doing like OSINT research and wanted to do more research about a specific satellite. Sources, if it's a smaller grade satellite, sources such as SATNOGs might be really helpful in order to get subsystem specific information. So you get both communications-based information about the ultra-high frequency transceiver and the very high frequency transmitter, as well as battery levels and terminal temperatures. See signal frequency of the radio, payload temperature, solar temperature. Awesome. So let's move on to reverse engineering satellite data. So reverse engineering encapsulates a lot of things. It has to do with hardware inspection and open source intelligence. Understanding the hardware that operates the satellite is really important, and the communications utilized by the hardware. There's also reconnaissance and monitoring involved, and understanding the communication protocol utilized by the communication subsystems of the satellite in order to contact ground-based stations. You also need to understand signal demodulation in order to demodulate the signal sent down from the downlink of the satellite, so you can interpret the signal and make inferences. There's also frame decoding involved. Once you're able to understand the protocol and demodulate a signal, you need to understand what frame protocol it adheres to, so you can decode it further and actually retrieve digital data from it. Packet demuxing, file assembly, these are all just like frame decoding terms. And then packet analysis as well, if you're dealing with network inspection. I would recommend using a resource called Go Satellite Hunt. The developer who made it He goes really deep into reverse engineering satellite data, especially with the GOES weather satellite. So I would recommend checking out his work. He covers, I think, packet demuxing, file assembly, and signal demodulation really well and goes really in depth onto techniques. We'll be covering the overviews of reverse engineering. We won't be diving really deep, but if you really want a thorough overview, I would check out the resource. So in terms of communications, satellites use various communication equipment for transmissions, like we talked about. So it typically uses a transponder, which receives signals in one frequency band, amplifies them, and then retransmits them in another frequency. The digipeater, which is the amateur radio digital communication relay in space. There's RX and TX terms, which are the receiver and transmitter components, respectively, of a communication system. There's also frequency converters. These shift frequency of a signal from one band to another. So let's say like you want to shift the frequency from like 2 hertz to 3 hertz. That would be a frequency converter. And then there's a telemetry tracking and control subsystem, which moderates communication between a satellite and ground station. So in terms of monitoring and listening to communications, you need to make sure you find the right communication configuration for obtaining signal, as with all satellites. So in order to make sure you have the right information, make sure you do research on getting the frequency. So get the band identifier and the frequency number for both the uplink and the downlink using open source intelligence. Also employ OSINT to get modulation schemes. These are specific modulation techniques and error correcting codes for decoding. You also need to know the bandwidth in order to calibrate your software-defined radio. So you need to get the bandwidth and other signal details by looking through the datasheet of the transponder or other like transmitters. You also need to get orbital parameters. So this is fairly easy. You can use something like gpredict or N2IO to get the orbital configuration and Keplerian elements. And lastly, you need to understand the antenna systems. So make sure you gather that information using OSINT. Once you have general communication information about a satellite, you need to go about understanding satellite protocols and which protocol the satellite you're trying to eavesdrop is utilizing. So there are many protocol variants for satellite packet transmissions. If you want to listen into CubeSats, which are fairly easy, especially for beginning out, CubeSats typically have a standardized protocol called the CubeSat Space Protocol. There's also the CCSDS, which is widely standardized and pretty popular, which is also denoted as the Space Packet Protocol. Some weather satellites use automatic picture transmissions, like we saw with the NOAA satellites. Digital video broadcast, DVB-S, which is a satellite-specific system for internationally recognized like internet entertainment video or sports video. Some protocols use controller area network, especially internal within the satellite. So if you want to retrieve information that's hardware or subsystem specific, it might have to deal with the controller area network. And if you're trying to investigate more niche amateur radio satellites, AX.25 is a common packet protocol for that. So once you have all the hardware set up and you have all the information to tune into a satellite, you need to interpret the signal you retrieve from the satellite using a technique called demodulation. This is inspecting the modulated carrier wave transmitted from the satellite to recover the original digital data. And in order to do this, you need to understand the carrier wave characteristics, which is often listed in the datasheet of the satellite. This can include the signal-to-noise ratio, synchronization, the modulation index, phase and amplitude of the wave, and other information. Also listed within the datasheets are modulation techniques. So you need to figure out which method it's using. So whether it's like amplitude modulation, frequency modulation, and so forth. And understand the error correction modalities. So this is for detecting and correcting errors that may have occurred during signal transmissions. And two of the most common are the Reed-Solomon, which corrects errors in blocks of data, and the CRC, which Cyclical redundancy checking is a checksum that helps detect errors. It's a pretty generic packet error correction format. So once you're able to demodulate signal, you need to understand frame decoding, because once you have the digital data, you need to understand how the frames are structured to interpret that data. So frames are typically split into 3 sections. You have the header, the payload, and error checking codes. The header contains metadata necessary for decoding. So this will include frame synchronization markers, the length of the frame, and other control information. There's also the payload involved, which has information transmitted using the satellite signal. So the payload data structure depends on the satellite system's protocol. And lastly, at the tail of the frame, you'll have error checking codes, which include correcting codes in the received frames. Let's talk about packet demuxing. Packet demuxing refers to the process of splitting and categorizing packet streams based on configurations. So there's multiple ways. It's a pretty more in-depth reverse engineering technique, but also is worth covering. So there's de-randomizing frames, which is reversing randomization to get original data. Sometimes packets of data are configured in such a way that you can't read it sequentially. There might be packets out of sequence. So this reverses the randomization in order to get to the original data. And typically the technique used to get this is something called polynomial generator strings that are used for generating CRC codes. There's also virtual channel demuxing, which are packets and logical communication paths separated based on identifiers in header. And then there's the Reed-Solomon error correction and FEC. FEC is good for data error correction, and the Reed-Solomon is good for optimizing data with low signal-to-noise ratios. So now let's talk about file assembly. This is the process of aggregating and decompressing packets. So when you're employing file assembly, you need to pay attention to the decompression algorithm. So satellite transmissions often involve the compression of data to reduce bandwidth usage and improve transmission efficiency. So in order to get the original data from the decompressed format, a decompression algorithm is used to reverse the compression process. There's also things called continuation flags. These are used in scenarios where data is split into multiple frames, and continuation flags help proper assembly of the data at the receiving end. So whenever there's like a long stream of data a satellite wants to transmit, it typically has to split the data into the specified and standardized packet length. But in order for the receiver to put all those packets together so the data is interpretable, it needs to have these continuation flags at the end of each packet. So it knows how to take the truncated packets and then combine them all together again in order to get the original data. All right, so just a general overview. In terms of packet analysis, you need to understand the structure, content, and characteristics of the packet you are analyzing. So part of this is having a good understanding of the protocol. There's typically, if it's using a widely standardized protocol like the CCSDS space packets, there are going to be rules and conventions for each packet, and there will be outlined like images like here to the right in order to help you with the decoding process. Packets also have flags, which are specific bits or markers like indicators within a packet's header, so inspecting the front of the packet in order to analyze the metadata included in it. And once you understand the packets, you'll use the metadata included in the header of the packet to inform your decoding process, which is where you extract and interpret data within the packet. And then lastly, understanding commonly used error correction and detection mechanisms for the packet formats, and having a good understanding of sequence polynomials and shifting. So a good application of this is interpreting CCSDS packets. I would recommend you check out this website I linked here. Since this is a widely used protocol, it's good to go over, and this website is really great at describing the breakdown. So you can see in the structure, we have the bytes, and we have the prime header, CCSDS also includes a secondary header, and then the actual data section. And it walks you through the procedure of unpacking a CCSDS telemetry packet. So you first unpack the primary header, the secondary header, the auxiliary header, and then go through each of the data points. So it's pretty sequential. Another thing to note is the size limit. So for this PICSAT CCSDS packet, it's 235 bytes, and that's how each one is split. And then the cool thing about this website is it breaks down each of the headers. So you'll get the name, the starting and the length of the bit, the type of data, and then a description of the data. You guys can read through this yourself, but I'll just go through the necessary parts. But yeah, in process ID, this informs the subprocesses associated with the packet. So you can see here, by reading the value, which is a number, you can see what process the satellite was running and what subsystem it may have been affiliated with. So that's really important. The secondary header contains just generic timing information and also telecommands. Yeah, and then packet categories, pretty important. So you get the name of it and then you decode it. So yeah, a lot of this is just understanding the framing structure. So once you get the data and have it decoded, you can just use references like this one to understand and get interpretable information of what this communication is doing. Okay. So a little bit about the CCSDS telemetry synchronization and channel codes. So these are techniques for synchronization, error detection, and correction in telemetry data, adhering to the CCSDS format. So, but it's also used within other satellite communication protocols and is worth noting. So it uses something called telemetry synchronization, which are markers within the telemetry data stream to aid receivers in identifying the start of telemetry frames or packets. So essentially it places markers in the data stream in order to indicate this is the start of the telemetry data, and then you can build off of that. And it also uses channel coding, which is utilized for error detection and error correction codes, such as cyclical redundancy checks and Reed-Solomon codes. So let's use our improved knowledge on CCSDS packet formats to run a example CTF. So Hackasat, I think 2 years ago, released a challenge called Can You Hear Me Now?, where you have to reverse engineer some CCSDS telemetry packets. And this is a great opportunity to apply what we learned. This is more of a reverse engineering type problem, less of a packet destructuring problem, but it gives you a good understanding of this. So if you want to run this yourself, I would recommend checking out previous CTFs and searching Can You Hear Me Now? But I will do a general run over of how you would solve this problem. So let's do an overview. So in this CTF, there's a company called launch.com, and they have a ground station that is streaming telemetry data from its Karnak 1.0 satellite in orbit using a TCP port. And they want you to implement a decoder using Python from given a definition in the XTCE schema format. That might sound complicated, but it's generally just a schema format in order to understand how you interpret packet information. So let's do a procedure overview before we dive in. So firstly, we'll need to connect to this telemetry service, which is a TCP port using Netcat. Netcat is a popular tool in order to get information from these ports. Then after we obtain the telemetry, we need to get a telemetry schema file within the specified XTCE spec format in order to figure out the structure of the packets so we can properly decode it. Next, we'll need to interpret files referring to manuals and documentations. And then lastly, we can reverse engineer the contents to get the flag. So the first step is using Netcat to connect to the challenge. This is a generic Netcat command. So you'll use a CLI tool for reading and writing data across a data network connection. So in the challenge, they mentioned that the port was 5032, and the website is here. You can try this out on your own. People have different operating systems, but you can try it out on your machine to get it working. There's also available GitHub repositories that host the files to run the CTF as well. So you run the nc command, hear me now, satellites above, .5032, and they will ask you for a ticket, and then you provide a ticket, and then it will give you a telemetry service running at a specific port. So connecting to this port using Netcat, so you run another Netcat command and you write like nc this port, you will get a bunch of binary that looks like the following. So in order to analyze this data, you will typically put it in a bin format. And once you do that, you'll be provided another file from the challenge, which is an XML file called telemetry.xtce, containing an outline on how the binary was encoded. So this is all encoded binary data from a telemetry service. So it's all telemetry data, but it's within binary, and we need to understand how to decode it using our understanding of packet structures. And this packet structure is outlined by this XML file. So let's look at the GitHub repository and see the XML file. So here, this is a schema file, and this outlines how a packet is supposed to be formatted. So you can see parameter type. So you can see here, it gives us the integer, so like the data type of the parameter, the name of the parameter, and whether or not it is signed. And you can see we have a lot of these parameters, which are just general rule sets for each frame to follow. This is interesting. So we have a parameter set, and these are the parameters used by the space packet primary header. We can see from here that it is using CCSDS. So you can see the packet frame inside the packet of the CCSDS packet. The version field will be 3 bits, will be a 3-bit integer. The ID will be like 11 bits, and so forth. You can get other like EPS information, payload information, so like payload power refers to payload power status. And you can see here, parameters used by flag gen. So in a CTF, we're trying to find a flag. So this is a good indicator. So here we have all these flag numbers. So we have flag 1, flag 2. So in order to solve this challenge, we'll need to figure out each of these flags and put them in order, because right now they're not in order. So we'll need to make our decoder to solve this challenge. Our decoder will have to go through each of these parameters in this parameter set, make sure to put them in order. So it goes 1, 2, 3, 4, 5, 6, and make sure it adheres to the type. This is a 7-bit integer. Typically, integers take up 8 bits of space, so it takes up 1 byte. It's pretty uncommon to have 7 bits. So in our decoder, we need to make sure we put everything in the 7-bit format that this flag parameter set adheres to. Yeah, so like I mentioned before, this parameter describes the flag makeup. Each line describes a character in the flag. The values are 7-bit encoded. ASCII characters generally take up 8 bits of space. So if we just viewed this in raw binary, we would not see an interpretable flag because ASCII characters are 8-bit, not 7-bit encoded, as the parameter type suggests. Okay. So let's understand packet header information. So like I mentioned before, the packet header contains a lot of metadata information. So by scanning through the schema file, we can view packet header definitions and corresponding encoding lengths. So near the top of the file, we found the CCSDS packet header information earlier. And then if you scroll further down, you can get the space packet parameter header encoding format. So let me show you guys one more time how you can do this. Let me scroll up. So here we go, we have the encoding format here. And then we have the header definitions here. Okay, so analyzing the flag content data that we find, we need to make sure we understand the value restrictions so we can parse each of these in our decoder. So by looking for the file, the flag contents, we can find the restriction criteria included in the telemetry packet header schema file. And we can see that the version, the CCSDS version, has to be 0 in order to be considered in the flag. The type has to be 0, the SecHD has to be 0, and the APID has to be 102. So let's find that in our file. So scroll down, typically it's near the bottom. Yeah, right here. So base container restriction criteria. And it says here comparison, the version has to be 0, type has to be 0, SecHD 0, APID 103. So the last step, I won't be showing you how to do this, but the solution is posted on GitHub for your own reference. You need to make the challenge asks you to make a custom parser using Python. So I'll give a general overview of how you would do this. Firstly, you need to loop for processing telemetry data. So the binary contains a bunch of bits that we need to decode. So we need to make a loop for processing the telemetry data. So this will read in the binary data, interpret the bits to extract information, adhering to the packet format here and here. So it needs to consider the version type, the APID, sequence flags, sequence counts, and the data links. And it needs to make sure that the flag APID is 102 and make sure to decode the characters to an 8-bit decoding because a 7-bit encoding, because that's what it was specified in here. Okay. And once you do that, it will give you the flag. So let's briefly go over the code because it does link it in the repository. And then we can move on to the last module. So if you go here, this is the Hackasat qualifier repository, and it has the challenge, and it will give you a solution. I'm Ryzen solver, yeah, solve.py. So in their solution, you see they set the parameters as noted in the schema file. They connect to the port. So this is just all connection stuff. They put in the ticket. Okay. There you go. And this is just connecting to the port. Okay. So this is where they get the bit string data. That's where S is a variable, and they're putting in all the binary data they get from the port. And then they specify the packet information that they found in the schema file. Once they do that, they loop through the data. So once you loop through the data, you need to make sure that each packet you're looping through matches the APID. If it doesn't match the APID, we disregard it. So this is what it's doing. And then once it does that, it gets the bit string of that. And then it puts it within the 7-bit encoding. And it puts all those characters together. It goes through each packet one at a time, puts them together in order to get the flag at the end. And you should, if you create your parser correctly, you will get the output noted in the end. So that's it for our last lesson. Congratulations. In the next module, we will be going over common attacks and vulnerabilities among satellites, and also covering a conceptual overview of the future of space and satellite security. So get excited, and thank you so much. Hi everyone, welcome to the final module of the Aerospace Cybersecurity Satellite Hacking course. You finally made it. This is the last module, and I'm really excited about this module because we're going to be doing a lot more interactive labs and CTFs where we apply a lot of the conceptual knowledge we learned in the first 3 modules and really apply it to something that's practical and hands-on. In this first lesson, we're going to be covering common attacks that are targeted on satellites and do 2 interactive labs to really refine your knowledge on what we are going to be talking about. So just a general lesson overview of what to expect. Firstly, we're going to be going over the conceptual know-how of attacks that commonly are utilized against satellite systems and equipment that is necessary to conduct those attacks. Then we're going to be diving into our first lab where we will be simulating spoofing GNSS signals, where we can spoof our location on Earth by sending up a malicious signal via a software-defined radio to a satellite. And lastly, we're going to be doing a Hackasat CTF called I Like to Watch, where I will be walking you through the solution of the CTF and how you can employ tools using Python and scripting to get your answer. Okay, so general attack categories that could occur on a satellite system are as follows. Firstly, there are replay attacks. Replay attacks occur when you're replaying previously recorded data streams and then resending it at another time. This is often used to confuse the satellite system's onboard computer. Secondly, you have uploading malicious code or payloads or exploded code. This is what happens when you execute bad, nefarious code, also known as a payload, onto a spacecraft, making it do things that it shouldn't be doing. Then you have subsystem compromisation. Subsystems are specific component categories of a satellite. And if you target a specific subsystem, you can compromise the functionality of the subsystem and lose control of the satellite. So for example, if you compromise the propulsion system of a satellite, then you won't be able to maintain its attitude, and it might have some kind of thermal regulation error. So there's a lot of ways an attacker could specifically hone in on a specific subsystem of the satellite and compromise the functionality. Then we have communication attacks. These are attacks pretty common that target the communication layers of a spacecraft to compromise control. So like the uplink, the downlink, or the crosslink. Then we have physical attacks. This is where the attacker tries to execute physical damage to compromise spacecraft functionality. Not very easy to conduct, but there are a lot of satellite attack systems that have been developed by the military, where you use either kinetic forms or non-kinetic forms, like electromagnetic pulses, to physically attack a satellite. And lastly, we have a more covert example, which are called side channel attacks. This is a weird kind of attack because it exploits indirect factors of a satellite to influence the execution of a specific program. I'll dive a little bit deeper as we go into each one specifically. So for replay attacks, like I said before, this is recording and replaying data streams to exploit a system. And there's two ways you can mainly do this. You can do this via custom crafted packets via the communication system. So this is what happens when an attacker records packets sent to a satellite and then replays them at another time. This is often used to perform a wide range of attacks, such as a denial of service, overloading, where you take what's being sent via communication link and then replaying it a lot of different times to overload the receiving end of the satellite. And then subsystem manipulation. So for example, if you take a telemetry message that was sent at another day and then replay it at another time, it might cause some subsystem error or issue to occur. Secondly, you have more internal based replay attacks. This is what happens when you manipulate the internal bus traffic that connects all the components within the satellite and the onboard computer of the satellite. And by monitoring for commands sent via the bus and replaying them, an attacker can overload system resources, such as like CPU or processing speed within the spacecraft, repeat behavior in order to cause abnormalities and delay functions of the satellite. For malicious code and exploiting code, this is what happens when an attacker uploads nefarious payloads or exploits onboard firmware and software. So we can categorize this into many things, but the most common are ransomware. This is what happens when some malicious payload is uploaded to a satellite via an uplink, and that ransomware takes pretty much takes control of all the data and it makes it inaccessible to whoever wants to access it. And it does this by encrypting all those files and then getting rid of the decryption key. So it's held there in place, and a ransomware will usually have some kind of message or an indicator saying, hey, pay us like this sum of money in order to get the decryption key to decrypt the files. There's also hardware commands, which directly run commands to perform malicious activities within the hardware. So these include sensors, motors, actuators, and so forth. There's also a type of malware called wiper malware, which just destroys all the data of a satellite and makes it inaccessible. Sounds like the name. It just wipes everything out. And then lastly, there's a rootkit. A rootkit's more secretive because it hides the presence of the malware itself by modifying the internal operating system of the satellite. So it's more covert, making it less detectable by people who are maintaining the satellite. There's also attacks that can be conducted on flight software and the internal operating systems. These attacks typically abuse the internal vulnerabilities within flight software to execute code and commands. Threat actors can also exploit flaws within the actual operating system itself to control the memory management and how tasks are allocated, storage functionality, and bus commands. Diving into subsystem compromisation, this is when an attacker attacks a specific subsystem to compromise its function. So there's typically the way it's done is by modifying the onboard values that are sent to each of the subsystems. And this is induced by performing specific commands to change internal values such as internal routing tables, registrars, scheduling tables, and so forth. By compromising the system, there's different modalities of pursuing it depending on the subsystem itself. So for instance, the propulsion subsystem, this could lead, subsystem compromisation could ensue orbit realignment, wasted energy, and damage to the satellite. For the attitude determination and control subsystem, this is where the position can be modified and orientation could be changed, causing the loss of a satellite because it escapes in orbit or wasted resources and energy. For the electrical power system, this modifies power consumption of the satellite itself, so wasted power and depleting its battery resources. Then we have the command and data handling system. This causes a lot of issues within the command handling system and delays communication. For the watchdog timer, it causes problems because it could alter timeout values to delete hardware and software resources and priority. And then lastly, we have the system clock, which could cause incorrect execution of commands depending on what command is being manipulated. So for communication attacks, this is, I would say, the most common for a general hacker who is staying at home and just wants to hack a satellite and cause trouble. This is what ensues when you exploit a communication link to coordinate an attack. And there's 4 ways of doing this. There's jamming. Jamming occurs when a well-known frequency for a satellite is overwhelmed with a lot of signals, which causes disturbances and interrupts communications. There's also spoofing, which is the transmitting of a counterfeit radio signal to a receiver to override a legitimate signal. So it would fabricate a new signal and say, hey, this is legitimate, while another signal is actually the valid one. So it fakes being a valid signal while it really isn't a valid signal. We'll be diving into this on the first level. And then we have eavesdropping. This is pretty common if you just want access to data and don't really want to pursue an active attack. And this occurs when you intercept communication and decipher and decode that communication to get access to data you shouldn't be getting access to. And then lastly, there's hijacking and control. And this is using a satellite to transmit or control a packet and then replace it with another. Hackers typically transmit fake data and then gain control over a part of the satellite infrastructure. Here we get into some of the interesting attacks. So physical attacks, they are quite rare, but they do exist. They sound kind of like something that would pop up in a science fiction film, but you'll be surprised by what military organizations have in handy today. So this is attacks that are caused by physical damage to a satellite. So there's kinetic attacks, and then we have non-kinetic attacks. Kinetic attacks is where we damage the satellite using direct methods. So this could be missiles, where the government has medium to long range missiles from Earth that target a specific satellite. Maybe it's from a foreign international organization that is doing something sketchy. And then you can also use other satellites, rogue satellites, to match the orbit of the targeted satellite and then collide into it and explode it and compromise its functionality. There's also non-kinetic attacks, which cause physical damage to the aircraft without directly touching it. So there can be 3 ways of doing this. There's the electromagnetic pulse, which are just detonations within space that degrade specific satellite components like the electrical subsystem. There's lasers, which use optic capabilities to damage components on satellites. And lastly, there's microwaves. Microwaves are typically used to compromise satellite electronic systems. Side channel attacks exploit indirect factors of a spacecraft to influence the program function. So there's active attacks that can occur, and there's passive attacks. So active attacks audit internal components in the satellite, and typically this is what happens with a fault injection. A fault injection occurs when an attack is executed, and the hacker is specifically trying to find a fault in an intermediate process, which results in the internal computation of a satellite to falter. So, for example, this could be manipulating electronics of the satellite using electromagnetic radiation that would compromise some kind of execution of code or some kind of actuator capability or some action you want to be performed by the satellite. For passive attacks, use external factors in order to run a side channel attack. There's many ways you can do this. There's timing analysis, electromagnetic analysis, and power analysis. For timing analysis, you're analyzing the data movement, so typically the processor, and analyzing execution times to figure out when specific commands are executed and exploit that. For electromagnetic analysis, you look at the electromagnetic emanations, so like power, wattage, current, to spot for information leakages. And lastly, power analysis analyzes the power consumption within specific subsystems to find where data is being transferred or hidden. So in terms of general purpose satellite hacking materials, you don't need much if you want to run a satellite communication attack. What you need is a high frequency and gain antenna. You need a radio frequency analyzer, and for eavesdropping attacks, a decryption software. So let's move into our first lab, where we will be simulating a GPS spoofing attack. Just a general disclaimer, I do not take any responsibility for what you take out of this lab. Please do not employ any of this knowledge to attack systems. This is for solely educational purposes only, and I'll remain it at that. So the objective of this lab is to create a believable GPS data signal and then simulate it. So what is GNSS spoofing? So GNSS, kind of like GPS, is this global navigation satellite system. And you've probably used it when you're running an app on your phone, like Google Maps or Uber. So many applications have integrated map systems, and all of those systems rely on this function called GPS in order to figure out where you are located on Earth. GPS spoofing is when a person alters data being sent to a satellite in order to appear in a different location and time zone. So for example, if I'm here in California and I want to spoof being in New York, I could do that by sending a fabricated signal to a satellite and saying, hey, I'm not actually in California, I'm actually in New York, and then set my location to a spoofed position rather than my actual location. So in order to understand this, one concept you should understand is ephemeral positioning. And ephemeris is a position of a celestial body in space. There's nothing fancy about it. It's just where something is in space. And GNSS works by using ground-based receivers to listen from signals from satellites in the GPS constellation. So typically, like let's say you're running an application on your phone like Google Maps, that's a ground-based receiver that's receiving all these signals from GPS satellites and using that signals and analyzing those signals to find out where you are. And each satellite it receives a signal from encodes position data into that signal. And by taking the signal from at least 4 satellites, you can get the location of the receiver, your phone, via a procedure called trilateration. And I included an image here, which includes like the mathematics behind it. So it takes in signals and then it encodes position data on a three-dimensional system, so X, Y, Z, and then computes the positions using those position points. So one thing that helps orchestrate a GPS spoofing attack is something called a GPS broadcast ephemeris file. And these are daily GPS broadcasts within the ephemeris file format. So you'll see .brdc, and this combines the individual site navigation files into one file format. And the user specifies the GPS constellation through a GPS broadcast ephemeris file. And these files generate pseudo-range and Doppler for the GPS satellites in view, and then it creates a IQ sample for the GPS signal. And the sampling rate of the user motion has to be 10 Hertz, and the attacker using this GPS broadcast ephemeris file, which contains the navigation data of all these GPS satellites, can set a spoofed location manually using a terminal and an accessible software-defined radio. So firstly, in order to execute an attack or simulate an attack like this, we will need to get an up-to-date ephemeris file. So NASA has an archive of these files. I will show you the website here. So it's cdis.nasa.gov/archive/gnss data/daily. You do need to make an account to run this, but just put in your email, username, and password, and you can get an access to this data. So if you scroll down all the way down to the modern year date, and then I'll get the most up-to-date one. And you can click any of these. So you'll need to download, so there's 3 constellations here, so you need to download one of them. And once you have a file downloaded, you need to set a location. So you can get GPS coordinates from any location you want it to. So let's say I want to spoof a location. So I don't want to appear to be in my location. I want to be at Universal Studios. So I would click this on Google Maps, and then I would right click it, and I would click here. And that gives me the latitude and the longitude. Once you have that, we can go about transmitting spoofed signals. So something like a HackRF, make sure it has both transmitting capabilities and receiving capabilities. If it only has receiving capabilities, like the RTL SDR, it cannot coordinate a spoofing attack because it cannot transmit anything. So I would recommend the HackRF, and it's pretty easy to install, and it's very compatible with the command line interface, and you can use something called a GPS spoof command with it. So yes, this is illegal, so we are going to be simulating it. Please do not do this at home. I trust your integrity, and please use common sense. So in order to do this, you'll need to download something called GPS SDR sim. So this is their GitHub repository, and once you install it by running git clone this repository, you can run it with C. And the command to do this will be gcc gpssim.c, and then you put in the parameters and SDRSim. And by looking at the documentation here, if you have a HackRF, you can transmit samples. So you can run either of these 2 commands. You can run the GPS SDR sim and plug in the ephemeris file to transmit. For our second lab, I will be running you through the Hackasat I Like to Watch CTF. The objective of the CTF is to analyze the TLE captured from satellite data and intercept a KML file to find a flag. So for the CTF objective, we've captured data from a satellite that shows a flag located at the base of the Washington Monument. The image was taken on this date, March 26, 2020, and the satellite used was described by this TLE here, so it's a redax satellite, and it has this TLE describing its orbital elements and different descriptors. And for the challenge, you're supposed to use Google Earth Pro, a KML file. A KML file is a Earth-based data file, and it links to the following URL. And there's a indicator called look at that spots where the satellite was when it took the photo in order to get us the flag for the CTF. So before diving in further, what is a KML file? So it stands for Keyhole Markup Language, and it is a file format used to display geographic data in an Earth browser like Google Earth. So for the CTF, they gave us this KML file. I included it here from their GitHub repository, and we can take a look at it. There we go. Okay, so just by looking at this, they have the look at. So remember I mentioned they want something to do with the look at file. And this is like more specifically whenever you run a KML file and put it into Google Earth, this is where it will point to, so you'll visually see it. So here it wants the longitude of the satellite, the latitude of the satellite, the altitude of the satellite, the heading, the tilt, the range, and the altitude mode. And it also wants this link here. And it gives us some parameters, angle 180, which will come in handy later. So the first step to solving this challenge is to analyze the TLE that was provided. So going back to TLE structures, the first line is always the name of the satellite, so it's redact. And then we have the line numbers here, line 1, line 2. And here we have the satellite designator, so that ID. Then we have the international designator. We have the epoch, which is the timing, and other various calculations. Then we have the 6 Keplerian elements down here. So we have inclination, rate of sensation of the ascending node, eccentricity of the orbit, argument of perigee, mean anomaly, mean motion. So what we need to do is modify the KML lookup, and we need to fill in the proper values and then display it in Google Maps. So in Google Maps, if you look at the Washington Monument and you get the coordinates, the latitude is this and the latitude is that. So we already know the latitude value and the longitude value. That's great. Then we need to calculate ESEF values. In order to make the other calculations for the other fields that were asked in the KML values, we need to operate in another coordinate system. And what ESEF is an Earth-centered, Earth-fixed, and it is within the Cartesian coordinate system. And you need to use a calculator like this in order to calculate the values for the CTF. So you put in latitude, longitude, and meters, and it'll give you the kilometers as a result. You also need to understand the topocentric value coordinate system. So this is another coordinate system with respect to a specific point on the Earth's surface. And these values include the other values we need for the KML file, which is the azimuth, the elevation and the range. So by using these systems, we can figure out the remaining values here: altitude, range, tilt, heading, longitude, latitude, altitude. So how do we make these calculations? So what's great about Python and scripting is that we can use these astronomy-based tools in order to automate a lot of the calculations for us. So we don't have to hammer in all these values into a calculator and spend hours of time trying to solve something for a CTF. So Skyfield is a Python library which computes positions for the stars, planets, and satellites in orbit around Earth. And getting topocentric values relative from the satellite relative to the Washington Monument coordinates, we need to get those values in order to figure out everything we need for the CTF of this challenge. So the Hackastat qualifier listed a Python script that they used to calculate everything that they need. So you can see they used Skyfield, they used a topocentric system. And what they did, so you can disregard this. This is all to connect the challenge. So it connects to the host and the port. And then it loads the TLE. So this was a TLE that was provided by the challenge. And then from here, it makes a satellite object, taking in the first line of the TLE, the second line, and the name of the satellite. And then right here. So this is just setting the timing specific to the challenge time date. Connects to the server. So here you can see it sets the longitude and the latitude of the Washington Monument system and the topocentric coordinate system. And then it creates the position of it within the geocentric. So it finds the specific location of the satellite. So this is just all finding the location of the satellite. And it finds it relative to the Washington Monument. So by doing that, it can calculate the azimuth. And once it calculates the azimuth, it can get the altitude and the distance using the altitus function in Skyfield. So at this point, you have the latitude, the longitude, the range. It just has to be over this many meters at altitude, and it works. And then it defines the heading and the tilt by using the azimuth values that were calculated in the topocentric grid system here. And then it sets everything up. So it submits and modifies the KML file in order to get the flag. So you can see here, it just makes general calculations using the Skyfield library in order to figure out where the satellite is relative to the Washington Monument. And then it calculates everything that was necessary in the KML file in order to submit the flag to the server. So I would if I were you, I would take a deeper look into the different calculations that were being made in order to get the values of the satellite telemetry relative to Earth. But pretty much the meat of it is within these lines of code where it's calculating the positions and then it's getting all the other values. Wonderful. So from the CTF and getting the calculations using Skyfield, you can get the latitude and longitude, which is the Washington State Monument's latitude and longitude, the altitude, you can set the 0, the heading, and the tilt, and the range. Thank you so much for watching this episode, and I'll see you in the next one. Hi everyone, you've officially made it to the last lesson of this course. Congratulations. In this lesson, we're going to be covering the future of satellite security, what it looks like, enhanced technologies, and cover next steps and resources for you to keep progressing in this journey in aerospace cybersecurity. All right, so just a general course recap of everything that we covered. It was a long course, so in Module 1, we went over basic reconnaissance tools, open source intelligence, Keplerian elements. Module 2, we did a deep dive into communication analysis and eavesdropping. That was a lot. We talked about transponders, receiver systems, transmitter systems, and reading data sheets for those. We also talked a lot about link budgets and the details that are included in link budgets. In the third module, we went over reverse engineering and decoding communication using software such as SatDump, New Radio, and also Wireshark to look over specific packet protocols. We went over DBS as well. And then in the last module, we did a bunch of labs, discussed vulnerabilities and common attacks on satellites, and also mitigation strategies in order to threat model and detect for common satellite attacks like spoofing. We covered a wide range of topics, so we started off with orbital mechanics, such as like the 6 Keplerian elements to identify where a satellite is located in orbit, satellite reconnaissance, figuring out characteristics of the satellite, decoding satellite communication, figuring out modulation schemes, looking through packet protocol structures, satellite onboard systems. We did a deep dive into each respective subsystem, like the propulsion subsystem, command and data handling subsystem, and went over each of those components that made up and comprised those subsystems. We tuned into satellites via radio frequencies using analyzers such as SatDump. We did a vulnerability analysis report of satellites using frameworks like Sparta. We covered common attacks employed against satellites, communication attacks, side channel attacks, physical attacks, and then we went over how you can detect for satellite hacking. Just a general skills overview of everything you covered. So in terms of OSINT for satellite systems and operations, we went over how you can use online sources like SatNow, N2IO, KVH for frequencies, EO portal, and so forth. We also visualized orbits using online sites. In terms of Python scripting for satellite reconnaissance and captured flags, we went over libraries such as AstroPy, CCSDSPy, making TLE and orbital calculations, and making antenna calculations for link budget or telemetry links. In terms of satellite tracking, we visualized ground tracks and past periods using gpredict. For satellite eavesdropping and packet decoding, we intercepted packets, found the packet protocol, and performed open source intelligence on the communications to report vulnerabilities. For satellite signals intelligence, we used New Radio for satellite decoding. We went over packet dissection with DVB-S2 with Wireshark. We decoded signals using SatDump and WX.2IMG. In terms of satellite attack understanding, we went over simulating jamming and spoofing attacks. We went over how to use software-defined radios like HackRF for satellite applications. And we solved about 4 CTFs hosted in the Hackasat competition. In terms of satellite file and data forensics, we taught you how to interpret TLEs, create custom Python parsers, and interpret MIA data logs. And then lastly, for attack mitigation and threat modeling, we went about understanding and categorizing attacks and modeling attacks for satellites such as OPSAT using Sparta. So diving into creating more secure satellites in the future, we need to make sure we adhere to a principle set by the Secure by Design. And the Secure by Design is making sure that there's appropriate security measures in place in the design and development process, not only the execution process. When you have things like cyber being implemented only at the execution process where attacks actually occur, then there's a lot more risk involved. So this principle makes sure security is in place from the beginning, so we don't have havocs and are not naive about security and then have it be attacked and vulnerable. So this makes sure that all spacecraft meets NSA level security and maintains that security. And it was established by a wide range of cybersecurity-based organizations. In terms of standards for cyber resilience, there have been multiple in development and continue to be more initiatives for standards and protocols put into place to make a more secure space environment. So one famous one is the Space Policy Directive 5. NASA also has a standard for this called NASA Space Asset Protection Standard. And then we have the Aerospace Organization's cybersecurity protections for spacecraft. I also wanted to mention more initiatives. One is SpaceOS. SpaceOS is a company that's thriving to create a more secure operating system for satellites. A lot of satellites use a generic operating system that are not founded on secure by design principles and in turn are very vulnerable to a wide range of attacks. SpaceOS is based off of a unikernel called MirageOS, which is secure from the beginning, and they fine-tuned it for satellite systems. So it is a unikernel-based operating systems adhering to secure by design principles. And I put a little architecture map of what SpaceOS is, and I highly recommend you check out their website if you're interested in learning more about this initiative. And the 5 axes for cybersecurity they implemented was within the programming language they used. So within the programming language, they used something called OCaml, which eliminates all memory corruption attacks, which are 70 to 90% of most satellite vulnerabilities. For the attack surface, they did not use code, and code was not included. So there was less code to audit and no dormant vulnerabilities and dependencies. So the binaries are much more compressed and smaller, and attackers can't see it. In terms of battle testing, they tested this out with over 10,000 attempts, where they offered 10 BTC worth of Bitcoin in a cloud-hosted MirageOS. So they invited a wide range of international hackers to hack into their system for 10 BTC worth of Bitcoin, which is a crazy amount, but no one is able to hack into it, showing its security. And then they isolated each of its components. So they compartmentalized the SpaceOS unikernel and made the security updates easier. And lastly, they implemented formal verification. So they have a wide range of cryptography libraries, mathematically proved to be protected to protect the underlying infrastructure. Diving more into the future of cybersecurity, so there's been a more recent initiative called the Moonlighter. You might have heard of it if you were at this year's DEF CON in the Aerospace Village, where the Moonlighter is essentially the world's first hackable satellite in orbit. So it's a satellite that was developed by the Hackasat team that is actively running a CTF environment, and SpaceX launched it as of this year for satellite training and research. There's also quantum cryptography libraries being developed specifically for satellite communications. Talking about it is beyond the scope of this course because quantum mechanics and physics is an entire beast of its own, but if you want to check it out, there is a library called KSAT, where they implement a low orbit satellite with a quantum receiver and transmitter using quantum-ended photons. So if you don't, when something is the point of using quantum is to make things ultra secure, because with quantum, you're not confined to 2 states with a traditional computer where you only have zeros and ones. With quantum, you can have a whole range of states, making it more secure. if proper encryption protocols are implemented. In terms of more communication protocols that are pragmatic, there's one called QPET, which is a proposed new encryption proxy for high latency satellite communication. In terms of security for satellites, I wanted to mention and make this point clear that I think enhanced encryption will be one of the most vital things we can do. So making sure that at least all satellites are encrypted, no matter their telemetry link. If it is a general purpose satellite with no attack vector, then that is okay, but making sure at least we have some kind of baseline protection that is accessible, especially for small startups and enterprise organizations. So one could be AES 256, which is one of the most secure encryption algorithms available on the market today. And it is resistant to brute force attacks, side channel attacks, and crypto analysis. For optical interlink satellites, this is where there's a cross-link between two satellites, and they typically use some kind of laser or an optical system to send information. Making sure those optical systems maintain some kind of encryption so other satellites in orbit cannot intercept those signals. And encrypt and decrypt data. There's been studies where they've encrypted and decrypted data for optical interlink satellite links with a throughput of 50 gigabytes per second per channel, which is pretty impressive. And lastly, quantum encryption, creating usable quantum channels for communication for satellites to secure links even further. In terms of quantum encryption, there's a wide range of things that can be implemented. First thing is QSSL, kind of like a session link, but quantum secured. So this will be an extended version of common protocols such as SSL and TLS, enabling the deployment of practical quantum cryptographic-based security applications. In order to make this technology work, there will have to be implementation of quantum random number generators, which leverage the truly random properties of quantum physics to generate a true source of entropy. So all the random number generator libraries today are not completely random. They are random to an extent, but there is a predicted quality to them. In terms of quantum-based random number generator systems, this will be through and through random. So truly random, intrinsic, and that would enhance encryption much more. And lastly, there's been a number of initiatives to make quantum-based satellites. There was one, I think the first one was deployed by China, where they were able to actually send a message that was encrypted using quantum key distribution. And there's one initiative from Canada Space Association called KSAT, where they're currently conducting an experiment of their own to make a quantum key distribution-based satellite. So I want to talk a little bit about the international initiatives that have been taking place. So space security discussions within the United Nations have been taking place since the 1980s. This was the first popular initiative you saw with this was the prevention of an arms race in outer space, where international communities came together and established a list of regulations to keep themselves out of danger and out of warfare within a space-based environment. There's also been guidelines written, such as the International Code of Conduct for Outer Space Activities, which puts limitations on what a nation can do in space. There's also the No First Placement of Weapons in Outer Space pledge, which is a pledge to keep space weapon-free. And then there's a voluntary moratorium on destructive anti-satellite missile testing. So this is just a general agreement that nations will not be utilizing missiles, ground-based missiles, to conduct physical attacks on spacecraft. You can keep updated with these international security initiatives on this website. They list a wide range of ongoing initiatives that are in relation to space and space security. So I would recommend checking it out. In terms of resources, if you like to dive further into this field and are interested in it, I listed out 4 free resources here you can use to leverage your knowledge and apply it in a different setting. So the first one, which is one of the main reasons I learned aerospace cybersecurity, was through these aerospace village talks. They list, I think there's lots of different talks they've conducted throughout the years, and most of them are related to satellite security. So I would recommend looking into that. I also created a tools repository for you to explore different tools you can use to conduct satellite security audits. There's the awesome space list, which has a wide range of resources like free online books, videos for spacecraft security, and then lastly the Hackasat CTFs. This is just a preview of the awesome space list. So you can see they included APIs, data sets, and software for you to enhance your knowledge. In terms of free online resources I was able to find, these were the best. The Hawaii Space Flight Lab has a lot of good nanosatellite and satellite-based lectures, so I would recommend checking out EPET 400. They just go over a lot of spacecraft knowledge, so if you want to find your skill set in that, I would recommend checking it out. MIT OpenCourseware has a satellite engineering course, which is really handy. There's a publication on ResearchGate that talks thoroughly about communication subsystems for satellite design, which I found really helpful. If you want one really like hands-on and pragmatic paper, I would recommend this site here, which goes over each of the different subsystems for the NanoStar project, which is an actual nanosatellite that was deployed, and you can read over the actual project, and they do a really good job documenting it. And then if you want to get further into spaceflight, NASA has a really cool repository of knowledge in their NASA Basics of Spaceflight and just general NASA resources. They're really big on education and huge proponents of it, so you can get a lot of information, especially from their nanosatellite guides. For getting hands-on practice, I listed below 4 simulations you can use. I personally believe simulations are a great way to get hands-on experience and really hone in your skills. So we use the satellite jamming simulator. I listed the link if you want to use it again. Hypatia is a low Earth orbit satellite network simulation. So if you want to practice with low Earth orbit satellites, I recommend checking it out. There's various satellite spoofing simulators, and also Hackasat CTFs are a really good way of getting hands-on practice. I would recommend looking through write-ups that talk through solutions, because they can typically be very difficult, especially for beginners. So just start by reading over the write-ups, and then from there you can write up scripts of your own to solve some of the CTFs. Some events and conferences coming up that you can attend to be part of the community is the DEF CON Aerospace Village. I know it'll be next year, but it'll be cool to like mark that down in your calendar if you do want to attend DEF CON. There's also Hack Space Con, which is going to be happening in April, which will be hosted in Florida and will be all around, all centered around space security. There's also more satellite-based conferences. There's this annual Small Sat conference, which focuses on small sats. And then the AMOS conference, which is another satellite-based conference. With that being said, I want to express my deep gratitude for everyone who attended this course. Thank you so much for taking the time and having an open mind to these concepts. I know satellite security isn't very talked very much, but thank you so much for taking the time to really pursue a field that is going to be integral in the future. If you have any questions or want to reach out to me, I listed my email there and my website. I also have different socials on my website you can check out to follow my work. And I hope you have a great rest of your day. Thank you so much for attending this course and congratulations. Hi everyone, welcome to lesson 3 of module 4's Aerospace Cybersecurity satellite hacking course. In this lesson, we're going to be talking more about the defensive side of things. So we'll be listing over ways you can detect attacks and mitigate those attacks with a couple of strategies. So a brief lesson overview. Firstly, we're going to be understanding threat modeling within a space-based environment. Then we're going to be doing one lab to detect for GNSS spoofing attacks. If you recall, in the first lesson of this module, we went over how you can simulate a GNSS spoofing attack. Now we're going to flip to the other side of the coin and cover how we're going to be detecting for them. And then lastly, we're going to be analyzing satellite attacks with a threat modeling framework called STARTA. All right, so a little bit about satellite attack detection. Space system cyber resiliency is really important for protecting space systems. And I listed out 4 of the most common attacks. For jamming, there's many ways you can detect an attack, but it typically involves locating a radio frequency, so performing some kind of signals intelligence. And then GPS interference. So if there's an interference with GNSS satellites, for example, maybe the downlink is being jammed. Examples of this will be the Spire's GPS radio occlusion, which measures the RF characteristics inside the Earth's atmosphere. For eavesdropping, attack detection involves enhanced encryption and modulation techniques to make decoding more difficult. Since eavesdropping is the ability for a hacker to sneak their way into a communication link and get data, a better way of defending it is just to make it more encrypted, so hackers have a hard time reverse engineering that packet data. Next up, for hijacking signal, you can combine a range of techniques such as signal monitoring, telemetry analysis, and anomaly detection. So monitoring for malicious signals, analyzing telemetry packets, so looking through like commands being sent, monitoring sensor values, monitoring subsystem values, making sure they're okay, and detecting for any anomalies within that data. And then control, just again, signal monitoring, performing forensics, specifically like on data formats or file formats that are being logged to make sure everything is okay and there's no hacker on board. And lastly, fingerprinting of media, making sure media is up to date and properly categorized, so if anyone were to intrude in the satellite, you would know. So let's talk a little bit about threat models. A threat model, you might have already seen this, is a model including details about potential threats and vulnerabilities to a system alongside appropriate countermeasures. So a common example I like to use is the Batman's threat model. So you can see here, it lists out all his assets, so like Batcave, Alfred, emails, texts, and then it lists out the threats. So here we have the police, Joker, and journalists. And then you see countermeasures. Security system, high location, encryption, and it shows the relationship between what he wants to protect, the mitigation, countermeasures, and the threats. And it marks the relationship between them using these lines here and the degree of risk. So we can apply the same kind of framework to satellite systems or any kind of spacecraft within space. So like I mentioned before, there's 4 main categories. There's the space segment, the user segment, the link segment, and the ground segment. For the space segment, There's a lot of onboard vulnerabilities, especially for things such as subsystem compromisation or onboard computers or the internal communication components of the satellite. For the user segment, we have things such as like the interruption of commercial services, which could result from an attack specifically on commercial-based satellite systems like satellite TV, satellite-based like radio calls, and so forth. Then we have the link segment, so the uplink and the downlink are the main threats there, so jamming, spoofing, pretty much any communication attack. And then the ground segment. The ground segment is critical because it connects everything together, and I would say it is the most vulnerable because since it connects everything, you really want to make sure the ground segment works. So these are target to a wide range of attacks. So I have an example threat model of the OPSAT. We're going to be covering this a little bit further in the lab that we do. But you can see here that they outlined pretty much in every component of the satellite. And then they walk you through a possible threat model of it using the attack path and a hierarchy structure. So here we have the satellite, and then they broke up the satellite into two component categories. So the bus of the satellite, so the internal communication, and then the payload. So things that are being uploaded to the satellite, such as code, commands, and so forth. So the bus, they said, is vulnerable to arbitrary code execution, control data interaction. They said the payload is vulnerable to denial of service and payload data interaction, which makes sense. For the satellite, the main threats they listed are seizure of control, denial of service, and malicious data interaction. And they listed out the relationship between these two by hierarchy, saying bus is part of the satellite, payload is part of the satellite. And part of the bus, we can break it down into three further categories. You have the communications, the command data handling system, and the bus payload link. For the payload, we can break this further. We have PLCOM, UDHS, and PDHS. And you can see here, they listed out on the attack path. So for example, the bus, an attack usually starts out with communication from the receiver. So it receives something via the receiver that causes it to bypass access control. And then from there, the attacker moves themselves to the TC fetcher, and then they can run a wide range of targeted attacks here, exploiting vulnerable TCs, dangerous TC suppression, or control data link. And then from there, they can move themselves up to compromising the bus via these two things, and then they can seize control of the satellite. Or another way they can do it is they can start from the link TC fetcher, so they can exploit a vulnerable TC interface or do any of these things, move themselves to compromising the command data handling system, compromise the bus, compromise the satellite. Same thing here, you can just follow the lines. So let's say they start with the PLCOM receiver, they bypass access control, they move themselves to the PD fetcher. Maybe they exploit one of these four things. They exploit a service information link, move themselves to the UDHS for a side channel attack. Or for example, they do an attack on PLCOM, move themselves to the PD fetcher, exploit vulnerable data processing, cause a payload data interaction within the payload that is malicious, and then compromise the satellite using malicious data interaction. So there's just a general outline and a hierarchy of possible threat models, and it really helps a lot of people on the cyber side look over and audit through possible vulnerabilities so attacks like this don't actually occur. So let's do a lab. In this lab, we'll be detecting for GNSS spoofing attacks, and we're going to be analyzing something called NMEA data logs to detect for GPS and GLONASS satellite spoofing. So what are NMEA data logs? So this is a standard format for sending GPS navigation information. This was established by, I think, the National Marine Organization, and it's just a generic standard text format that includes logs of GPS information. So firstly, they start with the type of satellite. So prefix is the satellite constellation. So GP would be GPS. So this one would be GPS since it starts with GP. So all these are actually GPS. They have 3D coordinates, which we'll dive into, so like latitude and longitude, the number of satellites involved in a satellite transaction, and latitude and longitude, and other like telemetry values. So this is just the generic log of GPS activity that occurs, and we can perform forensics on this, so we can analyze these files of things that happened in the past in order to detect for possible attacks that may have occurred. All right, so I included a sample NMEA text in this repository that you guys can visit and download, but I included a snippet screenshot of it here. So let's start with reading one of these values. So like I said before, the beginning is the prefix, indicates the constellation. So in this line, it starts with GP. So we know it's a GPS constellation. And then from there, we have 3 characters after. So it can be GGA or GSV. This is the standard, like the format of how the log is going to be formatted in the template, pretty much. So GGA is a fixed position structure. It's kind of like GSA. GSV, on the other hand, is just a visible log, so there's no SNR field. So just like slight nuances in how the log is going to be structured. It's not too much, it doesn't hold any information by itself. And then after that, you have the time in UTC. So this would be like September 27th, 50 minutes. And then from there, you have the latitude and the longitude. So this would be 53.216802 degrees north. And then here you have just 0.63033372 degrees west. And then the next one is fixed quality. So this one would be 1. And then it shows the number of satellites it used to get the position. So remember, the way GPS works is that it communicates with a bunch of satellites, gets positional information from them, and then uses that to calculate the position of the receiver. So this time you need at least 4. This one used 8 satellites. And then these are just more technical values. So we have 1.03 as a horizontal dilution of precision. We have 61.7, which is the altitude above sea level, meters. And then we have the height of the GeoID above the WGS84 ellipsoid, so 55.2 meters. And then the checksum, which is the star and the number at the end of it. All right, so we're going to be visualizing NMEA files. So if you go to my GitHub repository here, you can download the raw file. Download it on my desktop. And we can actually visualize these things. So if you go to nmeagen.org, we can see that these logs are commonly used to visualize coordinates. And then it computed it, and you can see here on our map that it points to a specific location. So it took the contents of the file and it just plotted out what was being logged. So in terms of spoofing the MIA files, there's 3 things that are mainly spoofed. We have GPS coordinates, altitude consistency, and signal strength. So in order to detect a spoofing attack, make sure you look for those 3. GPS coordinates that are off, that are not valid, or in a weird location. Altitude consistency, making sure the altitude of the satellite makes sense, and then the signal strength. So I think I just showed another example of an MIA log for another GPS satellite, so we'll go over it. So this is GPS, GSV stands for GNSS satellites in view. So this is going to be a GPS satellite and GNSS constellation. And then here we have these satellite logs. So it indicates that let's skip over these values. There's 2 satellites. Yeah, and then it goes through each satellite. So the elevation of this one, 39 degrees, azimuth 223, SNR 19, signal strength of 19. Goes for the next satellite, 13. Elevation is 28 degrees, azimuth 70 degrees, signal strength 17. Satellite 26, satellite degrees. So it goes elevation, azimuth, and then goes through each of these in the log. All right. So we're going to be doing one more practice lab with this. And if you go here, I included NMIA_practice.txt. And this includes 5 GSV files, records, and your job is to take a few minutes and try to figure out which one is spoofed. Remember that GPS coordinates, altitude consistency, and signal strength are important in figuring out which one is spoofed. So reading and decoding these, take like a minute or 2 and try to figure out which one you think is spoofed or not. Okay, I'm assuming you took a few minutes to figure out which ones are spoofed. So I'll be going over the solutions. So there were 2 spoofed satellite messages within each of these. And they were number 2 and number 5. So we can go over them. And the reasons for them being spoofed are that they did not have valid real-world GPS signals. They had an unrealistic elevation, or the signal strength values are way lower than expected. So let's analyze 2 and 5. So 2, so if you look back at the guide here, you can see 10, 65, 120, 17, 7, 70, 80. These, what I'm noticing here is not the elevation or not the GPS coordinates. I'm noticing the signal strength. You can see here that compared to all the other values, the signal strength is off. So from that inference, we can mark this one as spoofed. And then which one was the other one? 5. In terms of this one, this would be just GPS values and altitude inconsistencies. So when analyzing logs, it's important to look for all sorts of factors that could be indicative of spoofing. So these two were different factors like SNR and GPS. Okay. So now we're going to move a little bit on to threat modeling, where we analyze satellite attacks with the Sparta model framework. So we're going to be using the Sparta framework to analyze the OPSAT satellite attack. So firstly, credits to the Sparta team. This demonstration is mostly based on a paper they wrote for Medium. Brandon Bailey and Brad River from the Sparta team were proponents of this, where they made a robust presentation on the attack of the OPSAT satellite at SciSat 2023 for the Phallus group. So I would recommend checking out that presentation if you have some time. So when you're using the Sparta threat modeling framework, they categorize these tactics under these categories. So firstly, we have reconnaissance. That's gathering information about a specific spacecraft. So it would gather information about its subsystems, different components used to make it, and other things that will make it vulnerable. Resource development is finding resources to coordinate an attack. So the attacker would get themselves like the proper hardware and software necessary to orchestrate an attack. Then there's initial access, which is where an attacker tries to establish presence on a target spacecraft. So this is when they initially get access. An execution is the execution of the attack. So, for example, executing malicious code or malicious payload that could compromise the spacecraft. Persistence is being able to maintain their presence on the spacecraft and not getting ejected, so you have constant control. There's defense evasion, which is where you avoid being detected by authorities or the operators in the spacecraft. Lateral movement, where you navigate through various subsystems in the satellite. Exfiltration, this is when an attacker attempts to steal information from a satellite that could be privatized. And lastly, impact. This is when a hacker tries to interrupt operations of a spacecraft or compromise control and destroy it. Okay, so I just wanted to give a little bit of context of the OPSAT attack. So this was completely ethical. This was conducted by a team of researchers on the European Space Association's OPSAT. It was a nanosatellite launched in December of 2019, containing a very powerful onboard computer. More powerful than every other ESA nanosatellite that's previously been deployed into orbit. And the ESA tasked a team of ethical hackers to gain control of the satellite's application environment and introduce some malicious code. So just by getting some background information, we can outline the attack according to the categories defined by Sparta. So firstly, we have reconnaissance. So in the OPSAT scenario, the way they gathered information about the spacecraft was getting valid credentials. For resource development, they exploited a payload and they identified select delivery mechanisms on how they could upload a payload to the satellite. For initial access, the way they got access to the satellite was compromising a hosted payload and through the software supply chain. For executing the attack, there was various things they did. They exploited code flaws within the flight software and operating system, modified onboard values, and then altered the electrical power and added to determination and control subsystem. For persistence, they used the backdoors in the software to establish their presence, and then they used lateral movement to move between various subsystems and deploy their malicious code, and which exploited the lack of bus segregation. So there was an inherent vulnerability in the bus that connected the internal subsystems. And for exfiltration to get access to data, they used eavesdropping within the communication link. And then the impact they had was deception of values, disruption of satellite services, denial, degradation, and destruction. All right, so we can, knowing these category values, we can start to map out the attack. So Sparta has this awesome navigator feature that lets us do this. So let's create a new layer. So you go under here, create a new layer. Wonderful. So for this, the first value, it was gathers spacecraft. Let me go back. So yeah, it was gather spacecraft communications information and valid credentials. So under here, we have gather spacecraft communications information, valid credentials, and we can just map out these according to the category. So for the next one, we have exploiting payload and selecting delivery mechanism. Here we go. Obtain cyber capabilities, exploit payload. And then identify select delivery mechanism. For initial access, they compromised a hosted payload in the software supply chain. And then execution, they used a wide range of things. So what they did was they exploited code flaws. Flight software operating system. Modified onboard values. And they modified the command and data handling subsystem. Oh, pardon, attitude and electrical. For persistence, they used the backdoor within the software. And then lateral movement. They exploited a lack of bus segregation. Exfiltration, they used eavesdropping. And then impact, it had a lot of impact. So deception, misdirected the spacecraft, disruption, degradation, and destruction. So you can see here, after mapping out and analyzing the categories of an attack that was coordinated on a satellite, you can take that information and then plot out a threat model so researchers can take value from it, learn from the mistakes the vulnerabilities that's happened. Hi everyone, welcome to Lesson 2 of Module 4 of the Aerospace Cybersecurity Satellite Hacking series. In this lesson, we'll be diving further into attacks that can be orchestrated against satellites and get a little bit more hands-on practice with CTFs and simulators. So just a general lesson review of what we're going to be doing. So firstly, I'll be talking briefly about signals intelligence and its vital role in satellite security and interpreting satellite signals. Then we'll dive into doing a CTF, which will be configuring a telemetry link. This is another Hackasat CTF, and I think it's a great employment of some of the communication systems we talked about in lesson 2. And then lastly, we'll be doing an interactive lab for a satellite jamming simulator. All right, so let's do an overview of signals intelligence. What is signals intelligence? Signals intelligence, SIGINT for short, is the practice of analyzing electromagnetic signals to perform reconnaissance and get information about a specific target. So there are a variety of applications of signals intelligence, and it's mostly used to detect for hostile radio frequency attacks on satellites, such as jamming, spoofing, eavesdropping, hijacking, and troll, and so forth. And there's also a catalog of satellite RF sources. I would recommend checking out the SIG-ID wiki. This is really good, not only for satellite signals intelligence, but general purpose signals intelligence, but they have an entire catalog of satellite RF signals. So you can see here, it lists out the signal name, the description. So for example, this is the AMSAT, Amateur Satellite Oscar. And it lists out the frequency, the mode, the modulation scheme, the bandwidth, and a sample audio, and shows a waterfall image. So looking for this is really helpful if we're identifying a specific satellite signal that you are analyzing. And the reason I mentioned this is there's been an ever-evolving atmosphere for 5G and supporting 5G networks within the satellite, and it's called the 5G satellite spectrum. And these are going to be satellites powering the next generation of wireless technology. And there hasn't been a satellite segment of this implemented for 5G yet, but there are different proposals, one by the International Association of Electrical Engineers, IEEE, that are and the community is thinking of implementing satellites for this 5G infrastructure. And they're discussing using low Earth orbit satellites that significantly reduce latency, and the frequency for these satellites are still being determined. So with that being covered, let's dive into the first CTF of this class. We will be finding the link budget details. So recalling from what we learned in module 2, a link budget shows information and details about a communication system. So it could be the antenna, the receivers, the transmitters of a specific satellite. And this CTF tasks us with completing the link budget to complete the user documentation for a satellite system that is being developed by a few engineers. So diving a little bit deeper into link budgets, these are a set of calculations giving a performance summary of a communication link that is established by an aircraft. So this could include characteristics such as losses, frequency, EIRP, waveform schemes, signal-to-noise ratios, and carrier-to-noise ratios, spreading factor, and the transmitter antenna characteristics. So you typically have it in a tabulated format, including information about the antenna, the frequency, the uplink sites, and all the information necessary in order to make a communication link of a satellite. So this is segmented into 3 sections. So you have global parameters, and this is the reason why I'm mentioning this is the CTF segments these variables that it needs for the link budget into parameter types. So we have general parameters. This is just general information about a telemetry link. And we have the frequency, wavelength, and data rate. The frequency is the number of cycles of periodic wave that can occur in 1 second. So for example, here we have a wave with a lower frequency, and then here we have a wave with a higher frequency. So it just regulates how many cycles we have per second. Wavelength is the distance between 2 consecutive points that are in a phase of a wave. So this one has a long wavelength, and this one has a short wavelength, and we know that wavelength is inversely proportional to frequency. So meaning by that, as the wavelength gets longer, the lower the frequency will be. And the inverse, we have the wavelength gets shorter, the higher the frequency. Finally, we have the data rate parameter, and this shows the amount of digital data that can be transmitted over a communication channel in a given amount of time. So it shows how dense the communication link is with information. The second parameter category are transmit parameters, And these define the characteristics of the transmitter on a satellite. So here we have characteristics such as transmit line losses, which is in decibels, which shows the loss of signal strength over a communication link. There's also transmit half power beam width, which is in degrees, and it shows the angular width of a transmitting antenna radiation power at half its maximum power. So it shows the angle of the radiation power at half its max power. And then we have the transmit antenna gain, which is in decibels. And then it shows the effectiveness of transmitting an antenna and focusing radio energy in a particular direction. Shows how efficient it is in holding signals in a specific location. We have the transmitting pointing area, which is in degrees, which shows the angular deviation between the intended and the actual direction of the antenna's beam. So typically there is an inaccuracy or a buffer between where the antenna is actually pointed, the beam of the antenna is actually pointed, and the error. So this just shows the degrees with the error margin in degrees. And lastly, we have the transmit pointing loss, which is in decibels. And it is the reduction in signal strength due to deviations in the alignment of transmitting antenna. So because of just pragmatic and situational issues, there is always going to be a difference between the ideal alignment and the actual alignment. And this just calculates the amount of signal lost because of the deviation of the alignment. And then we have path parameters. Path parameters are characteristics of the path between the transmitter and the receiver. So we have the path length, which is the distance covered by a signal between its source and destination. So how much of a distance the signal is covering. Then we have polarization loss, which is the reduction in signal strength due to a mismatched polarization between the transmitting and receiving antennas. Then we have atmospheric loss, which is also in decibels, which is the attenuation or loss of signal strength caused by interactions with things in the atmosphere like gases and particles. And then we have ionospheric loss, also in decibels, which shows how much loss there is in signal, resulting in interactions of the ionized layers of the Earth's upper atmosphere. So the ionosphere is an upper atmosphere of the Earth is segmented into multiple sections, and the ionosphere is near the topmost, one of the topmost sections. And there's a lot of natural phenomena that occur that interact with signals because of the ionized nature of that layer of the atmosphere, which causes signal to decrease. So this shows, this is a measurement of how much signal that is lost because of this effect. And then we have receive parameters. These are just general characteristics of the receiver. We have the receive antenna efficiency, the receive pointing error. There's just a deviation between the ideal pointing alignment of the antenna and the actual pointing alignment. Then we have the system noise temperature, how much noise is created by a system. We have received line loss, which is between the antenna and the low noise amplifier, is in decibels, and it shows the loss of signal power as from the antenna to the low noise amplifier. So typically you have the antenna connected to the LNA, and it just shows the amount of signals lost between the during the transportation journey. And then there's the received demodulation implementation loss. So whenever you have a demodulator, you have some kind of loss of signal associated with it. This is a measure of that. And then we have the required EB over NO for BER. This is a very specific value, and it shows the minimum ratio of energy per bit to the noise of the power spectral density required for a specific bit error rate. So it shows the minimum amount of energy per noise. So how much energy you're getting compared to the amount of noise you're getting and it shows how much you actually need to maintain a specific error rate. All right, so to solve this CTF, it's asking for a wide range of things. So the first thing it's asking is to get the antenna gain. And in order to get the antenna, let me show you guys what it is asking for specifically. So here we go. Okay, so if you scroll down in the write-up, it says this is the documentation for the telemetry link, and you need to find a few key details that it is missing. So these are the values we are given, and we need to calculate. So the first question it asks is to calculate and provide the received antenna gain in dBi. So we are given in the problem, we are given the diameter, and let me see, yeah, we're given the received antenna diameter. Cool. So from given the diameter, we know the radius is half the diameter of a circle. So this should be radius. Receive antenna radius is 2.65, so it's 5.3 divided by 2. And we know the area of a circle is calculated by pi times the radius squared. So we plug in the radius. So we get pi times 2.65 squared, pi times 7, and that's 22. And then after you get that, you can plug in to an antenna gain calculator. So efficiency, let me see, yeah, efficiency is 0.55, so I'm going to paste that in there. We have the wavelength, which is this. And then we have the physical aperture area, which is what we calculated, which is 22. And if you click calculate, it will get the antenna gain. It's about 9.778. Oh my goodness, I think I adjusted the values. I'm so sorry. That wavelength, yeah. I don't know why it went to the negatives there. Yeah, it should be 53.86. After we get the gain, the second question the CTF asks is to calculate the gain to noise temperature. So this is a value of the antenna gain over the noise temperature, and it is typically used to indicate performance. And the way you can calculate this, you don't really have to calculate it. We can find a way around it. So just by having general knowledge of what these values can be confined to, we can brute force this. So just by doing a general Wikipedia search, you can find that an antenna gain to noise temperature has to be between 20 to 30 watts. So we can use brute force where we make a Python script, go through every single value between 20 to 30 in decimals, and then plug it into the solution. And the solution for the CTF ended up being 24.8 watts. And I can walk you guys through the write-up here. So if you can scroll here, this is the script. So it starts out at 20.1, 20.0, and then while while it waits for it to get the right answer, it keeps brute forcing it. And you can see it gets the answer of 24.8. And then lastly, it asks us to calculate transmit power. So this is a pretty tedious calculation, but you do this, so transmit power is this calculation here. And you do this by getting the carrier to noise ratio and then plugging it in to this very nasty calculation. So you can use an online calculator like this, or you pre-configure all these values, or you can write a script yourself in Python. I would recommend writing a script in Python. I think it's slightly easier and you don't have to manage all these calculations in your head. So the way this write-up shows is you plug in all the values for variables. So what you need is the required, not so you take all the variables provided to you here. So we have required, this one is 4.4. You got the data rate, the distance, the wavelength, the margin, the dBi for receiver and transmitter, and the loss we just calculated by adding up all the loss values. And by doing that, you get the noise decibel, the effective temperature, the bandwidth, and then a Boltzmann calculation, and then you can calculate the transmit power by adhering to this calculation here. So once you get those three values, you get an entire completed link budget for the telemetry link of the challenge, and it gives you the flag. For the second lab, we will be doing a satellite jamming simulator. The objective of this lab is to simulate basic radio frequency interference scenarios for a satellite in orbit of Earth. In this lab, will be simulating jamming a Starlink satellite. Okay. So about the simulator. So it simulates two isotropic antennas, one on a satellite and the other one located on Earth. And there's two antenna systems you can modify, the jammer and the defender. And the jammer and the defender are assumed to be operating in the same frequency, so it's tuned to the same satellite, and there's no protocol level implementation simulated. So it'll just simulate something that's unencrypted, nothing going on with the telemetry link. So we need to install a simulator. So the DoD offers a resource called the Space Jam simulator. So run the git clone command listed here and cd into the directory. So I can cd into my desktop because I have it installed on my desktop. And then you can run the npm, apologize, 30, and then satellite. Okay, and then if you don't have these modules installed, make sure you run npm install. I already ran this command, so I don't need to run it again. And then to run the simulator, go type this command, npm insert. And that will open up a local host server on your computer. So the local host server will be this URL, localhost 1234. So once it is built, you can type it in to your URL bar. Okay. So diving into the simulator a little bit, and I'll walk you guys through the process of this. We're going to be selecting a satellite. So in order to select the satellite in the simulation, you will, pardon me, you can go to the satellite jammer simulation localhost, type in Starlink under Starlink satellite, and then under these options, click the first one. So our target is Starlink 1007. And then once you have that done, I'll walk you through a couple of simulation terms and concepts. So we'll see EIRP, which stands for Equivalent Isotropic Radiated Power. And this is the radiated power from the transmitter times the directivity of the satellite. So kind of like gain, it shows you how much gain the satellite is pointing in a specific direction. So it combines the directivity aspect to it. We also have SINR, which is signal to interference and noise ratio. This measures the signal quality compared to the noise and interference. So in order to conduct a jamming attack, you need to wait for a satellite pass, increase the attacker EIRP, which is the gain of this attacker satellite antenna system. In order to defend the satellite, you need to wait for the satellite pass and then increase the defender EIRP so it's greater than the attacker EIRP. So the defender signal is stronger than the attacker signal, and vice versa if you want to attack the satellite. All right, so the way we will do this is we need to wait for a satellite pass. But in the simulation, the satellite pass is kind of slow. So there's this stepper ball function under simulation step size, which you can increase, and then this will speed up the simulation, and then we'll wait for the satellite pass to occur. And once we get communications with the satellite, so it shows satellite out of range at first, but once the satellite comes within the antenna range, it will go to communications normal. And then we can decrease the simulation size again to coordinate our attack. So let's do that. So here we have so here's my antenna, attacker antenna, defender antenna. So we need to find okay, so here's our satellite. Looks like it is heading on a pathway pretty close by. So I will increase our simulation step size just to make things go by a little bit faster. So just wait for it to pass over our satellites. Okay, I'm going to decrease it now. All right, it is within our range. I decreased it to 1 second. Communications normal. So here we have our SINR target, SINR clear, this looks like signal quality compared to noise. So now we can attack the satellite. So if I want to jam it, I increase the attacker EIRP value, and it says signal jammed. If I want to defend it, you need to make sure the defender EIRP is higher than attacker EIRP. So just increase this, and communications will return back to normal. So as long as the defender one is greater, it will appear that communications are normal, because the defender antenna transmitting power is stronger than the one of the attacker. So you can just play around with these values. If they're the same, it says the signal quality is degraded. And you can see that by the SINR here. So like if I were to decrease this, the SINR would get bigger because it shows signal quality. If I were to increase this, you can see it gets in the negatives because you see a lot of noise. So if the value of SINR compares the signal quality to noise, it will get in the negatives in decibels if it has a lot of noise. So the attacker is introducing a lot of noise, which causes the value to get lower. But when the attacker isn't attacking, SINR is good.